Dear colleagues, good morning. Are you with us? I think it's time to start our symposium.
Good morning.
Okay.
Great.
We are hearing you. So today we continue the symposium of metals and alloys, and I give the floor to our colleagues from Dnipro offline locations. Please.
Thank you very much. Good morning, everybody. Good morning, everyone, all auditory and all participants of 9th International Material Science Conference, HighMatTech-2025. Thank you for joining us. And we are continuing today, the second day of Symposium of Metals and Alloys. And we are ready to start. The first one is keynote speaker, Dr. Ramazani. Dr. Ramazani, are you online? Dr. Ramazani, are you online? Dr. Ramazani? Dr. Ramazani, have you joined us? Are you online? We are ready to hear you. So while we are waiting for keynote speaker, maybe we could go further. Is it okay? Here, dear organizers, could we move a little bit further? Oh, Mr. Ramazani, we can see him.
Good morning,
Good
Alexander.
morning. Dr. Ramazani.
Hello,
Dr.
good morning.
Is invited speaker, participant Ramazani, doctoral fellow at the Erich Schmidt Institute of Material Science, Austrian Academy of Science, Leuven, Austria, an expert in soft magnetic materials, metallic glasses, and advanced structural alloys. His research focuses on the ferrum-based soft magnetic materials, titanium and zirconium-based metallic glasses, and composites, nanocrystalline and metastable materials, additive manufacturing, and powder metallurgy. He will present a talk entitled Ferrum-Based Metallic Glasses for Magnetic Application, Fabrication, and Properties. Please, the floor is yours.
Thank you, Chair, for giving a nice introduction. First of all, I would like to say good morning for everyone, and thank you for giving me the opportunity to present my work. So it is really an honor to present my work among the elites in this group. So I am waiting for my screen to be sharing screen. Yeah, to share my screen. I think I cannot.
Yes, please share your screen.
The host has to accept it. I think you have to give the permission.
Dear organizers, please give an allowance to share the screen. Dr. Participant said that there is no allowance for him to share the screen. Dear organizers, give. Could you check?
Okay, I got it now.
Okay,
Thank you. Yes. Okay. Okay. I hope the participant can see my screen.
Yes, we see it.
Okay, so let me start. As I mentioned again, I would like to thank you all for giving me this wonderful opportunity to present my work. So I'm mainly working on iron-based metallic glasses for magnetic application. So today I'm going to talk about the general application of iron-based metallic glasses and their fabrication and then properties and how do we go, what is our motivation to work in this field. As most of you already know, the simple distinction between the traditional soda lime glass and the metallic glass. So any material which is cooled from a liquid, like from a hot to cold, it is called as a glass. But anything made by otherwise are called vitrification. So we can cool the traditional soda lime glass from a molten state to be a solid state. Similarly, we can do that for metallic materials. That's why it is called metallic glass, not simply glass. So it shows glass transition temperature, which is a key indicator for us to see whether it is an amorphous or not. This is a simple basic. But okay, if we do that, what will happen? Basically, it's a game with the entropy and disorder. We make them as much disorder as possible. Simply, it is called as a frozen liquid. That's how it's a. To put it in the perspective, you see, I have shown like a perfect crystal with dislocation and polycrystal, which we see regularly in our everyday application. But the glass, which does not have any order, so it's completely disorder. This is one of the important property of this glass. This gives a huge advantage compared to the crystalline counterpart. How do we achieve this? There are basically two ways we can achieve it. We can do it either the top down approach or bottom approach. Top down approach is like take any material, melt it to a higher temperature, we say, let us say Tm, melting point of the material, and then quench it as fast as you can. So then we freeze the material in the state as it is molten. So then we can get this complete disorder. Or we do bottom up approach. I mean, like bottom up approach. So we can build atom by atom, cluster by cluster. Basically, this is like CVD and PVD technique. In both ways, we can achieve this metallic glass materials with different varying thickness, size, shape, and so on. So that basically it depends entirely to us for what application we want to do and how we want to do. But the simple basic concept remains the same. We need to get the material as disorder as possible. So to put it in like a volume and temperature register, you can see it's liquid. That means we melted the many material to this highest point. Normally, crystalline materials are cooled slowly, and then there is a solidification shrinkage. But in metallic glass, that doesn't exist because we cool them so fast. So thinner ribbons are usually cooled at like 10 power 6 Kelvin per second, and then the bigger ones are like slightly lower cooling at basically 10 power 4 Kelvin per second, 10 power 3 Kelvin per second, and so on. Basically, it defines them as a bulk metallic glass. So give a simple basic definition. You can see this is a SEM of non-oriented electrical steel because we are working on magnetic material. So I think it would be an appropriate to give a proper example. So this is how you see when you take, okay, silicon steel, electrical silicon steel. This is how the grains are oriented. You can clearly see it. But when you take a metallic glass, then you don't see anything. In a SEM, you don't see anything with a metallic glass because everything is completely random and there is no grain structure or crystal structure to it. It looks like just a plane. So you don't get anything. So basically, metallic glass, if anything, any thin fibers or like ribbons we make less than 1 millimeter per, they are called basically metallic glass because they are not bulk. They are not considered as a bulk. But if you are able to make them more than 1 millimeter in thickness in any dimension, then they are called bulk metallic glass, be it a rod or plate or whatever the complex structure you want to make. But it has to be more than 1 millimeter to categorize as a bulk metallic glass. Otherwise, they are simply metallic glass. And then glass forming ability is a tendency of an alloy to show a glassy behavior. So with that, we just move on to magnetic properties. Most of you already know about the magnetic materials, hard magnetic materials, soft magnetic materials, and so on. There are like so many type of materials. So what do we focus in our work here? It's amorphous. So this is the range we are focusing on. So we are working in this regime, but not here. These are like mostly crystalline materials. Our work and focus is mainly on amorphous material. Okay. So is it new? Not really. It is not really new. This concept exists. It started in 1960s. To produce first production of amorphous material was reported in 1960s. However, the basic understanding of this material took time, some time, and to really make it something useful, it really even took some more time. But since 1990, we already started to have products available in the market, and it is brought to our day-to-day application, so that the advantage of these materials we can feel it in our day-to-day life, and then it gives us a great benefit in energy saving and reduction in heat dissipation and so on. This is a general picture. Okay, what are the exact values we are talking about? To put it in a clear perspective, see, you can see this fine made alloy was like somewhere like 1987, slightly before 1990s was discovered, and then you can see the saturation magnetization was barely 1.4. So then we moved on. We decided, okay, we need better. Then nanopump came. So those things were like typically made in form of ribbons, and then we decided, okay, we need more. Because constantly technology is evolving, and then we need more and more soft magnetic material to reduce the energy need. Because if the heat dissipation is one of the biggest problem in the energy sector, if we keep losing more energy in the form of it, then we need to put more input energy. So even for any battery related application, we need bigger batteries rather than a smaller batteries with efficient output. So it kept on going. We started to keep on working and working and working and working. So there are so many new alloys have been discovered, like in basically from 2010 to 2020 there is like a huge spike, like so many alloys were discovered. And then since 2020 there is a new stuff. There is even better understanding with the evolving technologies, and we could understand them even better. I will show you how do we really see that, how do we really decide in upcoming slide that this is good or not, how can we improve. Basically we can improve atom by atom. Yeah, to put it in a typical example, you can see this is a pure iron crystal. Then if we started to work with iron silicon boron system, then the core loss started to decrease. Then syntax 1, syntax 2, then we are almost in this regime now. Now we just keep going, and then we are reducing this energy loss to a great extent, as well as the eddy current. So does it only have a magnetic property, let's say functional property? No. These amorphous metal have excellent mechanical property too. You could see this is a typical like fracture strength versus Young's modulus curve, or like hardness versus Young's modulus curve. You can see these are like the black lines represent the crystalline materials. You can see super high strength steel is like nowhere near. Even the zirconium magnesium based ones are like far better than compared to the crystalline ones. So when you started to go with iron based metallic glass, you see they are excellent. They are like far exceeding the strength of any high strength steel we have known so far. You can see hardness as well. It's excellent. It has extremely high hardness. So being it, what are the application we are using it? What is the, bigger advantage? Why do we talk about this material in general? Yeah, because these materials have excellent properties. To put it in a perspective, low core loss, low coercivity, and low magnetostriction, and so on. You could see this. You might be seeing this kind of label in your day-to-day life in everything, being from supermarket to the high-end shops. You see this, and anti-theft label in the library and in many shops, like basically clothing stores and so on. Basically these has metallic glasses. So here this is basically metallic glass ribbon, and this is the back shield for this RFD antenna and so on. It is basically metallic glass because this gives them a longer range and avoid the wave dissipation. So these are some of the commercially available alloys which you can readily buy in the market and start doing whatever the products you want. So some of the consumer electronics which we are using in our day-to-day life has also metallic glasses. That's why the materials are electronics items are becoming thinner and thinner. You see mobile phone, laptops, and vacuum cleaner as well. Nowadays you can get more powerful ones with very less charging time, and you can use it for a long time. So mag limitation and so on. So how are they formed? Basically, so far the biggest application of this material are mainly from the amorphous sheets. Basically, the sheets are made in like tons and tons, and they were basically cut into or molded into different shape. needed for a different application. You can see this is a typical soft magnetic amorphous material and nanocrystalline material cores for different motor and applications. You could see basically these ribbons are maximum 40 to 50 microns thick. They were like cut into different or stamped into different things. Millions of those ribbons were stacked on top of each other, and then they made whatever the product they need. So this gives a unique advantage because these are very thin ribbons, and then the eddy current is very low, because eddy current basically depends on the thickness of the magnetic material used, square of the thickness. So basically if you use thinner ones and there is a lamination between every layer, and this is excellent. Okay, okay, we say it is core loss and so on. Okay, what is an example? You can see, you can ready. I mean, like, to a great extent you can reduce the no load loss when in comparison with the silicon steel. Then we can say the amorphous core transformer has a very low no load loss. That means it's very important, so that we can reduce the energy loss even without using. So to give even better perspective, this is a one-on-one comparison between the silicon iron electrical steel transformer core compared to the amorphous steel transformer. You can see when it is running, the temperature it picks up is too much. You can see this is with the thermal camera, but with amorphous core nothing. So basically that's why the nowadays the transformer comes without any coolant. Basically you don't need a coolant to cool down the temperature. It doesn't get heated up because you are not losing any energy. I mean, even if it is very minimal now with this latest materials. Okay, then these are other components which used in our day-to-day electrical circuit. We might not even see, but they are there. They are mainly played from the iron-based metallic glass. And one another important application, and it's much more interesting, is like now, since we are like moving slowly towards the fusion reactors, magnetic radiation is a very big problem, as well as in a running reactor or in the storing the nuclear waste. So amorphous materials are not affected by the radiations because it does not have a grain boundary. Grain boundaries are the weak region where the state starts to affect, and then from there the whatever the corrosion it happens, and then the material fails. So basically, with this amorphous material, we don't have a such problem. One such important application is like the storing the radioactive waste. You know, conventionally the radioactive wastes are like boxed in a such containers and kept it in a huge storage room. But the main problem there is like no one knows whether one container is leaking. It's $1 billion industry. If one container leaked in a enclosure, then that's the whole enclosure is, no one can use it. So, but by coating this metallic glass inside those containers, we can detect the magnetic property of this material, constantly monitor. If there is any corrosion or any changes to the magnetic coating inside the drum, then we can already detect it like few hundred kilometers away from the site. Then we know, okay, this container started to corrode. Then we can simply put the corrosion, the container with the problem to inside another container. So we can simply solve the problem, and then we can save a lot amount of money, and it is 100% safe. Apart from that, it's an excellent structural material also. In comparison with the crystalline material, it has a high fracture strength, large elastic strain, wear resistance, and corrosion resistance. So they are used in multiple applications where they need a long life for any component. So this is one such application. So these are AMO beads and Gala beads are like commercially available. You can simply buy it and use for any application, and their lifetime is 1,000 times stronger than the conventional steel material. And then it didn't stop there. So there are the steel powders, and we can coat the material for extreme environmental also. You can see they are like used in conventional power plant where it has a both high temperature and high corrosive environmental involved. So it has excellent corrosion resistant and temperature resistant. So this material is like will withstand, and it has a long life compared to any other materials. And also some of the critical examples and applications include like offshore platform and aircraft carrier. You can see compared to other crystalline material, the BMG does not exhibit DBD, ductile to brittle transition temperature, which is very very crucial when a single component is working in a like a very extreme cold environmental as well as in a warmer environment. So the material has to be very safe. So this is one such material. They use it in many critical components. to avoid the DBDT exposure. Yes. Okay. Then everything exists. Yeah, fine. But what is our motivation? I mean, our presidents discovered so many things, and what is our motivation? With the technology like getting developed every new days, then we are racing to provide a material which is suitable for the upcoming technology. It's not about the past; it's about the future now. Okay. I mean, people are already we started to work about 6G like 4 years before, because 6G is a technology, but we need a material to support those ideas. And then it would, if you cannot support a material with that, then it remains in the concept stage. You cannot materialize that material. I mean, that application, or you cannot utilize it. So for a high 6G means you need a material which can withstand a high frequency, and then show a low loss. So amorphous material is the only one which suits the purpose. So basically, with them evolve, every new technology evolving, then we also, as a material scientist, we also have to evolve to give the suitable material for the new technology. Otherwise, it's not possible. Yeah, that is our motivation. So we are working towards developing new materials for any application it comes in the future. So, being said that, okay, we always start from the basic. We should know the basic before we can design anything to a latest form. So simple rule for gas making analysis is very simple. It should have a three. This satisfying criteria, it should have multi-component alloys, which should be more than three, and should have negative heat of mixing, then significant atomic mismatch. Once we started to have all these criteria, the elements which meet, then we where this is the region, the point where we can find the metallic glass forming alloys. So as it is mentioned, there is always exception for this. So we have some exception in palladium-based metallic glass, but rest of the metallic glasses in any family, be it zirconium, titanium, aluminum, manganese, whatever this one, lanthanum, it falls in this category. So if we make that one, does everything has the same rule? No. We further classify them on what kind of elements we add. Simply metal type. This means only metallic elements are added into this to make a metallic glass. So magnesium, lanthanum, zirconium, titanium, hafnium, these things fall in this category. Then metalloid type. So platinum, palladium. So it needs both metal and metalloid elements to make a metallic glass. Then metalloid type, we have iron cobalt nickel. So this completely comes in a different category, because this iron cobalt nickel based metalloid does not obey the rules which are given to this type of metallic alloy, because it has a different purpose, and also they are like stronger in comparison with other materials. So there are and then it needs a lot of metalloid elements into it, so that makes it much more complicated. So the rules for making these alloys are slightly different in comparison with the other elements. So I don't go deep into that, but yeah, to put it in perspective, that's how we classify, and then we follow certain rules to work on this one and make these alloys. Okay, so how do we develop? Okay, ribbons is the basic for anything which we start. So there are many phase diagrams. There are many pseudo binary, pseudo ternary, pseudo quaternary phase diagrams we follow to see where it is possible to get a metallic glass forming alloys. It's not possible to make everywhere. In certain space, we could match it. So at that point, we should have a combination of all these elements: large atoms, intermediate atoms, and small atoms. Once we are able to reach a certain specific ratio, which we observe, based on the experience on one, so only those points we can able to make the metallic glass. So once we know where we can exactly play and make the alloys, so simply we melt them and then start to make amorphous ribbons out of it. Okay, so ribbons are basically made with this melt spin ribbons. It has a cooling rate of about, let us say, 10 power 6, 5 to 10 power 6 Kelvin per second, which is very typical for this kind of melt spin up yeah, melt spinning process. Then okay, perfect. Once we melt spin it, then what do we do? Then we decide how do we need to go, in which way. So in comparison with the traditional crystalline material, you make it in a bulk billets or whatever it is, then it's sent to series of steps in size reduction and so on. It is more than a kilometer. I would say. So we make, in the end, we make such things. But with the metallic glass, it's much more simpler. We can simply uh, cast it and then roll it in the coil, and it's much more simple. And then we need a small, very less space. Also, from the amorphous one, as I mentioned before, amorphous metallic glass were like applied in a certain areas, but when we need a high frequency application and so on, then we move on, we go to a different level, and then we engineer the atoms by atom, so that we can get a nanocrystalline one, so that it has even better property compared to the traditional crystalline ones. So to give it in a perspective, so this is amorphous phase. This is what like most people do. Then we add or dope few elements which act as a nucleation sites, and then the nuclei start to grow. Then, upon heating further, the crystal structure changes. Though the temperature up to which we heat, it is decided purely on the application purpose and what do we need to achieve in the end. Because we cannot randomly heat it, because we need to monitor how big the crystals are forming, how big the domains are forming, because that is very important for us, especially soft magnetic application. If we have a bigger domains and bigger crystal, then they are not suitable for our applications. So how do we decide it? Basically, we decide it by doing in-depth characterization. For example, TM. Okay, then we take a sample. Then you can literally see in this one. This is like, I don't know. We just did it like 2 weeks before. Yeah, I would say you can literally see this is amorphous matrix, and then the crystals are already there. Yeah, so this is a fine. We can already see how big the crystals are going, where they are going. Okay, then how do we control them? That is next to the point. We need to know the orientation of the atoms, and then we can control. You can see we did some high magnification, and then we saw the crystals, and like what kind of crystals forming. You can see there are two different types of crystals are forming. After annealing at each different temperature, then we see what temperature it started to form, and then when it started to crystalline and how it started to crystalline. So then, to even better understand that how the atoms are arranging themselves around the crystalline block or nanocrystals, what is the point, what is the origin of making such one. Then we do such atom probe tomography. Basically, in atom probe tomography, you could see we have this is a ribbon. We thinned it down to APT tips with the laser, and then you can see the tip we will investigate is like basically 100 nanometer. In that 100 nanometer, every atom is taken apart atom by atom, and then it is completely recorded in the screen. You can see when the tip is there, the laser knocks out every atom, and then it is their properties are recorded, and then it is replicated on the team. Then our example is, you can see how do we do this. This is completely for amorphous one, and this is for nanocrystalline one. You can see here, this is amorphous tip which looks completely like this, and then if when you started to have a crystal, you can see there are like a multiple amorphous zone and crystalline zone. So we see the orientation, how it forms, we see how big the clusters are forming, and so on. Then we decide how to heat and how to reduce the cluster size and so on. So this is very important to see and connect the magnetic property and the heat treatment to it, so we can now exactly pinpoint, okay, why we are having this higher coercivity at this point. Okay, the cluster is bigger, the stress is higher, then why does it go down? The cluster is dissipating, and the nuclei is dying down, and then basically we have alpha nuclei formation which have a lower coercivity compared to the other crystal. What type of crystal it forms, why it is increasing at this position, and why it is the slope is decreasing. So each and everything we can figure it out, and then we decided, okay, how we can go. So this technology improvement gives us a huge advantage in doing so. Yeah, then we decide like, okay, which is suitable for permeability, then for like coercivity, high saturation magnetism, why it happens, so on, so on, so on. Yes, well, it looks nice, but okay, does it, that's it? No. I mean, we have a different application. Not everything revolves around the ribbons. There are different application which needs the bulk form. Okay, how do we make a bulk metallic glass out of metallic glass? So it's simple again at thermodynamics. So this is a typical cooling curve. You can see what we are doing for obtaining a metallic glass ribbons is basically we are quenching them as fast as possible. Let us say more than 10 power 5 Kelvin per second. Yes, excellent. But if you want to make it a bulk, cooling this high, it's not possible because that's a huge amount of thermal stress, and it is not possible to achieve a uniform cooling throughout the material if there is more than 1 millimeter. Then what do we need to? We have to push the crystallization nose towards the other side so that even if we cool them slower, there is no crystallization is happening. So even if we can cool 10 power 3 Kelvin per second, then still it is amorphous. So how do we do that? This is done by careful addition of alloying elements and studying, how each and every alloy addition behaves and how to improve them. That's what we do. So if you are successful in designing one, then we make them, we cast them into bulk using suction casting. Let us say, okay, we make a rod. Perfect. Then what kind of application we can imagine for such kind of rods? So one such example we worked with is basically for the nails, for the nail guns. Yeah, because of its excellent strength, it can be used, and then it can be used in environment where we don't need to worry about the corrosion or failing, or like with a harder material, so the metallic glass can penetrate the harder material also. So it is chosen, these are the alloys we worked in this for specific application. So okay, then it looks nice. What are the problem we have? But they are extremely brittle. And then when we started to go for a complex shapes, they started to fail in the mold itself. Let us, this is one such key we formed. So they are simply failing. So because of the thermal stress, and then it doesn't like the gradient in the design. Whenever there is a stress gradient, then it simply fails inside the mold itself because they are harder and extremely brittle. So how do we overcome this problem? Because it's an excellent material. So when we were interested in using this for several applications. Okay. Is additive manufacturing the best strategy to produce PMGs? Yeah, we would like to explore this as well because few people have proven that it is possible to build complex shapes with iron based with the metallic glasses. I mean, we still have a lot of speculations around it and so on and how. But yeah, it is possible. The design is possible. Additive manufacturing is an excellent technique, so we can make happen several things in this one. So we wanted to explore that option as well. So we chose a certain alloys which have like a very nice glass forming ability, and then they were atomized, and then the powders were characterized to see if we still have an amorphous powder or crystalline ones. Getting an amorphous powder is another little challenge because it gets a lot of impurities and oxygen from such a big chamber. You could see it's at 12 kilograms, and then the useful powders we got is basically half of it. No, it's like only this much we can use it for 3D printing, and then yeah, still then we started to have inclusion because of improper cooling rate in the entire glass atomization chamber. Yes, but still we were able to make them amorphous by adjusting the condition. Yes, then you can clearly see the glass transition temperature and so on for the two different alloys. Then we work with the additive manufacturing. As you could see, the results are not promising in the beginning, but yes, with the constant parameter optimization, then thermal management, we were able to achieve a sample which are not really failing in the first attempt. But you could see there's a lot of residual stress. And you can see this like the amorphous form on the top, and there is a huge bump in this one. We don't really understood why it is forming in the beginning, but yes, with constant monitoring and parameter variation, we were able to make the bulk samples without any cracks in various shapes you want, be it a straight or in an angle, we can produce it. But again, the disadvantage is that if you are not able to make them fully amorphous, we have to play constantly in between. How do we want the sample? We want the crack free sample, or we want the sample with a combination of both amorphous and crystalline. Basically it's a composite. So that is the part we are constantly struggling to decide which one would suitable for the application, because some of the metallic glasses with excellent magnetic properties are very sensitive, and then once the crystals are become too big, then it has no useful for us. But it can be used the structural application ones are pretty forgiving, so we can use such composite material for structural application. But we are constantly working towards finding a way, or basically it's the thermal management, it's the key in this 3D printing of metallic glass. So if we are able to achieve a proper thermal management there, we are pretty much optimistic that we were able to produce fully amorphous in the materials in iron-based metallic glass by 3D printing. Okay, then how do we improve it? Because I mean, what we had one another problem with this gas automation, we had a lot of impurities from the ceramics or crucible used for atomization process. So we started to use new techniques like ultrasonic atomization of metallic atomization process, where the advantages is like we can completely control the environment as well as the oxygen, and it can be fully automated. However, the limitation is like the low production rate and low cooling rate, but we can always play with the allowing elements to adapt to the low cooling rate. So these are like some of the experiment we did. So you can see the powders we produce from this are excellent, 100% spherical. I mean, I would say 99.5% spherical, and then they don't have any satellite particle. This improves the flowability of the material, because with this less flowability, then we also started to have pores in the 3D printed samples. Since these are like magnetic metals, even a presence of a single pore or single crack will reflect in the magnetic emission. It might not be a big problem for the structural application. However, functional application, it is very important that we achieve the highest possible density and without any cracks. So it is important how the material is flowing, how we are able to print them. Yes, we've worked with few composition, and then we are able to constantly achieve the amorphous space within the given range, which is more useful for us for a 3D printing. Then we were also started to work on like slightly different field for chemical application. Let us say hydrogen evolution reaction, or like a dye cleaning application. So we started to focus on amorphous nanoparticle. This is so why amorphous nanoparticle? Okay, that nanoparticle constantly produced with a different form, placing like chemical method or biological method. What's the difference between this and why it needs to be amorphous? Yes, because amorphous material has a completely different properties, because it has a lot of bonds, and it can be used to enhance the oxygen evaluation or carbon dioxide reduction reaction, or like hydrogen evaluation reaction. So these are like highly explored in recent days. You could see most of the recent publication, they are exploring in this region, how we can improve the OER reaction, carbon dioxide reaction, HER reactions in this metallic class one. So main advantage of that, there is a high distribution of defects. So concentration of higher concentration of coordinatively unsaturated sites. So and loosely bonded atoms in the amorphous structure. So this basically gives us the bigger advantage to have like a higher surface for reaction. Okay. In our case, since we need amorphous material, so there is not many ways to produce them. So the one which is right away available is like laser ablation in the liquid. So basically, you can take a target and then you can melt it inside the liquid, and then you can produce a nanopowder. So is it as simple as such? Not really. You can see this is example. Give me a second. My video is not playing. Yeah. So you could see this is like a atomization of gold. So you can see it takes a while, and then you see there are a lot of bubbles forming on top, which is really bad for us, because though it is a nanoparticle, the formation of bubbles really reduces the cooling rate to a great extent. Once the cooling rate is reduced, then it becomes crystalline. It's not suitable for our application. So we need to find a way to work around, and we need to understand the basic principle why the bubble forms, how we can overcome it. So we started to work with some materials which are very much um, useful for the application we intended for, basically for HER reaction. So we chose an iron, cobalt, boron, silicon, and alloy, and then that ablation process was carried out in multiple environments. So acetone, water, or like water with sodium citrate. Basically, this is a additive to added to avoid the agglomeration. You could see in the one which we synthesized in the water, they started to agglomerate, which is not good, because once they started to agglomerate, then they started to absorb more heat and then they became crystalline. So we wanted to avoid that. So these things were done. This is one such. Basically, we made it with a master alloy and then it is atomized here. Then with the understanding, we could see once the material is hit by the laser, then it's an explosive boiling. So those material, it's a kind of explosion. You might have seen from the lot of bubble formation. Basically, this is that bubble. Those particles who escape from those, basically it comes out as a fully amorphous one. But some of those particles which did not and escape from the bubble, then they slowly started to get entrapped in this one, and then they started to become bigger. You could see. Then the cooling rate decreases. This is the fast cooling. It will get to 100% amorphous. But when the cooling rate started to go down, we may end up with amorphous shell, but inside it is basically a crystalline one. It's like in a composite. And then after a time, that bubble started to shrink. The particles comes out. Then they are completely crystalline. So these particles are no more useful for us. So we need to find a way to either to reduce the bubbles or increase the cooling rate so that we can still get the amorphous particles out of it. So this is like a new technique. We are also working on it. So yeah, one such example is like we have this powders we produce from the acetone. You could see the output is very low. That is also another problem we are dealing with, because since it is a nano powders, the output is extremely low, and we need to have a considerable amount of powders to work for, to test for any application, and it is entirely disposed in the media. So that also adds an important factor, how much material can be dispersed in a given media, because we cannot expose those material to a laser for long term, because iron and cobalt and nickel are basically black metals. It absorbs a large amount of energy. So we chose the time and exposure, and then what do? We come up with a simple idea used to centrifuge. Basically, with the centrifuge, we were able to separate out the material. So the simple example is like when we expose the material for like laser beam for 3 minutes, then we get less than 1 micrograms. This is the current state what we have now. It definitely could be improved, but this is just like new field we are working on it. So yeah, if we are trying to improve different techniques, different ways to get a large concentration of the powders. Yes. With that, I would like to move to the summary. Yes, metallic glass offer a unique properties for various engineering application, but the practical use is limited because of the size limitation and the challenge involving intricate geometries through conventional fabrication. Yes, additive manufacturing allows BMG with intricate shapes and so on. There are techniques like SLM, DED, LPBF, and so on. However, achieving a full amorphous structure is still challenging due to the thermal gradient and thermal cycle. So, as I mentioned, the thermal management is a crucial part to overcome this one. And then amorphous nanoparticles can be controlled if we again overcome the thermal gradient part. With that, I would like to thank and acknowledge all the people who helped me in doing this show. And thank you for your attention. You could see this is iron-based metallic glass ribbons. They cut and then they made a thin tube out of it. So it's an excellent material. You can do anything you want with this one, provided if you know what kind of application you need it to use for, and then yeah, you have excellent material in your hand. Thank you.
Thank you very much, Dr. Ramazani. And I would like to open the floor for discussion. Who would like to answer the question, dear colleagues? Please raise your hand and I'll come into you. Who would like to ask something? I'm coming.
Good morning.
Hello. Morning. Yes.
Good morning, Dr. Ramazani. This is Podolsky. I have a question.
Yes.
Thank you for your presentation. It's very interesting. My question is, what size for BMG do you achieve now today?
I mean, in iron-based metallic glass, or I mean, as mentioned, like the metallic glass are used in like many, like let's say zirconium-based, titanium-based, platinum-based, palladium-based. So the biggest one in general, when you say biggest metallic glass, we have like 20 centimeter diameter rods.
Oh, thank you.
Yeah, that is. I mean, sorry. I mean that is for basically what is platinum and palladium based. So those are really expensive, but you can find those in your costly Rolex watches and so on. Basically, they have it. That's why they are expensive.
Thank you.
Thank you very much. And who will be the next one? Who would like to answer the question? Dear colleagues, who would like to answer the question?
Hello, can we ask a question from
Yes,
EU
of course.
location? Alexander Vasilyev here. Thank you very much for a very interesting report. I have one question related to the additive manufacturing. So
Yes.
clearly, yes, it's promising technique. But as we saw from your slides, there is a lot to do. Did you consider or looked into application of machine learning, in particular Bayesian optimization, to solve the problems in complex with the printing?
With the printing, not yet. I mean, we have two problems in it, but because this is an excellent solution, because we are looking for the machine learning approach in the high entropy, because it's easily doable in crystalline materials, because we have a lot of database, much more reliable, available to give a feedback and then take it to the next level, especially with the amorphous materials. And for example, zirconium based metallic glass have been already proven to be printable, but with iron based there is a very less literature available for us to take a data, and then it even varies a lot based on the type of technique they used for atomization and so on. We need more and more input to really get into that, but that's an excellent approach. For any other crystalline material, we are using it and slowly started to make an iteration and so on. But iron based, it's still a lot to do, especially with the 3D printing. It's simply too expensive for us to explore in so many directions. Yes.
Okay, so our team is involved in optimization of robocasting techniques. It's different, of course, than laser powder bed sintering or something like that. But the principles are similar, so we would be open for collaboration if it's interesting for you, of course.
Yes, definitely. Thank you. Definitely, thank you.
Thank you very much for the report.
Yeah.
And who would like to answer more questions, dear colleagues? So
may I ask one more question? It's a very quick question.
Of course, and then
I would like also to say thank you for a very interesting and insightful presentation. And I paid attention that your powders you obtain can be available to deposit coatings by thermal spraying techniques. How do you think? Is it reasonable or not?
I mean, it is reasonable to do it. We can do thermal spray coating also, but if we have any project, then we are happy to supply. As I mentioned, this. I mean, we were able to constantly achieve a nice powder, but this new technique is we need a little more tuning. But if anyone is interested to have such thing, we would be happy to send some sample if you could try it out, because I mean, we don't have that setup, but we are like more than happy to try in that region also.
At Frantsevich Institute for Problems of Material Science, we have almost all thermal spraying techniques such as plasma, detonation, HVOF, and cold spraying, and we will open for collaboration. Maybe we should think about applied, for example, I know that there are Austrian, Ukrainian projects, such projects are available almost every year, so maybe we can
Yes.
apply together to do such work.
Yes, it's
Thank you very
definitely would be nice. Yes, thank you.
Okay,
Thank you.
thank you.
Thank you very much. And yes, are you here still? Dr. Ramazani, are you still here?
Yes. Yes.
Yes.
Yes, I'm here. I'm here.
Yeah. And I would like to ask maybe the last one question. Yes, and I would like to thank you for the amazing report. And what about the stability of the obtained ferrum-based metallic glasses at elevated temperature? Have you estimated?
So our materials, we have it is stable up to 450 Kelvin per 450 degrees centigrade. Because this is quite precise in our case, because it is extremely important for us to know up to which temperature it can be used, because beyond which these materials are like, it will crystallize in a minute. So that is like a real limit for the most of the metal we do work with. But some of them with the tungsten based, it has a higher limit, but they are structural application, not for functional application.
Thank you very much. Thank you, Dr. Ramazani, for real great, amazing, very applicable and useful report. And we wish you the best luck in your work to fulfill your doctoral fellow. Wish you good luck. Thank you very much.
Thank you.
And the next one is Rostislav Podolsky. Influence of process parameters on the morphology of single thread produced from 330L steel using LPBF technology. Please, Rostislav, the floor is yours.
Good morning. Thank you. Good morning, dear colleagues. Please. My name is Podolsky Rostislav, and together with my co-authors shown on this slide, I am pleased to present our research working title, Influence of Process Parameters on the Morphology of Single Tracks Produced from Stainless Steel using LPBF technology. Currently, experiment single tracks very most popular experiment, and a lot of scientific in world use this experiment in the LPBF technology. This experiment used for the development new alloys. It's a search development rational parameters for the printing high quality samples. Next. Second variant for the using this test, it's checking correctness working 3D print parameters. It's an optical system and AST. But when we used this test experiment single tracks, it's very justified for the development alloys. But when do we use this parameter, this test for the already known alloys? This question is this test using for the already known alloys for the check and analyze optical system circulation.
I'm really sorry to interrupt, but what we see is the presenter's view, not the slides, not the presentation but the presenter's view of the presentation. Could you maybe switch to full screen presentation instead?
Они не видят полной презентации, то есть только перед презентацией, только ожидание презентации, перезагрузить презентацию.
Okay. Сначала включите F5, а потом выберите дату.
We are trying to manage it right now.
Yeah, that's much better.
Better.
Thank you.
Thank you so much.
It allows you to take into account various technical characteristics of machine, the applied protected environments, and the same cases actual chemical composition which can affect the final rational parameters. In addition, the study of the single tracks of already known materials is ordered and explained database and ideas about crystallization process for the known materials is relevant. The general idea of this work to determine the parameter of influence on laser powder scanning speed and location of the building platform on the geometry and microstructure and single tracks during laser fusion of metal powder under the condition of dynamic focusing of the laser beam. This research have three stages. First stage is to produce single tracks with located across the building platform at conducting visual optical control. Next stage is metallographic analysis and studying crystallization fusions. Final stages it's research of rational parameters into account the influence of the location of single tracks across section on the platform. In this work, we are used all known material is stainless steel. Actual chemical composition this steel shown on the slide. For the printing this test sample single tracks with other position on the building platform. We used 3D printer LPBF using LPBF technology Alpha 280 with a building platform size 280 or 280 millimeters. And in the single tracks have 16 combination with 13 sub platform with on the build platform, track quality, melt pool morphology, and other analysis with optical microscope with bright field illumination and chemical engine as the samples with scattering reagent number 2. Statistical analysis of the obtained data was implemented uses skeleton library, which is relevant for regression task in Python. Main results. As results of the analysis of database obtained using metallography of single tracks, it's shown that outliers of values when applying same power and scanning spin along the plane of the building platform mainly affect the average values of width and length single tracks. Using the obtained data from the histogram shown on this slide to detect outliers, data samples was formed based on the results of metallographic analysis. The width and depth of single tracks using polynomial regression, the influence of the power and scanning speed parameters on the geometric parameters was established. Thus, as a result of the conducted studies, it was found the change in the scanning speed mainly significant effect on the depth and width of the melting pool. At the same time, the power and more linear effects increasing both the depth and the width. Another determinant for futures of the influence of the location of the build platform on a crystallization and experiment single tracks. The study in this study we are investigation single tracks with parameters power 150 watt and 500 millimeters on second. Comparative analysis of single track with this technology parameter was chosen in connection with the related dependence number, increasing for the scan spin to 500 millimeters on second. Each single text with parameters up to 500 millimeters on sec with power 150 watt demonstrated a threshold scanning speed which was influenced by additional factors. Many tracks showed a clear outline of the molten pool typical of conduction melting and associated with coarse dendritic structure. The region between the intermediate bottom and the final bottom of the molten pool was identified as party and melt zone rather than HAZ, due to feature associated with solidification. It is possible to observe the effect curvature of the melt pool depending on the location of single tracks on the platform surface, mainly the effect of associated with the magnitude of the correction of the focal length and angle on increases as the laser spot. In conclusion, the regrets of the formation of the single tracks in laser metal condition under changing technology parameters and determined it is shown that scanning speed has a predominant effect on the depth and geometry stability of the melt pool. A technological window of rational parameters is established and ensure the formation of defect-free tracks. However, it varies depending on the special position on the build platform, microstructure analysis, the influence of focal correction and beam inside this engine on the distortion of the shape of the melt pool. The application of machine learning methods, polynomial regression with use Skyline library allowed us to build a model the influence of parameters on the geometric characteristics on tracks, which can be used to optimize additive manufacturing parameters and predict tracks stability in various special construction conditions. Thank you for attention.
Thank you very much, Dr. Podolsky. Dear colleagues, who would like to answer the question? I'm coming.
Thanks for your really interesting and useful report. My question is, why does the position of the sample on the platform affect the morphology of the track and the stability of the melt? Thanks.
Thank you for a question. It's a very interesting question. Maybe this depends of several reasons. This is technical characteristics of the machine, and in second, it's correctness working and adjustment of the position or optical system in 3D printing, because optical system is a technical characteristics 3D printer, but correctness working sometimes not right working with other position.
I got your point, thanks.
Thank you. And who would like more questions? I'm coming.
Thank you very much for very interesting presentation, and I have some question for you. How does the depth to width ratio 0.68 determine the transition from conduction mode to K-hole mode?
Thank you for the question. Please, slide 6. On slide 6, we are shown results with the window technical parameters, rational technical parameters for this stainless steel. and increase the depth or with coefficient 0.68 on the green line on this slide. One moment. However, as a results of studying samples with parameters located on this line, deviations, and now we research in this work results or rational parameters on this technical window. Maybe in future we are more research this question in the green line on the coefficient 0.68, because now we have very interesting results, because on this line we have a single tracks with power different parameters of power and current speed. It's and this one problem, because good tracks have maybe 30%, and the single tracks with defect maybe 70%. But on this diagram, we know for the position. It's a red position. It's a K-hole defects. Blue position. It's a lack of fusion, and we didn't show on this picture zone with defect volume. But in future we are research the investigation this position in the green line. Thank you.
I wish you good luck for the future research.
Thank you very much, Dr. Podolsky. Dear colleagues, any question more? No? So thank you very much for your interest in the report. And the next one is Yuri Podrezov. Abnormal superelasticity of intermetallic titanium-3 stannum. Yuri Podrezov, are you online? Yuri Podrezov. Yuri Podrezov, are you online? I can see you. The floor is yours.
Good day. Anomalous superelasticity of intermetallic T3 stannum. The problem concerned an unusual mechanical behavior of intermetallic T3 stannum in the elastic region of loading. There are three types of stress-strain diagram in the elastic region of loading for different class of materials. Yes? Ладно, не показує. Добре. Так. The G-shape loading curves behavior characteristic feature of biological thesis. There are three regions of diagram. The first region relate to low loads. The linear section with a small slope angle determines the modulus of elasticity. In this case, such behavior of materials are studied by biomechanics. It is clear from the table that natural biological thesis exhibit G-shaped loading curves with very low modulus. Что-то не переключается. А вперед это. Точно. So, synthetic material with a G-shaped stress-strain behavior are used for various fields of bioengineering. The slides show illustration from a mass article with example of artificial materials that demonstrate G-shaped loading curves behavior. It is a smart textile which are used for chips or sensors, or artificial muscles with hierarchical structure. Переключилось, да? Metallic superelastic helix demonstrates S-shaped load curves behavior. In this case, the superelastic region is always preceded by elastic deformation of solids with Young modulus that is several order of magnitude higher than the elastic modulus of organic and more than bone. That is maybe see in graphs. In this case, sigma, that is not yield point, but that is the so-called trigger stress at which elastic twins are initiated. Usually this value 50 of 500 MPa. Просто быстро. Не получается, ладно. Titristanum is the only metallic material that behaves similar to organic materials and exhibit J-shaped load curves. Mechanical behavior, as usual for metals, was established as a result of serious mechanical tests or both binary or alloyed Titristanum in static and dynamic modes. Не переключается что-то. Он меня просто не слушается. Будешь ты переключать. In this slide, the equilibrium fast diagram of Titristanum system. In this case, the X-ray diffraction studied on crystallized structure have shown that it has the hexagonal structure. Latest parameter we can see in the slide. The closed следующий. The closed structure analogous to hexagonal Titristanum is well known intermetallic T3R. In this structure state both intermetallic are polyplastic with a high modulus of elastic, approximately 130 GPa, and large anisotropic of flow stress. The characteristic feature of the deformation are shown in slide. Дальше. The crystallographic relationship between the lattice of hexagonal orthorhombic but under cooling, high purity, intermetallic Titristanum occur martensitic transformation from hexagonal to orthorhombic phase. This is confirmed by the result of X diffraction and obtained from the electron micrographs. Orthorhombic phase have the structure we can see in a slide. Semi-accommodation twins microstructure of orthorhombic phase is observed. Done. The crystallographic relation between lattice of hexagonal orthorhombic fuzz are shown in slide. The transformation from hexagonal to orthorhombic lattice is accompanied by a contraction of 1% along x axis and elongation of 0.5% along the y-axis. The change in crystal volume 1%. Martensitic phase transformation conformed by the result study of temperature interval for shape recovery. The dilatorimetric studies during heating, calorimetric study of tetrastanum, and determination of electrical resistance. Bending test was determined by 4-point bending scheme. In this slide, the beginning part of coarse stress strain behavior. We can see that the part with the big elastic modulus, in this case, sigma triangle is less than 0.2 MPa. That is, curves have the G-shape forms. In this case, the value of yield modulus can be obtained from these experiments is very low, essentially lower than elastic modulus of bones. Effect of grain size on elastic modulus was analyzed based on the results of compression tests. The accuracy of this experiment is very good, and we can see that in this case we have a G-shaped behavior too. But the value of elastic modulus depends significantly on the grain size. Tensile test were also performed with a high precision strain measurement. The strain curves is shown in graph. In this case, we can see the super-elastic mechanical behavior with extremely low elastic modulus in the early stage of deformation. At the initial elastic modulus is lowest. After unloading, we complete have the restoration of shape. At the next stage, the modulus higher, and we have the small residual strain. The beginning of the bending in curves explained by the change in the propagation mechanism of elastic twins. The slide shows the results dynamic mechanical analysis. Analysis the effect of temperature, the elastic modulus, and damping capacity of tetrastanum alloys. The sensitivity of elastic modulus and damping capacity to the content of alloyed elements. The elastic modulus increased with the increasing of alloyed element content. The more modulus value given in the table are close to those obtained from the close to those obtaining to bending test. Experiment in which we it was investigate the elastic behavior of titanium studied by resonance oscillation method is shows that modulus Young modulus of titanium decrease with increasing of cyclic amplitude of deformation. Mechanical damping decrease with frequency. The Young modulus increase, but the dependence is not monotonic. The slide shows some of feature of deformation mechanism of hierarchical twinning microstructure. Fractal nature twins microstructure is important because the fractal are the characteristic features of biological tissues and exhibit G-shaped load curves. The presence of fractal nature of the twins structure implies the involvement of declination to implement the super-elasticity mechanism. The analogy low value of elastic modulus and the step-like nature of the pseudoelastic curves are explained by the special role of declination in the reorientation of twin structure. Conclusion. Titanium is only the metallic material that behaves similar to the organic materials and exhibits G-shaped load curves. The elastic modulus and damping capacity demonstrate sensitivity to grain size and alloyed element content. The elastic modulus increases with the increasing element content and decreasing grain size. Low Young modulus and high damping capacity are consequence on the reversible motion of twins boundary and or the reorientation of twins under the action of applied stress and their interaction with obstacle, grain boundary, microstructure, other twins boundary. Abnormal superelasticity of intermetallic titanium explained by the fractal nature of twin structure and special role of declination in the reorientation of twin structure. Thank you for attention.
Thank you, Dr. Padrezov. You have a really vital, pliable, very interesting report. Thank you very much. Dear colleagues, who has a question to Dr. Padrezov? Yes.
How did you get experimental titanium, stanium, and zirconium doped alloys?
Please repeat your questions because the sound was not very fine here.
Do you hear me?
We hear, but not very well. But we'll try again.
1, 1, 1, 2, 2.
Okay.
Okay. How did you get experimental titanium, stanium, and zirconium doped alloys? In what way?
Такий експеримент титан-цирконіум. That is titanium, that is not titan-zirconium.
Okay, how did you get the titanium, stanium, experimental alloys? How did you get, in what way? What was the question?
That is the high purity titanium in the state after melting. The main problem that is high purity materials. In this case, we have such structural
Thank you very much. And the next question will be mine. What is the bio-influence of your beta composition? How does it influence with the human liquids, for example?
This is very interesting problem. In this case, the value of young models less than the value for born. And we can have different value of models in the different structure material. That is why that material we can investigate and used for the biomaterials for in different variant of used. Maybe for the chips, when we have the same object, and that may be the implant of bone, but in this case we can have more materials. And that is problem because it is very expensive materials.
I see. Thank you very much. Dear colleagues, who would like to answer more? No? Oh, thank you very much, Dr. Podorezov, for a very vital, very pliable report. And the next one is Konstantin Korniyenko. Features of physical-chemical interaction in the aluminum-titanium DM7 to 8 ternary systems. Konstantin Korniyenko. The floor is yours.
The title of my presentation is Features Physical-Chemical Interaction is a ternary system formed by aluminum with titanium and the metals of 6-8 groups. Applications of this alloys are very wide. These ternary alloys are promising for practical applications, various fields of modern technology. And here are the components that form these alloys. And the fourth row is from the complete periodical system. These 5 elements are not used. And these 15 elements, 6B group, 7B group, E, and 8B group, these 9 elements. And one of the main tasks of material science of these objects is to increase their heat resistance while simultaneously preserving low temperature ductility and the oxidation resistance. Really, it is a very great problem, the embrittlement of the alloys at low temperatures. And for a promising way to solve this problem is creation of multi-componented metallic alloys based on titanium aluminides, titanium trialuminum, and titanium aluminium, alpha 2 and gamma, which are widely known as the basis of structural materials. And to improve the properties of materials of that class, complex alloying of aluminum titanium alloys is used, in particular of the metals of 6 to 8 groups. For the design of new structural functional materials based on these components, understanding of phase equilibrium and phase relations in the corresponding ternary systems is necessary. Usually, phase equilibrium studies often by annealing of the alloys at certain temperatures to study structures of these alloys and properties, and at certain temperatures to plotting isothermal sections. But this is incomplete. Also, it is necessary to study the path of crystallization of the alloys and to construct a structure at under solidus surface and to build solidus and liquidus surface. This will be allowed to know about peculiarities of formation of the structure of the alloys during crystallization, and to design the regime of special paths of crystallization to forming their structures and to annealing of these alloys. And our experimental investigation for equilibrium during solidification, it was carried out in Svantsevich Institute of Progress Material Science, Department of Physical Chemistry of Inorganic Materials. These form ternary systems with chromium, rhodium, palladium, and platinum. They used experimental techniques. Alloys were melted by arc melting or levitation melting, homogenization, and various techniques of physical chemical analysis. As a result of these studies of alloy system, phase equilibrium during solidification are represented by elements of phase diagram. They are solidus, liquidus surfaces, melting diagrams, superpositions, Schalk diagrams for solidification, and the vertical, or it's called temperature composition section, so isoplates. Here is aluminum, titanium, chromium system. One of the examples, this is solidus. Surface of it, one ternary phase form in this system. And about history of study of this system, first of all, this article in Johnson Compounds was published, and 1 year later, also was thermodynamic modeling of the system with refined aluminum chromium boundary system description was carried out with participation of scientists of our department, Bondar. And next, this our publication is 2022. This was a laureate of Fabric Best Paper Award for the best article in the world in 2022 year devoted to the phase equilibria and diffusion and thermodynamics. It was Abdicus Alloy Phase Diagram International Commission. Here, this aluminum titanium molybdenum system, this quite detailed one ternary phases, solidus, liquidus, and some isothermal vertical sections are available. This is from thermodynamic assessments of Vitusevich and Bondar data was carried out. The system in tungsten is quite limited. Data, stable ternary phases cannot be identified, and some isothermal and part of vertical sections only. System with manganese, our critical review of the current state of research and general literature data for equilibrium thermodynamics of alloys. This was published by MSI, Material Science International. This is organizations is Germany. This is international organizations which collect information, critically analyze this information about phase diagram and thermodynamics. More than 30 years, from 1990, and our department took an active part in activity in this direction. And in invariant equilibrium is famous aluminum-rich corner, some isothermal and vertical section, 3 ternary phases. With technetium and rhenium, practically is not famous. Information is missing, only one ternary phase. is known. With iron, this critical review was published in the handbook published by MCI devoted to the system. This available liquid surface child diagram as a thermal vertical sections, 4 ternary phases. System with cobalt liquid child diagrams at vertical sections, 3 ternary phases, especially Heisler phase. System with nickel practical the same. 5 ternary phases, also the Lewis phase and Heisler phase. System with ruthenium, liquid to solid to child diagram September vertical section, 2 ternary phases. A system with rhodium was plotted by us. This is 2 ternary phases take part in equilibrium. This is solidus projection. These are publications in which information about this system is represented. System with palladium, 4 ternary phases, in particular Lewis phase and Heisler phase. Only 2 ternary phases take part in equilibrium with liquid, and tau 2 and tau 4 phases are formed only in solid state. There are 2 publications devoted to the system. System with osmium and iridium is quite poor. Studied in iridium only liquid to surface thermal sections in the iridium rich corner, and osmium is not available information. Only 2 ternary phases in the osmium system and the iridium system. Platinum system as a whole 11 ternary phases. They are not marked, but on this figure they are all represented. This is solid surface projection. Data published in these articles about this system. As a whole, a total of 41 ternary phases were found. Most of them, 11, is the aluminum, titanium, platinum system. This is a number of ternary phases in every location. And at the whole, the fewest ternary phases, one at a time, are formed in the system with chromium, molybdenum, or rhenium. Ternary compounds with a thorium-6 manganese 23 type structure, they also called G phases, are formed by all the 8B group elements. All 9 these elements form these phases and not another elements. The ternary magnesium zinc 2 type Lewis phase is formed on the system with the metals for the nickel subgroup. Nickel, palladium, platinum. This is last subperiod, last subgroup in the ternary, in the periodical system. The largest number of ternary compounds is formed also by nickel, palladium, and platinum. 5, 4, and 11 respectively. And such increase in the number of ternary compounds may be due to close to complete filling or filled as in palladium of the external electronic D sublevel. High joint solubility of aluminum, the metal, and beta titanium is observed. It correlates with the high corresponding solubility in beta titanium as about the binary system. And in the system with chromium, molybdenum, and tungsten, continuous series solution between beta titanium and the corresponding structural component exists. This is a structure of tungsten type, but also in the system with iron, also the structure of some modification of iron and of beta titanium is the same, but many phases, intermediate phases form in the system boundary titanium iron, and that's why the continuous series is not exist between iron and titanium. Solubility of D metal and alpha titanium, the high solubilities, alpha stabilizers of titanium, of molybdenum, about 15%, chromium, manganese, more than 5 atomic percent, and rhenium, cobalt, nickel, osmium, iridium, invisible data. And this fact, quite a high solubility, open the possibility of alloying of the aluminum titanium based alloys by these elements with high solubility in the wide concentration range. In these phases, titanium, aluminum, the highest solubilities, the highest is molybdenum and chromium, the highest. And also in titanium, aluminum, about 9 atomic percent. And two main conclusions. The ternary system formed by aluminum with titanium and the metals of the 6-8 groups differ significantly in the number of ternary phases and the nature of phase equilibrium. And the most detailed information of the physical chemical interaction is available for the aluminum, titanium, chromium, 10 systems, and 5 other systems contain less common components. Tungsten, technetium, uranium, osmium, iridium. Experimental study of this system is significantly complicated for various reasons. Thank you for your attention.
Kornienko. Dear colleagues, who would like to answer the question? Raise your hands and I'll come in. Maybe I'll ask. Thank you very much, Dr. Kornienko, for your interesting and very applicable report, speech. And what system from your different ternary systems that you have studied could you recommend for the metallurgical practice?
Я не дуже розумію слова, що вона каже. Different.
What system could you recommend for metallurgical practice?
For metallurgical practice?
Yes.
Yes, no. No, the main system used in this, the specific systems, they are quite lightweight alloys with aluminum alloys and also quite not expensive alloys and with good properties of chromium, I suppose, with iron, with nickel and cobalt, and something is possible to use a system with molybdenum also.
Thank you very much. And who would like to answer more questions? No one. Thank you very much, dear Dr. Kornienko. You have really very applicable and interesting report. And could you hear us clearly? Kiev, is it okay? The voice is okay? Kiev? Kiev, could you hear us clearly? The sound is good? Kiev?
Yes, yes.
Yes, so the next one is a report from our institute, Tatiana Ayupova, changes in 70-75 alloy structure and properties under the influence of experimental physical factors.
Thank you very much. Good afternoon to everyone. Let me present my report on the topic changes in 70-75 alloy structure and properties under the influence of external physical factors. With the growing demand of the energy-efficient technology, the twin roll casting process is becoming an important alternative to traditional aluminum alloy sheet production.
Colleagues, I am very sorry for interrupting you, but we don't see the presentation. Please.
Okay, we will manage it right now.
The question for tech team, because we see the slides on your screen, but not in our screen.
I see, okay, we will manage it. Перезагрузите презентацию. Они не видят. Они видят вот видео с нашей камеры, но не видят презентацию. Перезагрузить.
Я понял. Іване, що треба зробити?
version.
You should do translation into Zoom.
Yes, we try. We try.
Okay, okay, thank you.
Is it okay? No, 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 it's not okay.
Unfortunately, we don't see any presentation.
One more try. One more attempt.
Yes, currently we see presentation, but not in full screen. So, oh, it's fine. Thank you very much.
Thank you very much for your help.
With the growing demand of energy-efficient technology, the twin roll casting process is becoming an important alternative to the traditional aluminum alloy sheet production. The structure, morphology, distribution and strengthening phases depend on casting, deformation and heat treatment conditions, which determine the final properties. However, there are limited data on twin roll casting of high-strength aluminum, zinc, magnesium, copper alloys, and it impacts on phase composition and mechanical properties after hot rolling and heat treatment. Therefore, this study focuses in examining of this effect. Thank you very much. Alloy 7075, table 1, containing the maximum allowed zinc content, was selected as the base material. Phase transformation parameters were determined by DTA with using the derivatograph device. Twin roll casting was performed on two roll unit, roll diameter of 420 millimeters, barrel length of 600 millimeters, with approximate cooling rate of 1000 degrees per second. The effect of hot deformation on structure and mechanical properties was studied using samples with widths of 40 millimeters and lengths of 200 millimeters, rolled with deform degree from 64 to 88 cents on 4 high rolling mill. Table to look at it. Heat treatment was carried out with three modes based on the solidus temperature of DTA. Table 3. Microstructure was analyzed by the Axiovier optical microscope. The intercept light method was used for measuring intermetallic size, D, shape factor, A, grain boundary fraction, E, and aluminum dendrite parameters. X-ray diffraction was conducted on drone 3 diffractometer in cobalt radiation. Intermetallic volume fraction was determined from phase at matrix 111 K alpha peak intensities. Lattice parameter crystallite size, microstate and dislocation density were also determined. The alloy structure and local chemical composition were investigated with MIRA-3 scanning electron microscope. Tensile tests such as yield strength, ultimate strength, and relative deformation were performed on UTM-100 machine according to standard. DTA figure 1 show that alloy 7075 begin to melt over eutectic phases such as eta, magnesium zinc 2, T, aluminium 2, magnesium 3, zinc 3, and M, aluminium 2, copper, magnesium, and magnesium silicate, and theta, copper, aluminium 2, in the temperature range of 468 to 550 Celsius degrees, melting within 583 for 685 Celsius degrees correspond to substrated solid solution. During solidification, figure 1b, crystallization starts at 630 Celsius degrees with the formation of aluminium and more the solid phase forming to 560 Celsius degrees. The total solidification range is 162 degrees. The liquidus and solidus temperatures obtained from DTA were used for determining optimal casting and heat treatment parameters. At crystallization rate, next please, near 1 degree per second, alloy 7075 forms non-dendritic structure consisting of alpha aluminium solid solution with dissolved zinc, copper, and magnesium, showing a rosette-like morphology and intermetallic compounds, figure 2a. Under twin roll casting conditions, with a cooling rate about 1000 degrees per second, non-dendritic nearly globular aluminium structure forms. Figure 2b. Within the aluminium grain, the fine intermetallics are distributed, while in the intergranular regions contains non-equilibrium eutectic phases such as eta, T, M, and iron-containing phase, specifically aluminium 15, iron magnesium 3, iron manganese 3, silicon 2. Look please at the figure 3. The solid solution contains up to 11 weight % of alloying elements. During the twin roll casting hot rolling process, with a deformation degree of 64 to 88%, aluminium dendrites aligned along the rolling direction, look at the figures 2C to E. At green boundaries, the T phase prevails over the M phase, figure 4. And the intermetallic compounds, aluminium 7, copper 2, iron, dissolving silicon, zinc, and manganese is also present. With deformation, the strengthening phase becomes finer, increasing the aluminium supersaturation to about 13% at deformed degree of 88%, and isotropic structure forms figure 2F. Dendritic cells elongate and volume fracture of size and metallic decrease due to fragmentation and partial dissolution during thermomechanical processes. Look at the table 4, please. The structure formed through the second twin roll casting, hot rolling. Next, please. No, that's all. With degree of deformation 72%, and heat treatment shows aluminium and intermetallics alliance along a rolling direction, figure 5, and quantitative structural parameters vary notably with the heat treatment regime. Look at table 5. Under heat treatment 1, annealing dendritic cells become smaller and less elongated, while the amount of grain boundary intermetallics increases. Spheroidization makes these particles finer and more rounded. Heat treatment 2, quenching and natural aging, leads to larger dendritic cells compared to heat treatment 1, but decreases the size and fraction of intermetallics at aluminium grain boundaries. Mainly iron-containing phases remained undissolved during heat treatment 2 and heat treatment 3, and form change under the deformation. Look at the figure 6. Rounded interfaces with aluminium and low shape spectra confirm spheroidization of secondary phases. Figure 5B to D. Artificial aging, heat treatment 3, increases the number of eutectic colonies and the size of intermetallics, which also become more round. Throughout the technological processes, next please. Throughout the technological processes, the phase composition of 7075 alloy remains essentially unchanged. However, the volume fraction and relative proportion of intermetallics vary at each stage. This is confirmed by changes in intensity of distribution of diffraction peaks, figure 7 and figure 8. The diffraction peak intensities of strengthening phases show a consistent trend, unlike of those of ion-containing phases, figure 7. These differences result from copper and zinc diffusing from ion-rich phases to the aluminum matrix. Each processing stage changes element and phase distribution, affecting on alloy microstructure, substructure, and mechanical properties. Table 6. Table 6. In the S-cast twin roll strip, the lattice microstrip, table 7, table 6, and concentration of alloy elements in matrix, magnesium, copper, and zinc are lowest among all processing stage, near the 11%. During hot deformation, several processes occur simultaneously: dissolution of intermetallics, enrichment of the aluminum matrix with alloying elements up to 13%. Figure 4. Don't touch it. Figure 4. And formation of more dispersed structure due to solid solution decomposition and phase refinement. The lattice parameter increases because of higher magnesium solubility in aluminum, along with rising microstrains and dislocation density, which promote dispersion hardening. The mass fraction of secondary phases also increases, figure 8. After heat treatment 2, the intermetallics content decrease, especially theta phase, M phase. The aluminum matrix remained highly supersaturated, 12.8%, figure 6, and lattice parameter decreases as copper and zinc dissolution in aluminum matrix. Following heat treatment 3, the structure coarsening sliding and decomposition intensifies. The alloying element content in aluminum drops to 11.8%, and intermetallic fraction increases up to 2-3 times. Microstrain rises while dislocation density and crystalline size remain comparable to heat treatment 2 values. The structural evolution of 7075 alloy during twin roll casting, hot rolling heat treatment has strong impact on its mechanical properties. That's all. What is the signal? As the cast strip, the S cast strip shows low strength, ultimate strength is near 250 megapascals, and very limited plasticity, less than 0.3%. After hot rolling, with a deformation degree from 72 to 88%, strength increase about 400 megapascals, and plasticity up to 10% due to partial dissolution of intermetallics in aluminum. They both facilitate dislocation movement and enhance solid solution strengthening, dislocation density, and microstrain. Heat treatment further improves properties by decomposition of supersaturated solid solution and forming fine strengthening phases. Figure 10. Maximum plasticity near 20% is achieved after 8-9 folds by quenching and natural aging, with ultimate strength of 440 megapascals and highest strength of 568 megapascals is obtained after fold rolling, quenching, and antifocal aging, and plasticity is 7 to 2%. Thank you very much for attention. That's all.
Thank you very much, Dr. Ayupova. Dear colleagues, who would like to answer the question? Yes.
Please tell me, why does the degree of deformation 3 to 4 fold or 8 to 9 fold compression in combination with quenching and aging modes lead to different combination of strengths and ductility?
Through these processes, there are some differences in structure formation. For example, the whole deformation is thermomechanical treatment of this alloy. And there are two processes which go in these conditions, such as dissolution of intermetallics and simultaneously decomposition of alpha aluminium supersaturated solid solution. And there are different stages of this decomposition. For example, GP zones or metastable phases or some stable phases, and these phases can provide in some different properties.
Thank you very much. And who would like to answer more questions, dear colleagues? Maybe I'll ask, have you made any comparison of twin roll casting with traditional production?
Twin roll casting is energy efficient process. Traditional production contains the first stage, it's casting of aluminum alloys. Next stage, it's mechanical treatments. And next stage is rolling stage. Yes, and we have one stage treatment and casting and rolling in one time.
Thank you very much. Much more advanced. Yeah. Thank you very much, Dr. Ayupova, for your great and very interesting report. And this is the last report before coffee break. Dear colleagues, I invite to the coffee break everyone, and would like to know that we are waiting for everyone at 11:20, and we will start the symposium flash poster session. 1, 2, 3. Dear colleagues, are you ready to start? Kyiv, are you ready to start Flash poster session?
Yes, we are ready.
So maybe we can start, yes? Am I right?
Yes.
So we start our Symposium Flash poster session, part 2. And the first one, Evgeny Titkov, Structure and Properties of Experimental Low-Cost Titanium Alloys. Evgeny Titkov, are you online? Evgeny Titkov. Evgeny Titkov, are you online? Evgeny Titkov. Okay, the next one, Yuri Semirenko. Yuri Semirenko, are you online?
Yes, I am online.
Okay, so low temperature mechanical properties and microstructure of non-equiatomic medium entropy alloys in coarse grained and nanostructured states. Am I right? Your poster?
Please share my presentation.
Yes, one moment. Technical.
Where are people?
Next slide, please. It's not my presentation. Okay. Good day, everyone. My name is Yuri Semerenko. Today, I'd like to present our research. I started on the top of the slide. Let me begin by outlining the scope of our study. At two temperatures at 290 kelvins, this temperature have to refer to as room temperature, and at temperature 77 kelvins, this temperature have to refer it as cryogenic temperature. The phase composition and mechanical properties of two non-equiatomic medium entropy alloys, Terrum 40, manganese 40, cobalt 10, chromium 10, and Terrum 50, manganese 30, cobalt 10, chromium 10, were investigated in both coarse-grained, have to refer to as CG, and nanostructured have to refer to as NC states. In these alloys, in both structural states, the additional deformation mechanism are activated under load. Thinning in the first case, this alloy have to refer to as TWIP alloy, and phase transformation. In the second case, this alloy have to refer to as TRIP alloy. The samples of both alloys reproduced via arc melting followed by post-processing through annealing and deformation. Construction was achieved through severe plastic deformation using high-pressure torsion. At two temperatures, at room temperature, this regime of deformation have to refer to as RT HPT, and at cryogenic temperature, this regime of deformation have to refer to as cryo HPT. As a result of HPT torsion, the average grain size was decreased from approximately 40 micrometers to about 60 nanometers. Phase composition was analyzed using X-ray diffraction on a Brücke D8 discovered diffractometer. Microhardness measurements were performed with both a PIR microindentation tester and PMT microhardness tester, with indentation taken along co-radial direction from the center to the edge of the disk. Mechanical properties were assessed using an MRK deformation testing machine at room temperature and at cryogenic temperature, with liquid nitrogen as a cooling medium. By acoustic properties, they studied the mechanical resonance spectroscopy at temperature from cryogenic to room temperature. Now, let's move on to the key findings of our research. In a nanostructure state, both alloy undergo a almost complete phase transformation from the face-centered cubic to the hexagonal closed packet structure, unlike in the coarser-grained state. The extent of this transformation shows minimal dependence on temperature on the number of high-pressure turns. The transition from the coarser-grained to the nanostructure state leads to an increase in microhardness. This one. In the coarser-grained state, both alloys exhibit thermally activated plastic deformation across the all temperature range. In contrast, in the nanostructure, TWIP alloy retains plasticity under active compressive loading at both temperatures, while the nanostructure TRIP alloy shows no microscopic plasticity under the same conditions. Tensile deformation up to 50% at 30 kelvins in the coarser-grained states results in a significant reduction in the absolute values of Young modulus across the entire temperature range. In the right part of slide, we present the transformation scheme of structural states of the studied alloys, along with an observed change in phase composition and microhardness. Similar trends are also observed in acoustic and mechanical property studies. Thank you for your attention.
Are you online? Сергій Наконечний. Сергій Наконечний. Are you online? Сергій Наконечний.
He said that he will be available, but later. Maybe then we will come back to his presentation.
Okay, the next one, Roman Sergійко. Are you online? Roman Sergійko. Roman Sergійko.
He is here.
Okay.
Here at our Kyiv offline locations. Please wait a minute.
Okay. Structure and properties of heat-resistant ferrum, nickel, chromium, cuprum, aluminium, high entropy alloys.
Can you hear me?
Yes, we can.
Okay. Hello, everyone. Good morning. Today I will present results of study on ferrum, nickel, chrome, copper, aluminium, high entropy alloys, which were produced using inexpensive and widely available materials. Normally, highly entropy materials consist of quite expensive materials such as cobalt and tungsten, which are making them economically impractical because of expensiveness of the materials. These alloys we were using are known for unique combinations of strength, thermal stability, and corrosion resistance, which come from the significant lattice distortion on their crystal structure. The aim of the study was to produce high entropy alloys in air using induction melting, using commonly available low-cost materials such as stainless steel, cast iron, aluminium, copper, and nickel. The aim of the study was to produce such alloy and investigate their phase structure, microstructure, and oxidation resistance. These materials, this alloy, as I said before, was produced by induction melting on open air. We used copper aluminium master alloy, which contained 33% of aluminum, and semi-finished nickel with 99.5% of purity, low carbon ferrochromium, stainless steel, and high alloy cast iron. Master alloy was produced in graphite crucible. The phase composition of the alloy was it has in it several phases. BCC ordered solid solution, FCC ordered solid solution, complex carbides, and and complex carbides. The carbides performed during the presence carbon in cast iron, which was part of the alloys. Microstructure is heterogeneous. It consists of dendrites, interdendritic regions, carbides, and cooper-rich regions. Oxidation resistance was tested at 900 and 1000 degrees of Celsius in synthetic air with gas flow of 100 millimeters per minute. The alloy demonstrated higher oxidation resistance than conventional heat-resistant steels at temperatures, as we discussed, as I mentioned, temperatures were 900 and 1000 degrees. In the result, we successfully produced the alloy, which was consisted of low-cost materials. The alloy consisted mainly BCC and FCC structure, which is aligned with the structure of high-entropy alloys. The microstructure consists of dendrites, interdendritic spaces, carbides, and copper-rich areas. Alloy we produce demonstrate high oxidation resistance, and compositions with higher chromium and aluminum contents show the best performance up to 1000 degrees. That's it. Thank you.
Thank you very much. The next one, Vasily Natsyk. Vasily Natsyk, are you online?
Good day again. My name is Yuri Semirenko. If the conference organizers have no objections, I'll present instead of Professor Natsyk.
Of course. The dislocation structure of the high entropy alloy, theory and experiment.
Today I'd like to present a work titled as shown on the top of the slide. Let's begin by outlining the scope of a study. We comprehensively investigated the low temperature dynamics and kinetics of dislocation motion in the high entropy alloy aluminum 0.5, cobalt, chromium, cuprum, ferrum, nickel across a broad range of elastic deformation. This was done using two experimental approaches, mechanical resonance spectroscopy and active plastic deformation. In parallel, we performed a theoretical analysis of the low temperature processes involved in plastic deformation and acoustic relaxation in this alloy. Our work proposed a dislocation model that effectively explains the experimental observations of low temperature plastic deformation and acoustic relaxation. Additionally, a detailed study of dislocation structure at room temperature was conducted using X-ray structural analysis, leading to a numerical estimate of the dislocation density. Now, let's move to the key findings of our research. For a proposed dislocation model, we derived quantitative estimates of crucial dislocation characteristics and their interactions with barriers. For example, the average distance between local obstacles within the slip plane, this one. The pile stress for dislocation and in an easy slip system, this one. The predicted speed of sound it matches well with experimental data reported in reference 3. The estimated energy per unit length of a dislocation and a linear mass density, this one, align with the modern dislocation theory. Notably, the dislocation density measured through X-ray analysis correlated with our model's estimates for density of dislocation interacting effectively with elastic vibrations. Our comprehensive experimental and theoretical analysis are grounded in contemporary dislocation theory allowed us to identify the primary types of dislocation defects present in the LS lattice structure, the nature of barriers obstructing dislocation line motion, mechanism of thermally activated motion for segments of dislocation strings overcoming these barriers, especially under moderate and deep cooling, and to provide quantitative estimates of dislocation characteristics and their barrier interactions. In the right part of the slide, we present the estimators of the dislocation structure parameters that we obtained through the study of mechanical and acoustic properties, as well as X-ray structural analysis. The arrows highlight the observed correlation between the estimates obtained by different methods and the data reported in the literature. Thank you. Thank you for your attention.
Thank you very much. And the next one, Dmytro Lukyanchuk. Are you here, Dmytro Lukyanchuk?
Yes, I'm here.
Evolution of the phase composition of the high entropy alloy, chromium-3, ferrum, cobalt, nickel, aluminium, copper after oxidation.
Yes, agree. Good morning, dear colleagues. I'm pleased to present our research, evolution of the phase composition of the high entropy alloys after oxidation at 1000 degrees Celsius. Yes, thank you. It is not my poster. Can you share another?
It's not Dmitry Lukyanchuk.
Yeah.
Some technical problems, just wait a little bit.
Okay. Yes. Thank you. This work was carried out in collaboration with the colleagues from the Francevich Institute for Problems of Material Science, Igor Sikorsky Kyiv Polytechnic Institute, and the Patton Electric Building Institute. High entropy alloys have attracted great attention in recent years because of their outstanding mechanical properties and thermal stability. However, one of the critical issues for practical applications is their oxidation resistance at high temperatures. Our goal was to study how the phase composition of the chromium-3 iron, cobalt, nickel, aluminum, copper alloy evolves during high temperature oxidation. The alloy was studied in the S-cast condition and after oxidation at 1000 degrees Celsius. 4 different holding times, 10, 25, and 50 hours. We use X-ray diffraction to determine phase composition and the scanning electron microscopy with the energy dispersive spectroscopy, EDS, to investigate the microstructure and local chemical composition. In the S-cast state, the alloy contains 2 main phases with body-centered cubic lattice and face-centered cubic lattice. The oxidation resistance of the alloy is explained by the formation of an aluminum oxide layer on the alloy surface. With the longer exposure, especially after 25 and 50 hours, the fractions of sigma phase increased significantly, reaching about 50%. At the same time, aluminum oxide remained one of the main oxidation products. In addition, in the near surface region, a significant amount of sigma phase was observed also. To clarify the phase composition of the alloy matrix, additional X-ray diffraction studies were carried out after the complete removal of the oxide layer. According to this data, the matrix still contains BCC, B2, FCC, and sigma phases with a sigma present in an amount of about 10%. The microstructure images show the gradual transformation of the alloy matrix, while the EDS analysis confirms the distribution of elements between different phases. EDS analysis of the alloy also revealed the presence of two different FCC phases. One of them is strongly enriched in copper, containing about 80%. To summarize, the high temperature oxidation resistance of this alloy is mainly due to the protective aluminum oxide scale and the formation of sigma phase near the surface. The formation of a significant amount of sigma phase can increase the wear resistance of the alloy under conditions of intense wear. Additional X-ray diffraction confirmed that even after oxide removal, the matrix retains BCC, FCC, and sigma phases with sigma around 10%, which is promising in terms of increasing the heat resistance of the alloy. In general, this study improves our understanding of the oxidation behavior of high entropy alloys and provides useful insight for their potential high temperature applications. Thank you for your attention.
Very much, Dmitry Lukenchuk. The next one is Mikhailo Turchanin. Dr. Turchanin, are you online?
I am sorry, my name is Pavlo Agrawal. Professor Turchanin is busy, so I can present our report, if you please.
Yes, okay, of course. High entropy FCC alloys in the chromium, ferrum, cobaltum, nickelum, and copper, ferrum, cobaltum, nickelum systems, CALFAT modeling of the phase stability, please.
Please, yes, more bigger if you can. Okay, hello to everybody. Experimental theoretical investigations confirm the possibility of producing high entropy alloys and close to them compositions with various structures and properties in the copper, chromium, iron, cobalt, nickel system and its quaternary subsystems. This includes single phase and dual phase high entropy FCC alloys. The last forms dispersion stress-sensitive materials and allows alloys with frozen emulsion type morphologies. Phase diagram analysis using the CALFAT method is a powerful tool which can be used for this for development of these materials. This approach involves parameterizing the Gibbs energy for liquid and solid phases and developing thermodynamic databases. In our work, a thermodynamic database was developed for the liquid FCC, BCC phases of the copper, chromium, iron, cobalt, nickel system. The database incorporates the model parameters of thermodynamic mixing functions for 10 binary and 7 ternary systems. Excess Gibbs energy for the liquid FCC and BCC phases are described by the equation, which consists of the two parts. First describes contribution of binary interaction, second describes contribution of ternary interaction. The 5-component copper, chromium, iron, cobalt, nickel system consists of 5 quaternary subsystems, but in this work we focus on 2 of these quaternary subsystems, copper, iron, cobalt, nickel, and chromium, copper, iron, nickel systems. For the first of them, copper, iron, cobalt, nickel system, polythermal sections of phase diagram were calculated. Please see the first figure at the central column of poster. This gentle concentration curves of the liquid curves indicate the tendency of liquid alloys to separation in the supercooled state. Along the sections with iron and cobalt beam sections, a continuous FCC solution is formed, which undergoes binodal decomposition with decreasing temperature. Along these sections, the binodal of the BCC phase exhibits a very general maximum near the equiatomic composition. The binodal decomposition temperature for the FCC phase of equiatomic composition is 1409 Kelvin. The results for the chromium iron cobalt nickel system shown in the figure at the right column of poster. The simultaneous formation of extended regions of homogeneity of BCC and FCC solution is characteristic, as you can see. Along the cobalt beam, the FCC phase crystallizes from the melt in the form of a continuous solid solution, and along iron and nickel beam sections in the form of a limited but extended solid solution, which becomes continuous with decreasing temperature. The formation of the BCC phase occurs at high concentrations of chromium and iron in alloys. The equiatomic composition of this system is within the region of homogeneity of the FCC phase. These results of calculations on both systems are supported by the experimental data available from the literature. The isotherms of two-phase FCC region in the copper, iron, cobalt, nickel system at two temperatures, and isotherm of the FCC BCC region for the chromium, iron, cobalt, nickel system at 1300 kelvins are shown in the bottom figure at the central column of poster. So we make some conclusions. First, the database for the liquid FCC and BCC phases of the quinary copper, chromium, iron, cobalt, nickel system was created, taking into account the parameters of the thermodynamic mixing functions for the boundary, binary, and ternary systems. Predicted in the framework of Kalfat method, high temperature transformations in both quaternary systems align well with the reported experimental data. Second, in the copper, iron, cobalt, nickel system, below the solidus temperatures, there is an extended region of existence for the FCC phase. The two-phase region with FCC1 and FCC2 phases expands with decreasing temperature and covers most of the concentration tetrahedron. Third, in the chromium, iron, cobalt, nickel system, single-phase FCC field covers most of the composition space, which makes it promising for obtaining single-phase high-entropy alloy, but makes it impossible to obtain dispersion-strengthened alloys. Thank you very much for your attention.
Thank you very much, Dr. Agraval. The next one, Anna Rusakova. Are you
Yes,
online?
I'm
Cool. The micromechanical properties of copper, chromium, ferrum, nickel, vanadium X, where the X is equal 0 to 2, high entropy alloys.
okay. Well, in this study, for the first time, we investigated the micromechanical properties of high entropy counteralloy doped with vanadium in the temperature range from 77 Kelvin up to the room temperature. Depending on the phase composition of the alloys, which changes with vanadium content increasing from 0 to 2, the studied alloys can be divided into three main groups. The alloys from the first group consist mainly of a single FCC phase without or with a low content of the tetragonal sigma phase. The alloys of the third group are also one phase and consist mainly of a single tetragonal sigma phase with a low content of FCC phase. And the alloys of the second group are two-phase alloys with comparable amounts of both FCC and tetragonal phases. For the alloys from these three groups, we obtained the temperature dependencies of microhardness, which are shown in the figure 1. You can see that with a temperature decrease from room temperature to 77 Kelvin, the microhardness of the alloy from the first group monotonically increases by about 45%. This indicates the thermally activated character of plastic deformation of the material under the indenter. It is known that the proportion of sigma phase precipitation in this alloy does not exceed 2%. we show that its microhardness is about the corresponding value of the counteralloy. The alloys of the third group are also almost single phase with a tetragonal lattice, and the whole volume of the alloys is mainly intermetallic sigma phase. The value of microhardness increases monotonically by about 32% with temperature decrease from room temperature to 77 Kelvin. A completely different behavior of microhardness was observed in the case of the two-phase alloys from the second group. The hard precipitation of sigma phase act as asomal barriers to the motion of dislocations, and as a result, in a fairly wide temperature range from 150 up to the room temperature, the average microhardness remains practically unchanged. And also, we analyzed the effect of vanadium content on the microhardness. At all studied temperatures, the microhardness depended weakly on the vanadium content at small and large values of X. At the same time, we revealed a sharp increase in microhardness starting from X approximately 0.5, which is associated with the formation of a large amount of hard intermetallic sigma phase with a tetragonal lattice. Thank you for your attention.
Thank you very much, Anna Rusakova. The next one, Sergei Tesla. Are you here? Sergei Tesla.
Sergei Tesla is in Kiev offline locations. 1 minute, please.
Okay. Mechanical alloyed tungsten ferrum cobaltum nickel high entropy alloy.
Okay. Good evening, dear colleagues. I will present you our research in mechanical alloyed high entropy alloy based on the tungsten, iron, cobalt, and nickel. Yeah. Unfortunately, we have some mistake. That is not high entropy alloy, that is medium entropy alloy. But so the focus of this study is development of tungsten, iron, cobalt, nickel high entropy alloys by mechanical alloying. So we know the high entropy materials is really used in different applications like aerospace, medicine, in the high temperature materials. This composition is for some military applications because high density, and the main idea of the mechanical alloying of that composite, it was in situ reaction between the carbon atoms which we add from the petrol or for H-heptane with the tungsten atoms and form the tungsten carbide after mechanical alloying. So we have the in situ reaction between metals and non-metals and have some precipitation particles into the high entropy body. So after mechanical alloying of initial powder was formed different phase composition. After only 10 hours, we prepared two solid solutions based on the BCC and the FCC structures. But after 20 hours of mechanical alloying, we will see on the XRD pattern the reflex of the tungsten carbide. So look on the pictures on the scanning electron microscopy. The evolution of the microstructure, it was shown that after 10 hours, we will see three phases, but not the correct. The light one, that is tungsten carbide, the small particles into the BCC solid solution based on the tungsten and iron. And we can see the big one gray phases, that is the FCC solid solution based on the cobalt and the nickel. So after the 20 hours of alloying, we have the homogenization of the structures and prepare practically fully BCC solid solution with the particles of the tungsten carbide. So the thermal stability of the high entropy alloys is pretty important for the high temperature applications. So we investigate that composition by different scanning calorimetry. So we can see two transformations in this high entropy alloy. The first one, that is the polymorphism transformation between BCC solid solution into the FCC solid solution, high temperature stability, quite different. But if we increase the temperature, we can see small exothermic peak, which can be associated with the stress relief, but also with the transformation between FCC to BCC, because we have a quite big amount of the tungsten. Tungsten at high temperature can stabilize the BCC high temperature structure. So the melting point of this high entropy alloy is near 1215. The small exothermic peak after melting, that is oxidation degradation substructure, because yes, we investigate in the high purity argon, but argon also have some waters and other gases which can give some effects on the DSK curves. So in this study, the tungsten carbide reinforced high entropy composite was successfully synthesized by mechanical alloying. The composite high entropy materials tungsten carbide consist of BCC major solid solution with the minor FCC solid solutions, and also tungsten carbide particles. So this research was supported by National Research Foundation of Ukraine. Thank you. Thank you.
Thank you very much, Sergei Tesla. The next one, Ksenia Kutnik. Silver alloying for creation of biodegradable magnesium alloy.
Good morning, everyone. This work is performed at National Science Center, Kharkov Institute of Physics and Technology, in collaboration with Sytenko Institute of Spine and Joint Pathology. The purpose of this investigation is to create a new biodegradable magnesium alloys with improved mechanical properties and a slowed dissolution rate that are completely biocompatible, do not cause inflammatory reaction, and have no negative effects on the human body. The modification of WV43 magnesium alloy hardened by rare earth element, that is yttrium, neodymium, zirconium, and lanthanum, was performed at National Science Center, Kharkov Institute of Physics and Technology, in order to reduce the dissolution rate and to improve the biocompatibility of medical implants. As a result, a new magnesium rare earth element alloy doped with silver was created. In collaboration with Sytenko Institute of Spine and Joint Pathology, were performed comparative experiments in vivo on 48 rats by implantation of samples of biodegradable magnesium alloys in the intervertebral discs and subcutaneously. The first figure shows the implantation operation, and on figure A, you can see implantation of the samples in the form of peak in the intervertebral disc at the base of the tail. And in figure B, you can see implantation of the samples in the form of disc subcutaneously in the region of withers. The second figure shows that 2 months after implantation, the disc-shaped rare earth alloy samples dissolve significantly faster than the magnesium alloy disc-shaped samples with silver. that is photo A, B, C, and D. If we look at photo E, F, G, and H, we will see that the peak-shaped samples of both alloys dissolve significantly more slowly. However, after 5 months, the magnesium alloy with silver is more resistant to corrosion. So it is established that the average dissolution rate of magnesium alloy with silver is in the body is 1.9 times lower than the industrial magnesium alloy. The histology showed that no inflammatory reaction was found around WE43 alloy with silver implants, and the formation of cartilage tissue was more active compared to industrial alloy at all stages of the study. This indicates a better biocompatibility of the magnesium alloy with silver. In conclusion, I want to say that the result of the in vivo experiments indicates that modified biodegradable magnesium alloy WE43 with silver is a promising material for use in medicine. Thank you for your attention.
Thank you very much, Ksenia Kutny. The next one, Igor Maximchuk. Igor Maximchuk, are you here?
Igor Maximchuk is here in Kyiv offline locations. So
thank you very much. Peculiarities of the aging kinetics and formation of mechanical properties in deforming alloys of the aluminum magnesium silicon system.
Good morning, dear colleagues, and peaceful sky for all. My report indicates the peculiarity of aging kinetic and formation of mechanical properties in the formed alloy of aluminum chromium system. The alloy of this system is widely used as deformed, hot deformed alloy in various branches of industries. To obtain the optimal combination, plasticity, and strength, the alloy subjected the hot treatment. As a rule, after the deformation, this alloy for a long time stored at room temperatures and subjected to the natural aging. Now it was in the process of natural aging, the formation of cluster embedded in the aluminum matrix is very intensive process. These clusters contain the chromium and magnesium atoms, and ratio depends, and ratio concentration magnesium to chromium depend on chemical composition of the alloy. The kinetic of aging we investigate by using the Wicker-Hagmet method and the method of mathematical planning of experiments. The dependence of Wicker-Hagmet in the temperature range of 140 and up to 200 degrees was investigated, and use this data, the hardness map, equal hardness map in the temperature time according annealing coordinates was present in the figure 1. Using the data, we estimate the energy of heat treatment process and calculate the effective energy or apparent energy activation of this process. It can be seen from feed lamp. We can to temperature range 140 to 170 and 170 to 200 degrees. In this interval, in low temperature interval, the activation energy is low and correspond to the diffusion or migration chromium atoms along the dislocation core. Another more high temperature intervals, the energy activation correspond to the volume diffusion of the chromium atoms in volume. We verify effectiveness of heat treatment regime. The samples were mechanically tested after added at temperature 150, 170, 190 degrees. The annealing time corresponds to the time required to reach maximum values of hardness. The table 1 presents the result, collected the result of the tensile test and hardness. As we can see, the hardness and the elongation correspond to the proposed our heat treatment process, confirm our heat treatment process. Summarize my speech, I conclude the role of clusters in process of heat treatments. In low temperature intervals, its clustering process have a positive role because the migration of magnesium atom along dislocation to clusters and form a subsequent form to the nuclear for formation of new fast magnesium chromium. In the high temperature range, the role of clusters more negative because the one of the traditional mechanism of the egging is the formation of the Guinea-Preston zones and subsequent formation of nuclei in these zones and the formation of new phase. Because for formation of these zones necessary to dissolve the clusters, chromium magnesium clusters, and diffusion these atoms to Guinea-Preston zones. Thank you for attention.
Thank you very much, Igor Maximchuk. The next one, Sergei Tesla again, biodegradable ZK61 magnesium boron to magnesium based composite.
Извините. Дело в том, что я вас совсем не слышу. Но когда идет трансляция через...
So, hello again, and for everyone. I will present the result of our work about the biodegradable magnesium alloys ZK61 with additional of magnesium diboride. So the magnesium and magnesium alloys, that is widely used materials for biodegradable applications in the orthopedics. The specific of these materials is the elastic modulus, which are near the natural bone compared to the titanium and titanium alloys, stainless steel, cobalt materials, and others. But the controlling of the degradation rate of the magnesium-based materials, the antimicrobial and antibacterial action around the implants is so important. It's a challenge for the researchers. but our good friends and colleagues in the Romania investigate the properties of the pure magnesium diboride and show that the magnesium in the magnesium diboride in the pure form show extremely high antimicrobial and antibacterial properties. But the ceramic-based materials in general, it's quite difficult to make some parts with these materials, especially screws and the orthopedic construction. So we want to combine the properties of the magnesium biodegradation and the high antimicrobial properties of the magnesium diboride. So to the commercial available alloys, we add 8 volume% of the magnesium diboride and consolidate by the spark plasma sintering at 500 Celsius degrees under pressure, especially in the argon flow. So between the magnesium matrix and the magnesium diboride particles, we wasn't found any reaction. Yeah, boron is quite good reduction agent, but the magnesium oxide, like calcium oxide and zirconium oxide, are extremely stability at low and high temperature, and so we haven't the reaction. We indicate the antimicrobial properties with 2 groups of the bacteria, that is pneumonia bacteria group, that is laboratory samples. So the additional of the magnesium diboride in the magnesium alloys increase the antimicrobial properties practically 10 times and clear the clean the environment around the part of the implant. So in this study, the magnesium alloys with additional of the 8% of magnesium diboride was prepared. It's shown that during spark plasma sintering, the composition is no diffusion of boron atoms into the magnesium lattice. It has been shown that due to the action of magnesium diboride in the environment enriched with the pneumonia bacteria, their population decreases almost 3-fold and 10-fold in different groups compared to the pure magnesium alloys. Thank you for your attention.
Thank you very much, Sergei Tesler. The next one, Svetoslav Gniloskurenko.
Okay. Yes, I'm here.
Properties of aluminium foam, please.
Thank you for presenting me. I am from Physical Technological Institute of Metals and Alloys, but my research team is mainly from Francevic Institute for Problems of Material Science. And here we will show you our results on the study of electrical properties of aluminium foam. The metallic foams are known for their unique properties because of very high porous state, up to 98%. It may be sometimes of porosity. So in this case, such materials leads to low transfer properties like heat transfer or electric transfer, and we were concentrated of the study of resistivity of aluminium foams for further application as electromagnetic shielding material. So we selected 2 aluminium-based alloys. First one is shown in the table left upper corner of the slide, relatively ductile aluminium magnesium silicon system alloys and aluminium zinc magnesium alloys. And we produced metallic foams from their melts by adding calcium carbonate forming agent. It's known like alpha-rasorot in the world, but we use calcium carbonate and powdered by CO2 particles to prevent agglomeration of this forming agent. And then we formed specimens like shown on some photos. Right side is in foamy state and left side is dense alloys. And then we measured electrical properties by our newly applied instrument, and we measured resistivity by 2 points probe tester. And on the right side, we show you some of our results. We realized the known tendency of porous metals when with increasing porosity, resistivity also increases. We find some difference between these two alloys, mainly because of their difference in microstructure. More brittle alloys shown higher resistivity. And the interesting point is that we compared our results with known in literature, mainly for aluminum, pure aluminum. This results is summarized in the table shown on the right side of our slide. And we can see that in general, metallic forms realized electrical resistivity 2 times higher than dense material, for example, pure aluminum or the same matrix alloys without forming, so twice lower electrical current conductivity. And comparatively for these 2 aluminum-based alloys, we can conclude, we find that more brittle aluminum high-strength alloys shown higher resistivity. Let's say that better properties to be used as a shield from electromagnetic waves, etc. So it's briefly about our first study. Thank you, and I'm ready to pass to our next talk.
Thank you very much. And the next one, mechanical performance of aluminum foam fabricated by melt procedure with the addition of boron carbide.
Yes, thank you. I'm ready to continue. Next slide, but please turn it. I can see it's in vertical direction. Okay.
I'm sorry.
Okay. I can share you in the right direction, but
technical problem, as I see.
Oh, okay. Okay, so the next our part of study concerns the mechanical performance of aluminum foam fabricated by melt processing with addition of boron carbide. In this case, we also concerns aluminum-based forms. We selected only one alloy, high strength and quite brittle aluminum zinc magnesium system. We again formed it by calcium carbonate. Similar procedure, actually it's patented by our research team. Similar like in the previous my talk. And in this case, we added the stabilizing agent powder, and it was a mixture of boron carbide and titanium boride with different content in relation with calcium carbonate from 20 to 70% in relation of calcium carbonate quantity. It was necessary step because we know that it's quite difficult to stabilize liquid metal form because due to gravitation, the liquid melt goes down, and some damage of pores occurs. So, but we propose this new powder to stabilize the foam. We studied some microstructure, relative density, porosity content, and then we undergo mechanical testing of foam sample under uniaxial quasi-static loading, and you can see the picture of our sample cut from the formed blocks. And I pass your attention to our results section that we right side not so clear our figures. I can describe you by words. We just analyzed, okay, thank you. We analyzed the stress strain curves on the first plot right side, and we could see that at the content of boron carbide tiboride powder about 50%, we got the higher plateau stress blue lines comparatively to 30% of this powder contents green line. Also, it turns to their another properties, energy absorption, right side plot, and we could get higher energy absorption, that it's important for forms application. In case of 50% of this mixture added. And the lower plot shows us diagram energy absorption dependence on the quantity of added powder mixture of stabilizing agent, and we realize clearly that about 50% of this added powder patented in our methods leads to higher energy absorption of such forms, metallic forms. And so briefly, I may give you a conclusion that we find the optimal contents of proposed stabilizing agent, boron carbide and tiboride. And also we find that it should be the size of similar order with calcium carbonate. In this case, using theoretical study, we can claim that the stabilizing effect of these additives is the highest. It's important to know in developing the technology for produce stable forms of aluminum-based alloys. Thank you for your kind attention.
Thank you very much, Святослав Гнилосkurenko. The next one, Игорь Воскобойник. Игорь Воскобойник, are you here? Игорь Воскобойник.
Oh,
are you here?
I'm here. My name.
Yes.
Make
Your
this.
report is high-strength aluminum foundry alloys of the triple system aluminum silicon manganese with increased performance characteristics.
Yeah. Good afternoon, dear colleagues. My name is Mykola Yefimov. I make these reports. Dear colleagues, let me present to you the report high-strength aluminum foundry alloys of the triple system aluminum silicon magnesium with increased performance characteristic. The analysis of both our experiments and published data has demonstrated the promise of developing eutectic aluminum and magnesium to silicon foundry alloys based on the ternary aluminum magnesium silicon system. Our novel approach explored the quasi-binary eutectic type section of the aluminum magnesium silicon phase diagram, in which primary aluminum solid solution coexists with intermetallic phase magnesium to silicon. The phase equilibrium topology of this system permits a multifold increase in magnesium content in the aluminum matrix compared with the conventional foundry alloys, elimination of free silicon, and thus enables more effective supplementary alloying with zinc, copper, and other transitional metal. The purpose of investigation was to determine ways to improve the performance characteristic of foundry aluminum, magnesium, silicon alloys. To implement solid solution strengthening in aluminum silicon magnesium system, the addition of manganese has been proposed. This strengthening arises from the dissolution of manganese atom in the aluminum matrix, which increase interatomic bonding forces in the crystal lattice of the solid solution at both room and elevated temperature. To achieve dispersion strengthening in the eutectic composite, we involved the scandium effect. Scandium promotes formation of finely dispersed aluminium-3 scandium precipitates whose lattice matches that of aluminum almost perfectly, thereby improving the mechanical strength, corrosion resistance, and other properties of the alloys. The aluminum-3 scandium phase does not have metastable modification and maintains the coherence of the aluminum matrix over a wide temperature range. For complexly alloyed aluminum, magnesium, silicon foundry alloys containing scandium and zirconium, the heat treatment regime providing dispersion strengthening by aluminum-3 scandium precipitates was determined. Specifically, samples with and without manganese were aged at 200, 300, and 400 degrees of Celsius during 20 hours. Hardness increase in all aging temperature, but the peak strengthening occurs at 300 degrees of Celsius. Since higher aging temperature enable components to operate at a higher service temperature, it is noted that the hardness of the scandium, zirconium, manganese alloyed eutectic of aluminum, magnesium, silicon alloys remain high even after aging at 400 degrees of Celsius. Thank you for attention.
Thank you very much. And the next one may be the yours too. Am I right? After, instead of Alexei Muzika, or Alexei Muzika will make a report. Alexei Muzika. Or again, Mykola Yefimov will make a report.
Good afternoon. I will present our short report. Aluminum alloys represent a new class within the well-known aluminum magnesium manganese system. With the addition of 0.2% lithium to their chemical composition, these alloys are characterized by an excellent combination of mechanical properties, including low density, increased elastic modulus, and relatively high strength. Therefore, it is reasonable to investigate the influence of alloying with scandium, zirconium, and cerium on the mechanical properties and corrosion resistance of this group of alloys. The microstructure of the samples was examined using optical and transmission electron microscopy. To determine the mechanical properties, tensile tests were carried out. The values of ultimate tensile strength, yield strength, and elongation to failure were calculated. General corrosion was studied by performing tensile tests on the corresponding specimens before and after exposure to 3% natrium chlorine plus 1% hydrogen chlorine solution for 90 days. The studied alloys had the following composition, which are presented on the in the table on the screen. The structure of alloy 1 after extrusion consists of recrystallized grains, 60% of them, and elongated fibers. Fine recrystallized grains occupy approximately 50% of the metallographic section in alloy 2 and 30% in alloy 3. Alloying the base composition with scandium and zirconium improved strength characteristics but led to reduced plasticity. In contrast, the addition of scandium, zirconium, and cerium in alloy 3 not only enhanced the strength properties but also ensured satisfactory plasticity at approximately 7%. The mechanical properties of the experimental alloys decreased after exposure to general corrosion. Also, the extent of degradation varied. For the base alloys 1, the yield strength was reduced by 13%, while in alloy 2 and 3, yield strength decreased by only 2%. Thank you.
Thank you very much. The next one again, Mykola Yefimov. Study the effect of scandium on the formation of a quasi-crystalline phase in aluminium copper ferrum ingots.
Okay, thank you. Dear colleagues, let me present to you the report devoted to studying of the effect of scandium on the formation of a quasi-crystalline phase in aluminum copper ferrum ingots. The study of the possibility of improving the physical and mechanical characteristics of stable icosahedral quasicrystals of aluminum copper ferrum system has a great scientific and practical interest. It is known that alloying of most aluminum alloys with scandium has a positive effect on their characteristics. Therefore, it seems reasonable to study the effect of scandium alloying on the structure and properties of the aluminum copper ferrum quasicrystalline alloys obtained by rapid crystallization. Ingots of the alloys from the system aluminum copper ferrum, both with and without scandium, with obtained and studied. For manufacturing, the technique of drawing the melt into a thin quartz tube was used. During the study, ingots was annealed in vacuum. Ingots microstructure was studied by same technique and X-ray investigation. Hardness and corrosion resistance were measured. The structure of aluminum copper ferrum cast ingot was characterized of the presence of stable icosahedral quasicrystalline psi phase and a crystalline beta phase and lambda phase. In the scandium contained ingot, in addition to the psi quasicrystalline phase and beta and lambda crystalline phase formed in non-alloyed ingots, the formation of a crystalline W phase with a hexagonal lattice containing about 8 atomic percents of scandium was observed. It is established that alloying of the quasicrystalline aluminum copper ferrum alloy with scandium in the amount of 0.3 and 0.4 weight percent significantly increase the content of the quasicrystalline icosahedral phase in ingot from 40 to 65 volume percent. In addition, alloying with scandium expands the region of existence of the quasicrystalline phase. The quasicrystalline phase contains about 0.01 atomic percent of scandium, but even such small content of scandium facilitates its stabilization. The study of electrochemical characteristics of in the corrosion process of quasicrystalline ingots showed that alloying of aluminum copper ferrum quasicrystals with scandium decrease the corrosion rate of non-annealed sample and simultaneously lowered the values of corrosion and pitting formation potential. It is proposed that the scandium addition to the aluminum copper ferrum alloys should increase the stability of the quasi-crystalline phase due to the large amount diameter of scandium compared to the atomic diameter of aluminum, copper, and ferrum. This difference of atomic diameter between scandium and aluminum, copper, and ferrum stabilize the quasi-crystalline clusters and improve all mechanical and corrosion characteristics of quasi-crystals. Thank you for attention.
Thank you very much, Mykola Yefimov. The next one, Anatoly Titenko. Are you online? Anatoly Titenko. Anatoly Titenko.
Can I speak from our group?
Yes, of course.
Hello.
Structure formation in a triple copper aluminum based alloys with shape memory effect.
Good afternoon. Today I will present our recent work focused on structure formation in cuprum aluminum based alloys with shape memory effect, particularly those doped with iron. These materials are of great interest for developing functional actuators, sensors, and microdrivers, thanks to their unique combination of ferromagnetic and shape memory properties. A series of alloys with general composition cuprum, 20.8 aluminum, X ferrum, where X range from 0.1 to 1 waste percent. We are prepared by conventional melting and casting methods, followed by homogenization, quenching, and low temperature annealing. The martensitic transformation were examined using differential scanning calorimetry, while the crystal structure was analyzed by powder X-ray diffraction. The magnetic properties were characterized by measuring the magnesium as a functional of applied magnetic field. The DSC curves revealed a two-shape martensitic transformation, showing both direct and reverse transition. With increasing ferrum concentration, the transformation temperature, both martensit start and austenite start, gradually decrease. For example, martensit start drop from about 307 degrees Celsius at 0.1 waste percent ferrum to 281 degrees Celsius at 1 waste percent ferrum. Similarly, the transformation enthalpy remained nearly constant, indicates that ferrum substitution modifies the kinetic razor than the energy of transformation. Powered by X-ray diffraction analysis confirm the presence of two orthorhombical martensit phases. Beta 1 martensit characterized by faulted structure and gamma martensit formed via twinned mechanism. The ratio between these phases depended strong on ferrum content and thermal treatment. The magnetization versus field curves demonstrate a clear evolution of the magnetic state. At low ferrum content, the alloy exhibits super paramagnetic like behavior, whereas higher ferrum concentration led to the development of a ferromagnetic response. This transition indicates that ferrum atoms promote magnetic clustering within the cuprum aluminum matrix, leading to the formation of ferromagnetic domains that interact with the martensitic structure. As a result, we observe a strong magnetostructural coupling, which is essential for achieving the ferromagnetic shape memory effect. To summarize, ferrum alloying induce a two-stage martensite transformation with distinct morphological and kinetic features. Increases ferrum content leads to a reduction in martensitic transformation temperature and to a magnetic transformation for superparamagnetic to ferromagnetic behavior. The observed change in magnetization curves confirm the formation of ferromagnetic clusters, which enhance the magnetic sensitivity of the alloy. Thank you for your attention.
Thank you very much. And the next report is Daria Savchenko. Daria Savchenko, are you online?
No, Daria Savchenko is offline, but in Kyiv.
Okay. In EPR study of copper aluminum ferrum alloys with low ferrum content. Please, Daria Savchenko.
Good afternoon, everyone. So my talk is about electron paramagnetic resonance study of copper aluminum iron alloys with low iron content. This work was done in collaboration with Kurdumov Institute for Metal Physics and Barykhtar Institute of Magnetism, and also with the Technical Center NAS of Ukraine, where EPR measurements were performed at the X-band frequency range and Bruker Alexis E580 spectrometer. So copper aluminum alloys is very well known for the unique combination of mechanical and magnetic properties, and when we add iron into copper aluminum alloys, it alters the eptectoid transformation point and also the deformation behavior, and thus it improves its mechanical performance. And from the other side, it can lead to variation of transformation temperature and to stabilization of the beta phase. And also, what is important, it enhances of the shape memory effect. However, despite of the detailed study of structural and mechanical properties of copper aluminum iron alloys, the magnetic and electronic futures remain an area of active research. So our work was focused on the magnetic and electronic properties of copper aluminum iron alloys. We have studies with samples with different iron content 0.1, 0.3, and 1%. The aluminum content was stable at 12.8%. Our powder samples were smelted in an induction furnace in an argon atmosphere. Afterwards, they were pre-quenched from 850 Celsius in water, and afterward annealed at 200 Celsius for 360 minutes. So let us proceed to experimental results. In EPR spectra of the sample with 0.1% of iron, we have seen an intense EPR signal. It's so-called low field microwave absorption, and there is a sign of ferromagnetic ordering. What is interesting, this signal vanishes as a ferrum content rises, and as a result, it can hit at the transition from positive ferromagnetic behavior to a frustrated, disordered magnetic state that can be, for example, spin glass state. Two other signals we have labeled them I1 and I2 were presented in the EPR spectra of all the samples under study, and the intensity rises with the rise of iron content. So we have measured the temperature dependence of the EPR spectra in the broad temperature range in the sample with 1% of iron. And based on this temperature-dependent analysis of the G factor, EPR line width, and EPR spectral intensity, we have concluded that I1 signal is due to exchange coupled iron 3+ ions, and I2 signal can be attributed to the isolated iron 3+ ions that are in distorted octahedral environments. What is interesting in the temperature dependence of all this EPR parameter is there is a sudden drop in all the dependencies at 25 K. And it is exact this same temperature where the spin glass-like transition was previously observed in copper, aluminum, iron alloys. So we have confirmed this behavior but by EPR, and also have identified all paramagnetic centers that were observed in those alloys, and the results we have obtained, of course, enhance the understanding of the magnetic properties of copper, aluminum, iron alloys, and support their potential for application in spintronics and magnetic sensors. So thank you for your attention.
Thank you very much. And the next one is Volodymyr Katerlenko. Are you with us, Volodymyr Katerlenko? Volodymyr Katerlenko.
Volodymyr is here. Please, one moment.
Okay, investigation of mechanical and tribotechnical properties of alloys based on the ferrum, chromium, titanium, boron system.
Hello, friends. Today I wanted to tell a few words about our development of new tungsten-free coatings on steels. The idea of the research is to find new coatings consistent of titanium, chromium, and borate with ferrum, which are tungsten-free, because this is much cheaper than usual tungsten quantities. And we want to have good wear resistance. So during our research, the first step was to make electrode powder wire based on ferrum, chrome, titanium borate system. The powder in the outer shell is made from ferrum or some cheap steel, and the inner powder consists from ferrum titanium, chromium, and ferrum borate. After this, we make automatic surfacing electrode powder on steel substrate, what you can see on the pictures. And the next step is tribotechnical measurement of tribotechnical properties. The sample is researched by a flow of air abrasive mixture. So the early research results show that our coatings have significantly greater wear resistance, but they don't outperform tungsten-containing industrial coatings. The further research will be continued. Okay, thank you.
Thank you very much. The next one, Яна Матвієнка.
Випробування триботехнічні проводили. Все чи?
Так.
Yana Matviyenko.
Sorry, Yana is also here offline.
Okay, great. Structure, thermal, and mechanical properties of nearly stoichiometric boron-copper-3 aluminum binary alloys obtained by vacuum arc melting.
Please wait a minute. We have some technical difficulties. Okay.
Okay. I'm from Institute for Metal Physics and Department of Physics of Dispersed Systems. Mainly my work concerned on mechanical alloyed powder composites on the base of aluminum and copper with carbon additions. However, today I would like to present you a little report about binary alloy in the region of beta phase. We tried to find appropriate substrate to obtain coating from our powder composite. It is well known that rapid solidification in the region of beta phase lead to eutectoid transformation with beta one-stroke martensite phase formation. However, these alloys are not very ductile. They have low tensile elongation. So one method to improve it is to obtain alloy with columnar grained structure. We produced copper aluminum binary alloy with 12.7 weight% of aluminum via vacuum arc melting method. And here we analyze structure along longitudinal and cross section. Here we can see results of optical microscopy and scanning electron microscopy in backscattered mode. And we observed a lot of martensite needle-like structure. The grains that we obtained along longitudinal section, the width of grains was up to 300 micrometers. And also we examined the samples via X-ray diffraction. We also observed a lot of beta one-stroke martensite along longitudinal and cross section. However, I have to mention that longitudinal section was more textured. Also, we applied annealing at 850 degrees about centigrade for 1 hour. And now we can see that we don't have martensite structure anymore. We just have gamma 2 phase and alpha phase. And we analyzed effect of structure along longitudinal cross section and heat treatment on micro hardness, Young modulus, and plasticity coefficient. We can see that highest plasticity was for as received samples, and the highest microstructure was for cross section. I would like to tell that it's only a small first step to obtain coating. The next step will be modification of microstructure with rolling and laser treatment. And the second one is application of additive technology to have some coating of powder. Thank you for your time.
Thank you. Thank you very much. And the next one more report by Sergei Tesla, novel ferrum aluminum, copper, nickel, and titanium, high entropy alloys.
Hello again, dear colleagues. So now I will present you the results of our research by preparation of the novel high entropy alloys based on the iron, aluminum, copper, nickel, and titanium. So the research was focused on the study in the preparation of non-equiatomic high entropy alloys by mechanical alloying and with the next spark plasma sintering. So this composition was prepared firstly in the Germany with our colleagues in the Otto von Guericke University by arc melting, and the features of these alloys is the solid precipitation and the precipitation of the Laves and the Heusler phases after heat treatment, so which increase the hardness and the strength, but the plasticity decrease, and after some cycle of the heating and cooling, that materials is quite brittle, and so it can be used in the different high temperature applications for the aerospace and for the rocket systems. So we want to increase the complex of the room temperature and the high temperature properties by preparation of the high entropy alloy by powder metallurgy route. So after mechanical alloying, practically to the 20-hour, the residual titanium atoms also we can indicate in the substructures of the powders and in the XRD pattern. That was happened because the titanium has quite small atom radio compared to the other elements in the composition. So after 40 hours, we will have the BCC solid solution only. After sintering by spark plasma sintering at different temperature, we have different structure and different phase composition. In the both cases, we can see the titanium carbide reflex and the carbide titanium carbide particles in the sintered high entropy structure. So the increasing in the temperature change the volume percentage of the titanium carbide. Because of we prepare the high entropy alloys by mechanical alloying in the petrol, so the residual carbon atoms near 3, sometimes 2.5% weight percent was in the composition in the powder around the particles. So during the sintering, the carbon react with the titanium and form the uniform distribution particles around the BCC solid solution structure. So in this work, a new non-equiatomic high entropy alloy was synthesized by mechanical alloying. It was established that the formation of homogeneous BCC solid solution occurs during the mechanical alloying after 40 hours. It's shown that after spark plasma sintering of the high entropy alloys, the formation of titanium carbide particles occurs. The growth of that particles is due to the some percentage of residual carbon from gasoline in the initial powder. Thank you. Thank you for attention.
Thank you very much. And I would like to ask, has the Sergei Nakoniechny joined us or not?
Yes.
Okay, the next one, Sergei Nakoniechny, aluminium, nickel, chromium, titanium, high entropy alloy, resulted from mechanical alloying from electron beam sintering.
Good day. Today I report for one of new high-entropy alloy based on 4 elements: aluminum, nickel, chromium, and titanium. The high-entropy alloy powders was obtained by mechanical alloying in planetary ball mill for only 15 hours in petrol. This was enough to obtain two-phase composition of face-centered and body-centered crystal structure. White and more gray phase on microstructure of hair powder particles, and some residues of titanium, which was left for future interaction and also strengthening of grain boundaries and grains of high entropy alloys in electron beam sintering. The method of sintering was choose to short time sintering, low interaction, and highest energy temperature of sintering. After sintering, we obtain very homogeneous composite structure of dendritic tip, which was conclude mostly body-centered crystal structure grains, and at same times in more dark in dendritic regions we have some residues from face-centered phase. Also, we obtain some secondary phases as titanium carbide in the form of crest in very low content. And what was more unexpected for us, that more of carbon content was concentrated in the place of titanium concentration left from mechanical alloying. Thus, so we obtain an ouch hard alloy, estimate 6.7 gigapascal, with also an ouch fracture toughness. That's why we also research the crack prolongation in the alloy. And from the mixture structure, it was seen that the main alloy phases, body-centered solid solution, and some content of face-centered solid solution have an ouch strength and break the prolongation of crack. That's why it can be used for more applications such as maybe aerospace materials. The chosen high entropy alloy have less weight, less than 5 gram per centimeter cube per volume, and also have an ouch hard and fracture toughness. While low concentration of carbon in solid solution is a more perspective for ductility of materials, which will be future aims of this work. Thank you for your attention.
Thank you very much. And I would like to ask if Evgeny Titkov presented now. Evgeny Titkov.
Yes, we have Evgeny here in Kyiv offline location.
Okay, so the structure and properties of experimental low-cost titanium alloys is the next slide.
Hello, my name is Evgeny Titkov. I'm here to present the work on structure and properties of experimental low-cost titanium alloys that was conducted in the Proton Electric Welding Institute of the National Academy of Science of Ukraine. So as we know, titanium alloys are getting more popularity in the industry, partially because in modern times the cost of those alloys are is being actively reduced by either reducing cost of technology that is being used, or by finding the replacements for more expensive elements that are being commonly used in the production of those alloys. So for this work, we've chosen the electron beam melting technology that already found its use in the industry, because it allows to use the scrap metal and to use the leftovers from other manufacturing technologies. But in this work, we are studying the
Пожалуйста, говорите. Please speak louder.
So we're studying the cheaper alloying systems to replace the common use more expensive elements like vanadium, molybdenum, niobium, and they are also commonly combined with such expensive elements like zirconium and rare earth elements like, for example, gadolinium or cerium. And here, to stabilize beta phase, we've chosen iron, which is also commonly used, but it has limited use due to its possibility to make the material too brittle and thus have low strength. But latest works shown that at lower content, in combination with some low amounts of oxygen, it can lead to good results. And also, a different alloy that uses aluminum, molybdenum, and iron as stabilizers for beta phase. So the first alloy is aimed to be a pseudo-alpha alloy, and second alloy should be a pseudo-beta alloy. So both alloys were obtained in our institute, and the X-ray studies shown that indeed the iron and oxygen alloy is a pseudo-alpha alloy, and the aluminum molybdenum ferrum is a pseudo-beta alloy. Further studies using microscopy, namely transmission electron microscopy, has shown that those alloying systems in the first case allow formation of intermetallic phase of ferrum with titanium, and two complex oxides with both of those elements, as well as titanium oxide. Those particles of the above-mentioned elements are uniformly distributed across all of the material. Similar results we've seen in the second alloy. We see a formation of intermetallic particles with intermetallic phase of titanium with all of the three alloying elements of iron, aluminum, and molybdenum. In second case, the particles are also uniformly distributed across the material. And this uniform distribution provides a dispersion hardening, which leads to a very high hardness of the material. In case of titanium ferrum oxygen, it reaches 2,700 megapascal, and in case of titanium, aluminum, molybdenum ferrum, the hardness reaches 3,800 megapascal, which is rather high for titanium alloys. At the same time, the increase of hardness with these alloying systems does not increase to excessive brittleness of the material, and the strength tests show that both materials have strength around 1,000 megapascal, with the pseudo-alpha alloy of titanium ferrum oxygen being 3 to 7%, having 3 to 7% lower strength. So 1,000 megapascal is comparable strength to the to the alloys that have more expensive alloying systems and are widely used in the industry. Thank you for your attention.
Thank you very much. So it's all agenda of our symposium. Dear colleagues, dear conference participants, the Metals and Alloys Symposium of 9th International Material Science Conference, HighMatTech-2025, a major event held in Dnipro, has concluded. The symposium once again demonstrated that the science knows no barriers, and desire for new knowledge and exchange of experience unite people from all corners of the world. Over the course of these days, we saw fascinating scientific discussion and explored the development direction of modern material science. Conference participants presented results and ideas that will undoubtedly serve as a comprehensive foundation for the further development of fundamental principles in material science and the search of new functional materials. On behalf of our organizing committee and of the head of our institute, we would like to express our deep gratitude to all participants of HighMatTech 2025 conference for their high quality presentations, constructive questions, and active discussion of the presenters' materials. We would like to express special thanks to the partners, sponsors, moderators, and system administrators who made HighMatTech 2025 possible. And from myself, great thanks to Dr. Marina Starozhenko for the support. I'm so happy that I am become a part of an amazing event. We wish everyone continue creative success in other scientific works and new discoveries. May results achieved become a solid foundation for new research, and may the established connection develop in a long-term, mutually beneficial collaboration. Dear colleagues, we are looking forward to see you again at HighMatTech conference. Thank you everyone who joined us. Eve?
Thank you all also for your great job. I hope that one day we will meet offline, maybe at Francevich Institute for Problems of Material Science, maybe in Dnipro, but currently I think we have many friends around the Ukraine, so we can travel and meet our colleagues in many cities of Ukraine. Thank you very much for your job and for your participation.
Thank you very much.
Dear ladies and gentlemen, good afternoon again. My name is Marina Storozhenko. I'm Doctor of Science. I am head of the Symposium of Films and Coatings, and today I will moderate our session. It's really great pleasure for me to say welcome to all of you because I think we have a very strong direction in the science connected with the coatings here in Ukraine. But I am also very glad to say welcome to our international participants who are online now. Today, we have some changes in our conference program because our first keynote speaker, Andreas Rosenkrantz, unfortunately is not available to join us today due to some troubles. So it's my pleasure to introduce our next key speaker. It's Dr. Oksana Bersirova from Vernadsky Institute of General and Inorganic Chemistry, National Academy of Ukraine, with the keynote speech, Advanced Electrolytic Coatings Based on Noble Metals and Superalloys of Refractory Metals. Please.
Thank you very much. Good day, dear colleagues. My name is Oksana Bersirova. I'm electrochemist, Institute of General and Inorganic Chemistry of National Academy of Science is my home institution. For 2 years, I worked in Vilnius University in frame of the project of Maria Sklodowska-Curie Action for Ukraine. But now I work in my Ukrainian department of electrochemical material science and electrocatalysis. So, electrochemical material science is a field that connects electrochemistry and material science. It studies how materials can be created, modified, or improved using electrochemical methods. Electrochemical material science focuses on structure, composition, and properties, especially on materials with special and valuable functional properties. There are many different methods for metals and alloys production, but the electrochemical method has several important advantages. You can see on the slide, easy to control of alloys composition, the ability to create coatings that are inaccessible to other methods. This method is simple, energy efficient, and can produce multi-component or nanostructure materials without expensive equipment. That is why electrodeposition remains one of the most powerful and flexible tools in modern material science. So in this presentation, I will focus only on the controlled electrochemical formation of functional materials, functional coatings. The slide shows the classical triad of Kurnakov: synthesis, structure, and properties. Establishing the relationship between all parts of this chain makes it possible to control the properties of future functional materials and even predict them. The main tools of the electrochemical synthesis is vast composition, especially composition of electrochemical active complexes, and electrolysis parameters, current densities, potential, and over-potential electrochemical resistivity. The electrochemical method has many internal and external factors that influence on the coating formation. You can see on the slide, the main ones include electrolyte composition, electrolysis mode, and parameters, and different external factors, including even different fields. Such method include stationary and non-stationary pulsed program electrolyzers, magneto-electrolyzers, sono-electrolyzers. All their tools can be used to control the composition, structure, and properties of coatings. The development of technology of electrochemical formation of functional materials, functional coatings. This fundamental and applied aspects. The main approaches to solving the fundamental aspects of functional electrodeposition, I will show the application of the formation of functional coating for microelectronics. Microelectronics is a high-tech industry, and its product contain almost all industrial requirements, but the main thing in it is reliability. For any product, there are strict requirements for the necessary complex of functional properties. Using as example of noble metals, silver and gold, I will show how we operated the fundamental aspects. I will try to show complex things in a simple way. We have identified the relationship between electrochemical kinetics, current, potential, and overpotential, and electrodeposition, structure, and morphology. Crystalline grain size as a main structural characteristic of deposit is directly related to the kinetic of electrochemical active complexes electroreduction. The key levers for effective control of electrochemical system are firstly, the composition of ions in the bulk of the electrolyte, the Yatsemirski and Bierun function, and the composition of ions of the electrode surface and in the near electrode layer is the Gordievsky and Kublanovsky function, electrochemical kinetic function. If we know them, then we can determine electrochemical active complexes and electrochemical non-active complexes for all systems. Look on this slide. With scanning electron microscopy photo of silver deposits from solution of various complexes obtained at the same conditions. The morphology and structure is different. This means the influence of the kinetics and mechanism of electrochemical active complexes discharge on the oriented electrocrystallization of deposits on coatings structure. In order to consistently achieve the required functional properties, it is necessary to learn how to controllably obtain the appropriate structure. Here I will show a simple example of how the reduction kinetics of the complex affect the surface structure and of the deposit. On the slide, you can see the polarization curve for the reduction of trisene argentate of ions together with microphotographs of coatings obtained at different current density. You can see on the slide from 5 to 75 microampere per centimeter square. As we move along the polarization curve, the surface morphology changes dramatically. The most uniform fine grain coatings appear at around 15 milliampere per centimeter square, which corresponded to the mixed kinetic region of deposition. This behavior is very typical for all silver electrolytes. This slide shows a typical polarization curve, which can be divided into several distinct regions. First region, inhibition. The process is slowed down and no deposit is formed. Second region, slow discharge. The reduction begins, but growth is limited. And next, the mixed kinetic region. Under these conditions, fine-grained and nanocrystalline deposits are typically formed. Following region diffusion control and limiting current zone, here we observe the formation of spheroids, amorphous deposits, and powders. And finally, at more negative potential, other processes occur. For example, hydrogen evolution and metal oxide phases may appear. It can be seen that functional coatings are formed only within the region of mixed kinetics in a narrow potential interval where the energy conditions for crystal growth are more favorable for production of desired structure of thin silver and gold coatings. Our studies have shown that the structure of the deposit depends not only on the polarization current, which determines the growth rate, and not only on the deposition potential, but most importantly, on the combination of both. It is balance that allows us to obtain the specific nanostructure responsible for the functional properties of the coatings. The current density, the rate of the growth, while the potential control the surface energy. And really, nanocrystalline functional coatings of silver and gold are formed only under mixed kinetic conditions. The size of the crystal grain as the main structural characteristic of the deposit is directly dependent on the kinetics of the electroreduction of electrochemical active complex. The smallest crystallite size are characterized by deposit obtained at deposition current density corresponding to half the limiting current. We have established a dynamical stability regime of electrochemical system. It's in this dynamic stability regime, the most favorable crystal facet growth energy for the formation of clearly defined metal structure that coatings will a stable set of recurrent functional characteristics are formed. It has been established that within this interval, the electrodeposition process remains stable. This means that in this range, we obtain a structure where the following parameters reach stable minimum values of crystalline size, and internal microstress and roughness, and with a high value of corrosion resistance, and micro hardness and electrical resistivity. The table shows requirements for silver and gold functional coating for microelectronic products. Our research we can obtain functional coatings of silver gold with all set of requirements for macroelectronics. So I want to present you several our main technical developments that has been successfully implemented in production. And now I'm going to talk about next part of my presentation, electrochemical formation of functional coatings of superalloys, molybdenum, tungsten, and rhenium alloys with iron group metals. Cat-resistant alloys based on the iron subgroup with molybdenum, tungsten, and rhenium, often called superalloys. Such materials work in extreme temperature and power conditions in aggressive environment. You can see an example of superalloys application. It's maybe height resistance, scale resistance, wear resistant alloys, it's different functional coatings and composite coatings, nanofiber alloys, high temperature, 3D printers. And also it's magnetic materials and different materials for hydrogen energy and catalysis in fuel cells. It's very important materials. In my home department, we 20 years studied electrodeposition of binary and ternary molybdenum, tungsten and rhenium alloys with iron group metals. It's nickel, cobalt, and ferrum. The surface and structured deposit, corrosion and electrocatalytic behavior. A combination of unique physical and chemical properties of superalloys renders these metals promising for using in high technology sectors, in aviation, nuclear power engineering, electronics, biomedicine, and catalysis, and other. So the main objective is our study is development of efficient electrochemical synthesis of multifunctional magnetic and electrocatalytic dense films of binary and ternary refractory metals alloys with the iron group metals. In an enable way to control composition and nanostructure and study their functional properties. On the slide, you can see very short illustration of our scientific group research results in obtain of different functional coatings. And also, right, on the slide, you can see a contribution of Ukrainian scientists to the study of theoretical and applied aspect of electrodeposition of superalloys, according to the Web of Science. You can see it's very, very good. It's 6%. It's very high, very high. So in 2021 years, my colleagues and me were awarded the Patton National Prize of Ukraine for our scientific results. And the head of our group, Professor Poblanovsky, entered the top 20 authors who have made the greatest contribution to the topic of electrodeposition of functional coatings of refractory metal alloys with iron group metals. And today, the object our investigation is rhenium alloys. You can see the largest application of materials based of rhenium alloys is superalloys, 70%, especially for jet craft, aircraft engine gas turbine blades. Yes, more intensive study of rhenium alloys electrodeposition started in 1990. Up to now, only 76 papers published in journal having impact factor, and only 50 papers deal with rhenium alloys with iron group metals. So I would like to draw your attention. There are two main researchers group investigated these alloys in Tel Aviv University in Israel and my home institution. The main attention is paid for nickel rhenium alloys. Some results are published on cobalt rhenium alloys, whereas research on ferrum rhenium alloys has been scarce. Therefore, the development of a new electrochemical method of ferrum rhenium alloys obtained is of particular interest. Early, I have studied system nickel rhenium. The fundamentals of controlled classical and induced electrochemical synthesis of nickel rhenium alloys from sulfamide and citrate electrolyte have been developed. During the electrodeposition of the nickel-rhenium alloys, the catalytic effect of nickel of the electrodeposition of rhenium occurs. I want to show that composition, structure, and morphology of the obtained deposit depend on the composition of the electrolyte and the modes of electrolysis. Nickel-rhenium coatings from 8 to 58 atomic percent of rhenium deposited from sulfamate electrolytes. The use of citrate electrolyte allows to increase the current efficiency, but at the same time, the rhenium content is reduced. Corrosive, electrocatalytic, and magnetic properties of nickel-rhenium depend not only on chemical, but also on phase composition. Changing the complex composition of the electrolyte and hydrodynamic conditions allows to vary the chemical composition and size of nickel-rhenium crystallites. It is found in the study that the nickel-rhenium alloy composition is largely determined by the ratio of concentration of rhenium and nickel in the solutions, and weakly depends on the current density and temperature. You can see the reducing of rhenium concentration in the citrate base by half lead to a dramatical decrease in its content in the alloy. The role of rhenium content in rhenium alloys with nickel has been established, which is based on the ability to control the crystalline size and make it possible to vary the structure, nanocrystalline, amorphous-like, by changing the composition of the alloy. The concentration of electrolytes and the electrolysis mode allow precise control and reproduction of the chemical composition, thickness, and structure of coatings. The quantitative composition of nickel-rhenium alloys can be varied from 5 to 95 mass percent rhenium with a current efficiency of 15 to 99%. It was found that nickel-rhenium coatings obtained from a sulfamide electrolyte have a fairly high tension, which sometimes lead to hair peeling, and coating from citrate electrolyte is characterized by high ductility and quality of adhesion to the base. So the influence of current density, temperature, and pH as a ratio of main components of the electrolyte on the composition and structure electrodeposited rhenium alloys formed from sulfamide and citrate co-solution is different. It can be explained by different synthesis mechanism, classical or induced. Now, the main subject of our new study is similar system, ferromrhenium, because of some restriction. Nickel is highly allergenic, and cobalt salts appear as substances of high concern. Several key aspects can be determined the interest in the study of electrodeposition of ferromrhenium superalloys. It's exhibit either soft or high magnetic properties depending on alloy composition, and they have potential to be used in the micro devices. And so rhenium alloys exhibit electrocatalytic properties in the reaction of hydrogen evolution. However, a problem that related with intensification of electrodeposition and convenient control of ferrum alloys still limit the larger application. The electric position of ferrum alloys is often carried out using ferrum-2 based compounds. However, repeat ferroferry oxidation reduced ferroferry reduced the base lifetime and reproducibility. We have just started working with this system and have so far developed new thermodynamically stable citrate electrolyte for ferrum rhenium alloys electric deposition based on ferrum-3 compounds. During the study, it was possible to obtain from developed bias dense coatings of ferrum rhenium alloys with rhenium contents from 1 to 95 atomic percent. For example, ferrum rhenium coatings containing about 75% of rhenium are deposited at room temperature without stirring, but use the stirring or ultrasonic bath significantly improved the surface quality, as you can see on the slide. The structure of the coatings differs for alloys of different composition, from amorphous for rhenium and rhenium-rich alloys to polycrystalline for the iron-rich alloys. The crystalline size of the obtained alloys is from 2 to 25 nanometers. So the main idea of our project, all proposed family of iron group metals magnetic alloys are divided into two groups. Soft magnetics, compact films, it's iron rich alloys with high crystalline sizes. And hard magnetic compact films, rhenium alloys with iron group rich metals with low crystalline sizes. And such group of investigation object consists of electrocatalytic materials, iron group alloys with high content of rhenium. So you can see on the slide that for ferrum rhenium alloys, we have obtained coatings that meet the requirements and specific ranges corresponding to obtaining promising materials that can have the properties of soft magnets, hard magnets, and electrocatalysis. The study of catalytic and magnetic properties of obtained ferrum rhenium alloys is the next part of my study. And the end of my presentation, I want to thank my mentor and scientific guru, Professor Kublanovsky. I'm thanking my hard-working research group and friendly collective of Faculty of Chemistry of Vilnius University. And of course, thank you to organizing committee to possibility to take part in this very interesting conference. Thank you for your attention.
Thank you, Dr. Oksana, for such interesting and insightful presentation. We have some time for the discussion, so colleagues, please, your questions. Please, Dr. Olena Lavrinenko, Francevich Institute for Problems of Material Science.
Thank you very much for your very interesting talk. And my questions is, what is the technical application, your catalysts, and which role plays precious metal, noble metals coating on the activity of the... Okay. Okay. I will thank you again for your very nice talk. And the questions is what is the technical application of your catalyst and which role plays the noble metal coating on the activity of your catalytical system? Thank you very much.
Thank you for your questions. The catalytic properties of noble metals, it's not idea or investigation. Electrocatalytic properties we study only for alloys, superalloys, alloys of refractory metals and molybdenum, tungsten, and rhenium alloys with iron group metals, iron subgroup metals. And it's such materials is very perspective as electrocatalytic properties of electrocatalytic materials for hydrogen evolution. And it's I know that from this materials, the highest electrocatalytic properties, the high value of electrochemical activity have nickel molybdenum alloys from this subject. But I think that maybe it will be in future. I think it's rhenium alloys will be higher values of electrocatalytic activity. So it's because maybe it's very important of electronic configuration, because metals with D4, D5 configuration, it's with content with metals for metals with D6, D8 configuration. It's very good perspective materials maybe for electrocatalytic properties. So we study such object.
And do you use your catalyst for hydrogen evolution? Was testing your catalyst was test?
It was electrochemical testing. We study polarization curve of for our subject. We obtain a polarization curve in potassium potassium media, 1 mole and to 31 mole kali-wash media, and we analyze it or current of current of exchange. We analyze it of our potential of this reaction, and we can change. We can give
to compare.
And my questions lie in the field that only hydrogen do you obtain or another gases, oxygen or carbon?
Yes. Yes.
You analyze these gases. It is important for practical application in the hydrogen engineering and
yes, not only hydrogen, but also oxygen, but
carbon dioxide maybe.
Yes.
Thank you very much. Thank you for your answers. And sorry, maybe my questions was very.
Thank you very much. More questions, please? No, so I will have opportunity to ask something. Dear Oksana, please, can you show slide 10 or maybe 11?
Oh, okay.
Its structure, it's the surface or is it is cross-sectional structure?
Structure or surface.
Of surface. So we can conclude about the roughness, yes, but it's very interesting pictures in the Yes, because it's like some powder particles on the surface. Yes.
Yes, because in this area of polarization curve, we have kinetic of diffusion kinetic and limited current density. In this range, we obtain it's typically obtained of spheroid and.
But what is the size? Because it's very small.
It's
increasing.
It's maybe different. I don't see.
Oh, it's not very, very. Okay.
Interesting.
Yes, very interesting structure, especially for the surface. Oh, and it's some mountains. Yes.
Yes.
Some crystals. Yes, are growing. Okay, thank you very much. And as I know, the thickness of such coatings is not very high. What is the range of the thickness of such type of the coatings?
Thickness, we can regulate thickness, yes, and from nanometers to, I don't know, but 20 micrometers maybe.
But for practical applications, what is the optimal thickness?
For microelectronics, it's about 10 micrometers. Micrometers, yes. For contact materials, for microelectronics, it's our...
Okay. And maybe somebody has questions? No? So only one small question. Yes, I agree that iron-based rhenium alloys is much more better because it's more cheap, and nickel is not only toxic effect has, but according to the European classification, nickel is
allergenic.
Yes, nickel belongs to the critical raw materials.
Yes.
So, but what is about the properties? Which alloys have highest properties? Nickel-based or iron-based, or can we compare because we have problem, for example, for high temperature application, nickel sometimes it's only one function that we have, because iron-based alloys are not available to work at high temperatures. But what is about your practical applications?
Practical application of nickel alloys, you're right, but in aerospace, for aerospace product, it's gas blade turbine. Now it's nickel coatings is good.
Is better.
It's better. It's no other not cobalt, not ferrum. It's not used in this. But I don't know. Maybe we I hope we can.
But we don't need nickel alloys for all the applications. Yes, for high temperature, yes, but not for all. Maybe for your applications, iron-based alloys maybe will be better.
Maybe, but it's functional coatings.
Yes,
not only.
What does I mean? That maybe for your applications, iron-based alloys will be better or comparable with nickel alloys. Yes,
we work. I hope.
Okay, thank you very much for a very interesting presentation and for the possibility to see you today at Frantsevich Institute for Problems of Material Science. It's very nice.
Welcome. Thank you.
Small question. Viktor Kisluk from Kurdyumov Institute of Metallophysics.
The technique itself of receiving this curve is the static. Is the sweeping rate the matter, or it doesn't matter?
It's typical. Typical for not only for it's for example for silver and for, but it's for other metals we can typical polarization curve. It's very good tools, electrochemical methods, so we can control it of structure. But the structure is very important for
Did you try to play with the rate? Probably also there's some tool to control some size or some morphology. Is it it has sense?
Yes.
Opinion.
Yes.
And so it's a rate dependence, or you just what's the criteria of choosing the specific rate?
It's correlation with potential deposition and current deposition. So we can it's correlation different kinetics of process, different kinetics. So it's different kinetics. Inhibition. I don't have any deposits. It's and mixed kinetics. We understand. We obtain fine grain coatings with good properties. But if you work in the other region, you can I don't know. Maybe for you use you need in pro powders on maybe spheroids coatings.
What is the value of the sweeping rate?
Value it's for other system it's different, but in region it's we can electrochemistry use and use equations. Thank you. Equations. What we can find this region for only for system for silver, for gold, for alloys. It's
what is the typical value? You know. What is the typical value? How long lasts this process?
I think it's from
it's hours or days or minutes.
How long?
Duration.
Duration of this process.
It's duration. It's
how much time it takes.
No. It's if you need in the very thick coatings films, duration will be smaller. But if you need in if you need for
micrometers,
you need maybe half of hour and half of hour at and it's different for different system. It's not constant. It's not.
You sweep the whole range. You may use only some restricted area, but the range of potential change is the same.
The same, yes,
so
yes.
You vary the rate.
Yes, it's very important. It's important. It's range. It's not for important only potential, but it's approximately half of limiting current density. Limiting current density for this different system is different. So for this half of current of limiting current density is it's dependent of this region. Sorry for my poor English.
Okay, thank you very much. Thank you again. I think we can continue our discussion in cover break.
With pleasure.
Yes.
With pleasure.
Thank you. And it's my pleasure to introduce our next speaker. It's Dr. Science Viktor Kisluk from Kurdyumov Institute of Metal Physics, National Academy of Science of Ukraine.
Good afternoon, dear colleagues. The chair, thank you for invitation and for this unique possibility. Prior to proceed, I would like to express my big grateful emotions to organizers for their efforts and time spent to organize this meeting. So the topic of my presentation is the result of our work entitled Thermoactivated Behaviors. Thermoactivated behavior of the ethylene vinyl acetate encapsulants under the tensile load. So the plan of my presentation, the outline, contains the material itself, just what is the problem, and then the material description, how the problems we deal with, what the matter, and then we will discuss the same characteristics we used to characterize the material and to find some peculiarities to establish the mechanism of degradation, because this is the main challenge. And we then consider the thermoactivation mechanism and make the conclusion. This is the whole run of this presentation. So first of all, I would like to present my colleagues. This is the Dr. Vladislav Shivanyuk, Yuri Palushkin, and Professor Vika Trechko. We make our mutual research on this topic, and also we would like to thank Dr. Ruth for XRD measurements, which also some very important part of our experiment. So probably each of you know, or at least one time at your life, you see the solar panels, photovoltaic, or probably another name is solar batteries. But in this field, the common title is solar photovoltaic cells, and there are several arrangements. They contain the elementary. It doesn't work. They contain elementary cell. This is a cell which is a part of probably as module, and module can combine into panel, and panel can combine to fabric some factory of electricity. So this is the whole set of facilities to generate electricity with the help of conversion of solar power, solar energy. And as a matter of fact, the main type of the solar cells is based on silicon. Now on the market, the silicon-based photovoltaic cells is the major representative of this kind of electricity. And the operation of these modules is regulated by standards. This is the standard of International Electrochemical Commission, which defines how they should work, what is the requirements, and the requirements is rather severe, because they demand 25-year service, and also performance efficiency should not reduce lower than 1% annually, and the total loss of power shouldn't exceed 5%. So as actually on practice, the customer overpay the price. They pay the overprice because the actual operation time or service life is lower, and they didn't serve 25 years with these requirements of performance. So, and what is the main, and why customers didn't count their money? This is the question. And probably this is the inertia of commerce, because it's very simple to have some technology, and the industry proceeds in this way. They just make the whole range of their products. They sell them, and doesn't matter how long they operate. And consumers the same way. They just buy and have some profit from their product, and doesn't matter how long it's served. But just look at this. This is 2011 year, and the effect of degradation of encapsulant is known, is already known. It is known just as the in-field testing of solar cells was known. It starts from 70s, last century, and just plus 25 years, just till the millennium, it will be known that they didn't serve 25 years. And what is the main features? This is the brown color, and cracks and discoloration and corrosion of metallization. Yes, this metallization made as electrodeposition method, just talking about in previous talk. So let's consider what is the reason why it so happens. But to consider this, just look at some frame of one element. Of one photovoltaic element contains the frame and the converters itself, the functional components of the converter, and it embedded in between EVA it's ethylene vinyl acetate foil, which encapsulates the whole element, just to avoid penetration of oxygen, of air, of humidity inside the heart of this device. So, and the cover glass is also some invitally element, because cover glass just protect from chemical damage. And what is the EVA copolymer? It's a copolymer of 2 units. It's polyethylene and vinyl acetate, and also it subjected to curing procedure, just annealing at some temperature near 150 degrees or around, and in the presence of some active initiator of curing, some cross-linking proceeds between the side groups, and so we have the rather strict material which able to protect. This is amorphous and crystalline. It's amorphous and crystalline material. It means that aside the amorphous phase, it also has some quasi-crystal, but this is quasi is important because it's also why so many materials called amorphous and crystalline, because of this method, X-ray diffraction. If X-ray diffraction has peculiarities, it means that we can treat them like materials which have some periodic order. So, and actually, this crystalline counterpart consists of polyethylene quasi-particles, quasi-nanoparticles with the size which can be calculated by Scherer formula as 7.4 nanometers of size. So we make tensile testing, and we discover a very huge, enormous dependence on temperature. If the temperature varies only around the room temperature, several degrees Celsius, several kelvins of Celsius, which corresponds only 1 milli-electron volt, we have a huge deviation of stress. You see this is the stress and strain, stress and strain dependence. The stress can change several times at the limited value of strain. And we just try to replot these dependencies, the series, and we see that they have a very peculiar dependence with pole, with this point of intersection of these lines, which are approximation of our dependencies. This is in another coordinates, the stress and temperature at various strain. And they have this pole and this value of cross-section, of intersection of these approximated lines with abscissa axis. And so we analyzed, and what we may conclude that these nanoparticles, the quasi-nanoparticles, behaves like knitting and unraveling. Unraveling and knitting is unraveling is the process reversal to knitting. Yeah, yeah. And so when we increase the temperature, then the melting itself proceeds like unraveling of some sweater, and we release the huge segment of polyethylene, and in such a way, we just, with our rather coarse mechanical testing method, may reveal such a very, very fine chemical, not the chemical, there's also mechanical, but nanomechanical phenomenon. So unraveling temperature, we define the temperature of intersection of these approximation lines, depends on the strain in such a manner that it has some non-monotonity. And these two modes of behavior corresponds to our previous investigation, our previous results, just made in terms of double logarithmic scale. And we then discovered two modes. This is the strain mode, this is the diffraction mode, and this dependence exactly corresponds to the behavior of temperature of unraveling, as we decided, as we defined. So the main conclusion, just not to be bothering, and what is our final purpose? The first was the establishing the mechanism, and now we know the mechanism. The mechanism is that the nanocrystals, just subjected to temperature and to stress, may unraveling and to release the large molecules. But is this process reversible or not? And we may conclude that it's not reversible processes, and it depends on the stress. And stress just put apart these released molecules, and that's the degradation starts. So at the core of this degradation process is not only chemical oxidation processes associated with the humidity and oxygen penetration inside the foil, but also the mechanistic process of unraveling. And so we may conclude that if we have component of EVA, which is embedded with between two substrates, let's say substrates, it's cover glass and silicon wafer, and if we compare the temperature coefficient, temperature expansion coefficient, we see the huge difference. So this is the operation conditions when we have very high value of stress, which acts on the EVA embedded between these two materials, because the temperature of module, its operation node, varies till 80% Celsius. This is a huge variation. Daily amplitude is rather high, and so the degradation just accumulates, and the module itself has no chance to proceed more than 25 years. And also, just to use another, what are the recommendations? Use another encapsulant. But producer says, we are common with this one. We know that the disadvantages, but the price, it doesn't matter. We has the role this encapsulant plays, and nothing changes. But customer should be aware of overpricing. So thank you for your attention, and for this possibility to
Thank you.
present.
Customer can be very careful, but customer usually don't can influence on the price of production company. Okay, dear colleagues, do you have questions? Okay, I have some questions. It was great idea with the presentation. Using your testing method, can you predict the service life of such elements or not? In real conditions, I mean.
This is what our final objective. It's not so easy, but we can use this set of experiments at different temperatures allows one to extract the data for estimation the time. We now the work of the algorithm now in progress, and we hope that we may propose the very clear algorithm how to make estimation, because it's not possible to make the strict decision. This is the real time of life. It's not possible.
But do you have experience of cooperation maybe with some producers to try your methods or testing methods? I understand it's not very easy. But I think many of researchers would like to have such experience, but usually it's very hard.
Everyone wants to live long. So it's all if we know the secret, it would be the solution for each of us, but it's impossible. This is the only some God play with this. But the producers just declare that they are interested in, but as a matter of fact, they do not have a huge involvement in the process of improving the lifetime of the material, and because it works.
Yes, and every innovations need also money, not efforts and money. So it's not very easy for producers also. And slide 6, I have one small questions. Maybe it's not for you. I just would like to ask your opinion.
It doesn't work.
6. The content of the laminations in the destruction is the highest. Why? Why the lamination? Why not corrosion or cracks? Why the lamination? It's because of poor adhesion or
because of this. The difference.
Difference in
the expansion coefficient. The stress at the interface is so huge, and we vary the temperature, and it varies along the while the operation time. So due to this this much mismatch.
Yes, it's a very good explanation. So thank you very much for a very interesting presentation and your great idea, because it was really presentable.
Thank you very much. Thank you.
Thank you,
everyone.
My pleasure to invite our next speaker. It's Irina Gaustyan from Kurdyumov Institute for Metal Physics, National Academy of Science, Ukraine, and she also works at Leibniz Institute for Solid State and Materials Research, Germany. And as I know, Irina is with us, but online.
Yes, hello, Marina. How are you?
We are fine, thank you.
Yeah,
it's
thank you for the introduction.
Okay,
Good
you can
afternoon,
share.
dear colleagues. Yeah. Let me a moment. Now I share my screen. I try to do it. Share. Share. No, it doesn't work.
We see your
It's
presentation. Oh, no.
yes, now you see. Yes.
Yes, we can see, but
Okay.
not full screen. Oh, yes,
Now it's okay.
You can start.
Okay. I don't see you now, but okay. Good afternoon, dear colleagues. Warm greeting from Dresden. This is not first talk about perovskite recently, I think. And I'm sure many of you have already heard about them. But if not, there's a brief introduction about to what perovskite are. Metal halide perovskite are the crystal with the formula ABX3. The A side is anorganic or inorganic cation. For example, it can be cesium or formamidinium. The B side is usually lead or tin, and the X side is a halide part. It's iodine, bromine, or chlorine, so on. Such structure give us special properties. For example, they absorb light very strongly, even when we have only thin films, and we can change the composition and tune the band gap. They are also absolutely tolerance to defects, for example. Because of this, perovskite are prospective for many applications, such new generation solar cells, LEDs, lasers, photodetectors, so on. And today I'll use a mixture perovskite with formula cesium FAPI bromide to demonstrate you, to show you our results. Here is the cesium and formamidinium occupies the A side, lead at the B side, and the halides such iodine and a small fraction of bromine sits on the X side. Okay. Such composition helps us to improve stability and optoelectronic properties. It is the organic compound of Phi that mostly gives stability to perovskite. There are several methods to prepare. Oh, sorry. I do something wrong. Several methods to prepare perovskite film, such as spin coating, beam evaporation, and I'll just highlight magnetron sputtering only, why it's so attractive and important in our work. Magnetron sputtering is interesting because it's scalable and allow uniform and well controlled films. But as usually in our life, there are pros and cons. This process is very non-equilibrium, and many parameters affect the final film, and it also needs very strict control. This is a general scheme of how sputtering works. Plasma creates energetic ions, and then they hit the target, and atoms are like ejected to form the film. By the way, our sputtering machine is a bit different, you'll see later, but in principle, it's the same. So the slide shows the general pathway from powder to film. First, we prepare the perovskite powder by mechanosynthesis in a ball mill. Then we press this powder into a dense target, and using this target, the film is deposited by magnetron sputtering. It can be glass substrate or substrate with ITO or another maybe coating before. And using the target's film deposit, and finally it can become like a part of the device architecture for solar cells. And now let me show each of the steps in more detail. This mechanosynthesis step using a planetary ball mill. We mix different precursors, and after milling during 3 hours, for example, we obtain powders with different composition. And here you can see my like a palette of struggling, because if even you strictly follow the protocol, each batch can still look completely different. Despite this, actually we were able to synthesize at least 3 compositions that remain quite stable even after long-term storage, of course, in the glove box. The next step, target preparation, is also very critical. If the target is loose or maybe uneven, it will never give you a good film. It behaves completely unpredictably during the sputtering. How we prepare the target? First, I press the powder with a copper holder with 10 tons. I use 10 tons and keep it for 30 minutes under the load, and then anneal it or not, it depends. By the way, some of my colleagues trust to automatic press, but I prefer to do it myself the hard way. As we can see, 2 compounds which was selected have degraded during the target preparation. Of course, such targets are not suitable for sputtering. Now we come to my favorite step, is sputtering process. We use a laboratory magnetron system, nano PVD. Unlike the general scheme I showed before, this tool has 3 sources, which makes it more conventional and useful. And we applied radio frequency sputtering mode because the direct sputtering works usually only for metals. This film which we use here we deposited on substrate with ITO layer. So I test different sputtering regimes, which I would roughly call soft, medium, and hard. It's more convenience. I would better not to show the numbers for power or pressure here, because what works best for me was like a dynamic mode. By this I mean keeping a constant deposition rate while adjusting other parameters during this process. It really helps to avoid local overheating and results in more uniform films. Okay, but let's buy soft mode. I mean a deposition rate for about 1 angstrom per second. Medium is 2 to 5, and everything higher I call like a hard mode. As I have said before, the sputtering process is very sensitive and unpredictable. And when you open the chamber, you never know for sure whether you have obtained good films or not. Everything influence on the result. It's a power, pressure, argon supply level, distance to substrate, chamber cleanness, so on. Okay, this is all I wanted to show you about the process itself, and now let's take a look at the result. What we can see, both the deposition mode and the post-treatment strongly influence the final films. Maybe this chart look a bit complicated, but the main message is simple. Annealing temperature is critical in this process. Film which annealed at 170 degrees show much better crystallinity than at 150 degrees. You can see here the crystallinity improves significantly. With the soft regime, we usually get lead iodide rich and unstable film. Actually, this film is not a perovskite at all. So this deposition mode is not suitable for this type of perovskite. So sorry. Medium mode combined with 170-degree annealing gives the cleanest perovskite fuzz, and high intensity mode produce strong perovskite peaks too, and good crystallinity also. But at the same time, it increases the background from the substrate. Maybe it's more defective films. Look here. Here we compare the film morphology for different deposition mode. In the high intensity mode, we often see the spherical hillcocks and very rough surface. In the medium mode, like here, it gives us much smoother and more homogeneous films with compact grains. So morphology clearly confirms that the medium mode is the optimal pathway for this technique. And here we look at the optical band gap from UV vis spectroscopy. Again, both the deposition mode and the annealing temperature play a role. And for medium mode, annealing at 170 degrees gives the most consistent result with the band gap. Sorry, with again band gap closer to 2.4. 2.4, sorry for my English. And the best linear fit, I think. In the high mode, we also get values in the same range, but if you see with more variation. These optical measurements show us what we saw before. Medium mode with proper annealing is the optimal condition for get good film. And this result, I think, finally clearly demonstrates that the optical properties of perovskites in films can be tuned simply just by adjusting the sputtering condition and subsequent annealing treatments. And the observing variation in band gap values is consistent with reports from other scientific groups who share their results using different fabrication methods. I think it's a really success for me. So, colleagues, instead of the conclusion, I will leave you with these thoughts. First, magnetron sputtering, I think, is not the easiest path, and maybe not even the best one. But it works, you see. And it opened a really possibility to move perovskite film from lab experiment to industrial fabrication. And this challenge is not finished for me. I'm very grateful to DFG for supporting my project financially. I really appreciate Professor Yana Vainzov and my young international team. They help and inspire me every day. Special thanks to Lex for his help, and also for organizing committee and our chairpersons today. And colleagues, thank you for your attention. And now I am open for your questions.
Thank you for joining us, and we have some small time for discussion, and we have questions from Professor Leonid Shahinian, Francevich Institute for Problems of Material Science.
Thank you for your presentation, and I have a couple of questions. Please tell me, did the composition of your targets changed up to the end or during sputtering? It's very important issue because the films deposited from your targets also will change its composition and all other properties as well.
Yes, thank you. It's a good question. First, the target I can use only one time. Because it's mostly full damage after sputtering. At this process, how it looks, the lead iodide part, which colored like yellow, go to the bottom of the target. And during the sputtering, when you have the stage like pre-sputtering to get the necessary condition in the chamber, we often lost this composition. For example, iodine part or bromine part can flow away from your target. There are different tricks to avoid this stoichiometry loses, but it's not work for all. It depends on your system which you're used to sputtering. It also depends the geometry of your target. But yes, of course, we have also technical secrets to avoid these losses. Yes, the stoichiometry of target changed during the sputtering.
If I understood well, then you mean that in some compositions, the content of your target is changed. In some compositions remain the same. And how it influences the film properties? I mean, optical properties and maybe others.
Of course, all these parameters influence on our final results. Of course, you ask me how it's influenced.
Oh, okay. And
it's like opening the Christmas presents. When you open this box and see something unexpected. Yes, I have a protocol, but it doesn't work every time. If I can get a repeatable sputtering, it's really a victory for me.
Okay. And the next, what is new in your work?
Okay.
In our institute, in 18th have been produced a lot of targets prepared from powder by methods of powder metallurgy. It was many compositions and for different purposes. But what new in your work now?
Okay. What is new in my work? We have maybe thousands publication with obtaining perovskite films in different countries. It's really popular and on time. But only maybe 100 of this publication deal with magnetron sputtering process. Because spin coating, the most popular method to obtaining perovskite film, it's good. It's very known. It's very famous and useful. But we don't have any possibility to create the object more than 10 to 10 millimeters. New in my work is a possibility to get the perovskite films using magnetron method. Concerning your question about the powder metallurgy in target preparation, to be honest, I'm not good in powder metallurgy, but we have a nuance here also, because we have a limitation in heat treatment. 170 degrees, as I talked about, it's maybe a maximum temperature that I can use managing these targets or all these objects, because after 180 degrees, all this composition mostly damages. It's really it's not easy to create the target from this powder. Thank you. Thank you for the question.
Are there any more questions? One more question from Victor Kisluk, Kurdyumov Institute of Metallophysics.
Hello, Victor.
Oh, thank you for your very exciting presentation. But, the new is the composition. Composition is always a specific thing. It's just continue the discussion. My question concerns the possible application. As I see from the last slide, it's photovoltaic. So
Yes.
photovoltaic needs at least two components. This is only one. And
Sorry, what do you mean two components?
no, you should have some internal electric field. To get the internal electric field, you should have at least two components, two layers. What is the second layer? P-type of
Yes, do you see my screen now? Because I see only my presentation.
I see.
Yes,
So
you can see.
And what is expected advantage of these
Yes,
composition?
I understand your question. You ask about efficiency. Yes.
And what is the role of this component? Is the window or its active layer? Thank you.
Yeah, it's an active transport layer. You can see here on this my presentation list. This is a PN device, and you also can use a conventional architecture. It doesn't matter. What can I say about this efficiently of this layer? This very complicated system, and every layer work together and at the same time independently. And I'm not good in device preparation, really, but I ask my colleagues who is, and they integrate this film into their device, and preliminary results show us efficiently at the level from 16 to 19%. It's not excellent, okay, but it also depend on another layers in this system, and also if you was born with both arms left, as for me, for example, you don't able to get a good device. You need a big experience in this area. But yes, this films working good and show us a good results. Another scientific groups demonstrate in their publication efficiently at the level maybe 26, or even I saw 31% of efficiently. It's higher than gallium arsenide, if I'm not mistaken, and also closer to silicon oxide. Yes. It's really prospective. It's potential.
It's another niche because this is the organic photovoltaic.
Yes.
Their niche is
Yes. Closer to this, the most prospective direction is field transistors. They have another problem in this area because it's very fast ionic transport and oxygen vacations and other thing, but it's potential to use like a field transistor. So.
Thank you, Irina. Good luck.
Thank you, Victor. Thank you all for your attention and being safe.
Thank you, Irina, again for joining us. I think it was also answer for my questions, because my question was, are you going to continue with magnetron sputtering to obtain perovskite films or not? I think
yes.
Yes.
Yes, I can answer on your questions.
Every challenge is very interesting. Yes.
Yes. Result I show you today is marked in my lab journal like a sputtering number 47, and it's concerned only with this composition, and I have many another composition to show. It's really interesting. It's like playground for chemicalists and physicists.
Okay, I think
So-
we can wish you all success in your magnetron sputtering challenge. Okay,
Thank you.
Thank you very much.
Thank
And
you.
dear colleagues, we should continue. And as I mentioned it before, we have some changes in our program. Konstantin Korotkov asked to move their presentation from oral to poster session. So we will hear him later at poster session. And I am very thankful Professor Leonid Shahinian, who agreed to make his presentation instead of Konstantin Korotkov. Please, Professor Leonid Shahinian, Francevich Institute for Problems of Material Science.
So I will repeat my good afternoon. And, you know, we just right now heard about the magnetron sputtering from different targets. And I will continue this. It happened so that my talk is connected directly with this previous report. So we investigated structural and compositional changes what occurred in multi-component alloy targets during ion bombardment. And the question, my question to this lady who was before me was, is something changed during sputtering of these targets? But I didn't obtain any more or less reply to my question. So let me continue. Next slide, please. Oh, this is magnetron sputtering, sketch of magnetron sputtering system. And main part of this system is tiny thing, very tiny thing, which is the core, which is the heart of the magnetron sputtering, because it creates the film-forming species under bombardment of this target by ions. It can be very different ions. For example, argon, nitrogen, oxygen, doesn't matter. So magnetron sputtering, as we right now heard, is widely used technology for fabrication of various materials, films of various. And target is a source of film for film material. So we can say that target is a father of the film. Father, do you understand what I mean? It is the father because from under the bombardment by ions, the film forms from these very small particles sputtered. It's from the target. Okay, and so we understand that the target properties directly influence properties of the film. And it is also clear that during exploitation of the initial properties of the target may change. So is it right or not was the problem which was posed in our investigation. Next slide, please. I won't stay on these details. If you want anybody, I will explain it after my talk. So next, please. The only what I would like, can you back the previous? the only to what I would like to pay your attention, the targets where high entropy alloys, which contain a lot of different various elements. So it's important for this our work. Please, next. So the target, it is the target. Due to ion bombardment, annual groove, racetrack sometimes they call, forms on the target during operation. With time of work, the groove becomes deeper and wider. And around 75% of ion current falls just on this groove. Side walls of the groove subjected to moderate ion bombardment, while remain target area is almost not under the ion bombardment. It means that mostly sputtered area in the target, only this groove, and all other areas almost didn't sputter. So the most changes which can experience the target is in this groove. And that's why we attentively investigated composition and microstructure of the bottom and side walls of the groove. Bottom and side walls. Next, please. Okay, so let we have a look through scanning electron microscope. What is this target on macro level? This is the target on macro level. And microstructure is non-uniform. This is for two different alloys. You see that the target contains two phases. One is the matrix, and it is black areas, black surface, and white points or lines. It is the inclusions of this in this matrix. The same you can see a little bit different, but the same is for different targets. It is the same. So let we have a look on micro level, the composition and structure. This is the inclusions as well as here, and this is the black areas is the matrix. And on macro level, the composition is more or less uniform, as it must be for such targets, for high entropy alloys. It is the composition. And pays attention to a little bit lower content of copper among the others. But if we will have a look on micro level, the composition, we will see that the composition of the inclusions is strongly enriched in copper and aluminum. The same we can see, we observe on this target, on this alloy. And so the conclusion from this slide is the targets are non-uniform in composition and in structure, microstructure. Please, next. And let we compare the composition of this. It's concrete. It's the same for others, but I took it as an example. This is a target at the beginning, at the very beginning, before sputtering. it's more or less uniform, and it should be as it is for composition of high entropy alloy. And at the end, you can see that the composition more or less strongly have changed. Instead of 10, 11, around 2.7% changed the content of copper, and the same we see for aluminum. So concentration of copper and aluminum in the target decreases with operation time. It changes. And it means that sputtering of deposition of films from near the end of the operation lifetime of the target will change also. I will show you a little bit later. Okay, next, please. This is the microstructure of the side wall. This is the after, at the end of the period of working of the target. It is the same, right? It is just for comparison. And if you will attentively look at these two pictures, you will see that these trenches, its trenches, appeared on the smooth at the beginning target, appeared trenches, and instead of smooth, we have rough surface. This is, again, inclusions, white points and lines, and it is the trenches. And if we'll compare the trenches, the position of trenches, they are completely repeat the trench, the positions of these inclusions. That is, it means that the sputtering mostly sputtered just these inclusions, because the trenches appeared just in these areas where exist these inclusions. So next time, please. Next slide. And if we will have a look at the microstructure of the bottom of the target, groove bottom. Before it was the side walls, and now it's the bottom, where the strong ion bombardment exists. And we see that appears these shapes are remind liquid solidified waves. That is, you see, it is like waves which were on the, and then they solidified after when temperature decreased. And this effect, it's very important thing. This effect indirectly indicates that the bottom of the grooves was melted. Whereas it is known that the temperature or the target temperature doesn't change strongly, and it is close to the temperature of the cooling water, because the target is tightly bound to the magneton block. Next, please. And let me have a look at the films deposited from the target, which with this composition. We see that at the beginning, the film was normally the same, almost the same composition as it was in the target. At the end of the target work time, it is the composition was changed, and we see that aluminum and copper were decreased in this composition of the films. And if sometimes we use this method, we applied the voltage to the substrate. And we see that under the severe ion bombardment, the content of copper and aluminum dropped seriously. Instead of 13, it is 2%. So both, and we can make some short conclusions that the target during its service lose the copper and aluminum. The same occurs with the film, and especially when it is deposited under ion bombardment around 200 eV. Next, please. Okay, so we have seen that the target properties changed during its working time. That is, microstructure and composition of all targets to the end of their lifetime have changed. It is the problem which was put in the beginning. What for we investigate these targets? And yes, we see that it is really have changed not only composition, but also a structure. Next, please. The question arises, what are the reasons for so crucial changes occurred in composition and microstructure of the targets during its service time? And we have a hint to it, namек, that the targets consist of two components. We have seen it, matrix and inclusions. That is, initial structural and compositional non-uniformity of the targets may be the real reason for changes which we observed. Next slide. To understand why and how initial non-uniformity in compositional and microstructure of the target influence their final properties, let us have a look at enthalpy of mixing of pairs of elements comprising the target. It's very important parameter. Enthalpy of mixing. It means that this enthalpy shows if it is negative when during combining of two atoms, the energy is released. It means that the energy of combination of these pairs is high, and they took with each other these elements with high energy, with high forces. But if please next, we will see there. But if that is, I will repeat, positive enthalpy leads to weakening or disappearance of chemical bonding. Negative enthalpy provides strong chemical bonding. We see here copper with other elements of the target do not interact. Moreover, it is they cannot be combined with each other, whereas copper and aluminum have negative chemical enthalpy, and they are tightly bound to each other. The same we see for all other components which are tightly bound to each other. That is, it means that, and they comprise these elements, they comprise the matrix, whereas whereas inclusions are combined mostly of copper, sometimes aluminum. So these elements do not friendly feel each other. Next, please, next time, full slide. Weak chemical bonding between matrix elements and inclusions results in formation of non-uniform microstructure of the target on micro level. That is just the reason for formation of two-mode, two-component elements of the target is the non-uniformity is the result of weak chemical bonding and formation of rough microrelief on the target surface at the end of the surface, also the result of non-uniform energy within the between the elements. And because of this, we revealed quite new effect is the effect of preferential sputtering. It is not normal for magnetron sputtering or for any of sputtering matters, just sputtering, I repeat, not evaporation and chemical vapor deposition and so on. But it is not normal. Preferential sputtering, it means that some components sputter with higher velocity, higher rate, because normally explains this mechanism why they do not sputter separately. So, and now let me turn to the next slide. So, combined effect of weak chemical bonding between matrix elements and copper and high sputtering yield of copper. Copper has maximal sputtering yield among all other elements presenting in the target. And just this combined effect of weak chemical bonding and high sputtering yield results in the appearance of effect of preferential sputtering of copper. And films deposited at the end of the target surface, as well as films deposited under ion bombardment, are also depleted in copper and aluminum. This means that the depletion of the films and the target under ion bombardment of the same elements is of similar nature. Please, the next. It is conclusions. I will, so, first of all, I would like to say that the posed issue in the very beginning of this of our investigations have been achieved. We have shown that really the target composition and target microstructure have changed up to there at the end. Why? The composition of films also changed when the films were deposited at the very beginning of the working time. They have one composition. At the end of the working time of the target, they also change their composition. And the reason for these changes is the initial non-uniformity, that is, matrix and inclusions of the composition and microstructure of the used high entropy alloys. So, and we also, new type of effect of preferential sputtering we revealed. The main condition for it is the micro inclusions in the target containing elements which sputtering yield is higher than that of the matrix. And specific micro relief on the surface of the targets upon the ion bombardment is a result of combined action of high temperature. We have seen that the bottom of the groove is under high temperature, and sputtering, normal sputtering effect. So, okay, next, please. Thank you for your attention. It's me. It's not from...
No, from internet, yes.
No, it's me. I can show you. Okay, so And okay, maybe questions, because if you have, I would like to show you next slide, but only, please, next. Is it possible? Oh, I would like to compare the microstructure of the films or of the target. It's the side wall of the target. And this is the shapes weathering figures. And if you compare these ones and with that, you will see that it is many features.
The same mechanism, yes. Material science in the nature.
Yeah, and just because the formation of these cavities is the result of different forces between the matrix and the inclusions. In these pores, there were inclusions, which were sputtered by weather, by temperature, and wind. The same is here. So, thank you.
Very interesting. I think you will be our keynote speaker for the next conference.
Okay.
Okay. Are there any questions? Lina Sartinska, please.
You told a problem, but what should we do to avoid this problem?
Sorry?
You told about problem that there is
nothing can be done, because it's nature of these high entropy alloys. They every time they will have the matrix and inclusions where, because the elements of inclusions do not friend with the matrix elements. So they every time you cannot to manage do something which will increase their bonding energy. Why not? I will show you again this table of enthalpy.
But we want to produce coating. We should do something with.
Try to do it, but it's only during first 10-15 hours of sputtering. Nothing else. Nothing. It's in the nature. You cannot overcome the nature forces.
So we should use short time.
Yeah, short time instead of sputtering about around 45 hours. Stop it in 10, 5, 15 hours. Stop the sputtering and deposit the film. That's all.
Thank you.
Are there any more questions? Okay. One moment. Okay.
Just about the how to solve this problem. Probably, I don't know. I'm not a specialist exactly in this field, but as just from common sense, is it possible to apply transverse field or to modulate magnetic field just to blur out this effect, to not to just to make this effect uniform, to make uniform evaporation of matter from the target?
No, I will repeat again. You know, the nature of...
Sorry, did you try it?
No, and I will do it because I understand that you cannot come together with of elements from the inclusion. Copper doesn't interact with other elements. It will be обязательно, он будет выделяться, понимаете? И поэтому ничего тут не сделать. Это природное явление. Вот и все.
Okay.
You understand in Russian? I hope yes.
It's better Ukrainian, but if you say Russian.
Okay, but you know.
But it evaporates not by itself. It evaporates as a result of bombardment. But if you can have a tool to operate with bombardment conditions, you also can manage to operate the evaporation of matter as I see this process.
I would like to say you that about evaporation from the such targets, it's a great problem. It's just revealed this effect that it can be evaporated also. Along with sputtering, it can be also evaporated also. But what combination of these fluxes, evaporated, and what meaning of these evaporated and sputtered fluxes. And again, we will have the problem with evaporation of different, if we will evaporate. If we will evaporate, just solely evaporate without sputtering, then we will see that it will be much worse than the films than we obtained by sputtering.
Okay, thank you very much. And one more question from me. Okay, there are some changes in the microstructure and composition, but how about the properties? How such changes influence on the properties of such alloys? Maybe it's not bad effect, yes.
Of the film?
Yes.
You know, I guess that it is very important composition of the films, because all properties of any film depends only on two properties: composition and structure. That's all. Nothing.
Yes, but is this effect crucial for properties or not?
I guess that I didn't investigate this problem. It's just the beginning, the beginning of this.
It's very interesting because sometimes such changes can be really crucial for properties, sometimes not. Maybe it's not.
You know, we have such an experience when we studied just films deposited one of these alloys. Very attentively, we investigated the composition and structure of these films, and not only. And it has been shown that it is crucially influenced the composition. If you will deplete these films in copper, the films become harder. If the copper will be enough, then it will be more or less soft.
Okay, and the last questions.
Okay.
You have studied the composition and of matrix and inclusions before the magnetron sputtering.
And at the end also.
At the end also, yes.
It was shown in this talk.
I mean separately in matrix and inclusions, yes.
Groove.
Groove.
We investigated the groove, because the most impressive changes could be only in the area of the groove, because it's under the sputtering, and whereas the other areas of the target, it's it's very bad, because only 75% of this target remains without any changes. But we should waste it, because the groove appeared, racetrack appeared on the target, and it cannot be.
Okay. Okay, thank you very much for very interesting presentation.
And thank you.
Dear colleagues, as I mentioned it earlier, we have some small changes in the program, and so we have many times for coffee breaks, because our poster session will start at 5 p.m. So I kindly asking you to hear one more presentations. Such presentations was in ceramic and glasses symposium, but unfortunately, due to some reasons, Vlad Billy was not able to present. So I kindly ask you to hear him. And Vladislav Billy is a member of our organizing committee. And he is PhD student. In such presentation is very important to pass my exam. So more questions is better for him. Are you agree to hear 15 minutes? Yes.
Yep. Yes.
Can we do this? Okay.
Okay. Okay. Oh. Dear colleagues, my name is Vladislav Billy, and yeah, oh, okay. And now I want to share my work about ab initio modeling of failure mechanisms in aluminum-doped boron carbide under uniaxial compression. Yep. Firstly, boron carbide is widely used as impact-resistant ceramic due to its hardness, low density, and high elastic limit. But it's prone to amorphization under high non-hydrostatic loads. Here on left picture, you can see shock waves profiles for commercial armor grade boron carbide and silica and ceramics measured with velocity interferometry diagnosis. Here it is. Boron carbide demonstrates post-yield software and which degrades its performance against high velocity projectiles. Yeah. On the right picture, you can see the impact crater after high velocity impact, and a small fragment from these craters was used to investigate its behavior under transmission electron microscopy here on the right. Yep. Here you can see the one amorphous region, and here you can see oh sorry, the analysis of this region, and after this investigation was made idea or hypothesis about amorphization. It's a very discussable question. Many different scientists work on this problem, and Fancini showed in his work that a problem can be catched but by one of the boron carbide's polytype. It's boron 12 CCC polytype, so it has boron only icosahedral, 12 atoms icosahedral, and 3 carbons chain. Yeah, there is many ways was supposed to solve this problem, but we choose doping as one of the most promising way because it can change chemistry of the chain of the possible problem. And additionally, in our previous work, we demonstrated that substituting in of aluminum in CCC chain is energetically favorable. So here you can see aluminum modified boron carbide. Yep. On the right picture. So in this work, we consider the simulation of uniaxial compression to along the inter-icosahedral chain to compare their failure mechanisms. Okay, about methodology. The DFT simulation was performed using the quantum espresso software package. For compression calculation, we used 2 per 2 per 1 hexagonal supercell and 180. This supercell have 180 atoms. DFT parameters you can see here, and simulation method, it was uniaxial compression in direction perpendicular to 001 plane with 0.01 strain steps. This compression method was used instead of compression along the C-axis, and due to better comparison between polytypes and due to allowing to solve problem of the high distortion during the experiment, DFT experiment. Yep. So now I want to remind the mechanism, first principle mechanism of boron carbide failure. Here you can see stress strain curve of boron carbide and boron carbide doped by aluminum. Here, blue boron carbide doped by aluminum, boron carbide by red. Up to the critical strain, the chain remains straight. Yeah. But after the critical strain value, a sudden pronounced bending of the chain occurs, and it's lead to the icosahedra become highly distorted but remain structurally identifiable. Although this loss of symmetry was considered as amorphization. The failure mechanism for the aluminum doped structure is distinctly more complex and gradual than undoped boron carbide. For this modification, we have here firstly atom of the aluminum atom and boron atom from the icosahedron move closer, and the icosahedra begin distort. Here you can see here, yes, here this boron atom and here this aluminum atom. They become closer and icosahedra become distort. Then after first stress, a huge stress drop here, new structure emerges. Some icosahedras change their forms into tabular structures formed by two layers of boron hexagons, while others retain the original form. Chains change their shape too. Some of them become straight. Here it is. While others lost their aluminum atom and it rearranged into the vicinity of the tabular structure. So it goes here. Here is our tabular structure, and here we have this aluminum atom that goes from this chain. Yeah, goes here. But at the strain 0.31, stress drastically drops to 5 gigapascals, which was considered as an ultimate failure. So conclusions, this polytype of boron carbide fails abruptly under compression due to the change buckling and repeat amorphization, while boron carbide doped by aluminum exhibits a more gradual failure characterized by local distortions like reconstruction and delayed collapse. Aluminum doping Aluminum doping can increase ductility and ultimate strain, although the peak stress is significantly lower. Thank you for attention. I'm ready for questions.
Thank you for presentation, for the late but presentation. Dear colleagues, do you have questions? Questions from your colleague.
Yeah, okay.
What further computational or experimental steps should be taken to advance this research?
Firstly, we want, it's a great question. Firstly, we want to finish all work with, okay. Firstly, we need to continue investigation with other polytype of boron carbide that consists of bore 11 and one carbon atom in icosahedra and CBC chain. Yeah, we should try to compare them. Next will be more complex investigation of the structures with defects, maybe using machine learning potentials. Because it's ideal crystals, and so we may have not so fully picture.
Okay, and one more questions from me. It's modeling, but are you not a modeling?
Only
But are you going to investigate the real structure of such material?
Yes, thank you for the question. Yes, we we made a prototype of this. It was not my work. It was made by Muratov in our institute. He synthesized this structure. It was composite that have two structures, but one of the main parts of this composite was this structure where he made an article about that. He supposed that aluminum can substitute in the chain. Yeah. And yeah, we will try to make investigations of this composite, and we will connect our calculation and this.
So you will have the chance to check your modeling in real life, yes?
Yeah, yeah.
Okay, and one more question is for me. Such amorphizations occur due to the impact, yes? It's due to the stress or due to the temperature, or it's a combined effect of the impact?
It's due to we can observe amorphization in boron carbide at any non-hydrostatic load.
It's a load is crucial, much more than temperature, yes?
Yes.
Yes, okay, thank you very much. Are there any questions?
Yep.
Oh, one more questions.
Okay, great.
Talk at the beginning, you just remind about the technique, shake wave profiles, and what is this
idea of this?
Yeah. And what is they relate to your calculations?
Yep.
Is there any associations?
Okay. Thank you sorry for I'm a bit nervous now. Thank you for your question. This methodic describes describes behavior of the material at shock impact. Yeah. Here you can see by red is shown silicon carbide. After impact, this line that go up, it says that this material tries to bear in load and tries to resist the impact. Yeah, while boron carbide, after which has higher this initial elastic shock strength, elastic limit. Houdinian elastic limit describes the limit, and and boron carbide didn't. We don't see the hardening and higher. I don't know. Higher resistance after more resistance after impact. Yeah, and a connection. It was supposed due to this glass-like behavior. Yeah, due to this amorphization. What is connection reason here? Here we see drastic drop of the boron carbide, of ideal boron carbide. When one of the structural element failures, like it's about chain, yeah, he drops all structure suddenly, yeah. While boron carbide doped by aluminum, yes, he has lower total strengths, but he don't lose his symmetry so rapidly. Yeah, and we think that due to this, we want to compare these values, these top values, when we have defects and more realistic structure, and maybe we will have different maximums, and probably, yeah, we suppose that this behavior is much better than this drastic strength loss.
Окей, thank you. Я перейду вже на українську, тому що на каву-брейк у нас тут, на жаль, тільки українці. Да? Колеги, я вас запрошую туди в коридор, там біля холу у нас кава. Ми розпочнемо постерну трішки раніше, але не сильно, о 5 годині, тому що не всі онлайн доповідачі знають про такі зміни в нашій програмі. Будь ласка, проходьте, тільки там не дуже тепло, тому якщо в кого є, одягніть щось. Ну і чекаю вас на постерну сесію. Okay, colleagues, I think we can start. Before the beginning of the poster session, I will remind about the rules of flash posters. We have 5 minutes for each presentation, but we don't have time for questions. So all questions can be discussed later after the symposium, okay? Okay, and we start with the presentation of Alexey Onoprienko from Frantsevich Institute for Problems of Material Science. As I understand, Alexey should be with us online. Alexey, are you here? No, sorry for mistake. It's we will start from Konstantin Korotkov. His presentation moved from oral to the poster session. Konstantin, please, you have 5 minutes.
Okay, my name is Konstantin Korotkov. I'm from Institute Problem Biomaterials Frantsevich. Is my report is analysis of impedance spectra of ferrum gadolinium oxide nanostructure with FD interaction. This analysis have two parts. First part is a Nacris rhodograph. For this rhodograph, we can see the electrical schematic. The pre-percolation thickness, less percolation thickness. We have odor for precipitation scheme. This scheme also have in microelectronic and other electronic position. In high thickness, high percolation thickness, we have inductivity scheme, and this is thickness is not the not been to the microelectronics techniques. Second chapter is the we calculated experimental the impedance parameters, and in the for this parameter we calculated dielectric permeability. This permeability we have frequency peak, and this peak is seen in phenomena spin precession. And in this phenomena we have reverse magnetic volumetric spin wave or direct. This wave um, uh, 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 calculate in micro technical theory. In this wave we can see in polarization peak in this is in frequency peak of 2.10 power 5. And this peak in no one. This peak is 2 for other range of frequency in radio, in FM diapason, in microwave diapason, in infrared diapason, in visual diapason, and in visual diapason we have experimental peaks in 620 nanometer. This peak is analog frequency peak 4.88001 times 10 power 14. And in ultraviolet we have one peak because it's last for gamma radiation, and this peak is only negative alpha, because this is not reserve. Reserve wave. Reserve volumic magnetic-static reserve wave or reserve wave. In conclusion, in Nyquist photogram we can see for signals less percolation this scheme have a capacitation character and height percolation thickness inductive character. In the frequency range 10 power 5 Hz, the dielectric dependence and that polarization have a percolate in the form of extremo at frequency. The formation of these extremos is probably associated with the spin noise effect. This effect have phenomena of reverse of direct volumic magnetostatic static spin voice. This depends.
Okay, dear Konstantin, we have only 5 minutes for presentation, so if you is possible, be shortly, please.
The dependents have two peaks. First, height 0 second. This is direct, and the second 0 all range of frequency. Less 0, this is reverse. The spin noise effect is characteristic of films with thickness less thickness of percolation.
Okay, thank you. Next presentation. Oh. Our next presenter is Alexey Onoprienko from Francevich Institute for Problems of Material Science. Alexey, are you with us? Okay, maybe later, next presentation. Volodymyr Ivashchenko, also from Francevich Institute for Problems of Material Science. Okay, next presentation. Dmytro Borovik. Thermal conductivity of plasma sprayed zirconium dioxide coatings at temperatures up to 1100 Celsius degrees. 5 minutes.
Hello, my name is Dmytro Borovik. I will present our work about thermoconductivity of plasma sprayed coating. This property is critical for design a reliable thermal barrier coating. The aim of this work was twofold. First, to develop and validate a reliable method of thermal conductivity at high temperature. Second, to obtain new data for zirconia-based coating for different nickel content. Here is our method. We use a special substrate for the coatings, for the samples. Here we tested 3 coatings: pure ceramic, 10% nickel, and 30% nickel. Here you can see the samples after testing. This graph shows the process. We heat the sample and record the temperatures. The model based on one-dimensional heat conduction to calculate cold side temperature. The red line, this is our reference. The surface, the hot surface is red line. The model, the black dot are model result. The purple line is experiment. We change the thermal conductivity until the black dot fit purple line. Now have the main result. The black line is pure ceramic. It has the lowest conductivity. The red line is 10% nickel. It's highest conductivity. The blue line is 30% nickel, much higher. And one important point, above 600 degrees, whole curve rise faster. We think this comes from radiation inside the coating. Now, we have conclusion. 2 conclusions. First, our combined computation and experimental method is reliable for new materials. Second, we obtain valuable data for coatings with different composition. This data can be used for design better gradient thermal barrier coatings. Thank you. This is the end of my talk. Please, next.
Thank you. Yes, next presentation is also will be made by Dmytro Borovik. Twice, yes?
Yes. As you can see on this slide, our goal was develop dense ultra high temperature ceramic coating with low porosity, about 3%. We combined optimized composition powder and high velocity flame fuel. We obtain by combining optimizing powder composition and high velocity flame spraying, we achieved a fine and stable microstructure with good oxidation resistance. These coatings can work up to 1200 degrees Celsius in air and are promising the airspace, energy, electrode materials with good oxidation resistance. And any space application which reliable for which stable under extreme heat resistance. This is the end of my talk. Thank you. Excuse me.
Okay. Thank you very much, and please take your certificate. Okay, it's Natalia Vigilnyanska from Patton Electric Welding Institute of the National Academy of Science of Ukraine. Natalia is not here, but maybe she is online. No, okay. Next presentation. Ruslan Krivoshabka from the National Science Center, Kharkiv Institute of Physics and Technology, Ukraine. Are you online?
Yes. Hello. Do you hear me properly?
Yes, we can hear you. Please present your slide. You have 5 minutes.
Thank you. Good afternoon, everyone. The research I would like to present today is entitled Nitriding as a Method for Modifying the Properties of Nitride Coatings. Improving hardness and reducing friction are among the key goals in surface engineering. Several techniques are used to achieve these effects. One of them is the deposition of nitride coatings, which significantly increases surface hardness. Another one is the nitriding process, which enhances the wear resistance of steels, alloys, and coatings. So the main purpose of this study is to investigate how the nitriding process influences the micro-hardness and wear resistance of vacuum arc nitride coatings of different compositions. The materials used in this work include stainless steel substrates, single-layer coatings, and multi-layer coatings deposited by vacuum arc evaporation, the composition of which you can see on the slide. All coatings were deposited using a modified Bullard 6 vacuum arc installation. The cathodes were made of pure metals like titanium, molybdenum, and zirconium, as well as several complex alloys. The substrates were mere polished stainless steel samples, carefully cleaned before coating. The plot 6 setup allows both deposition and nitriding within the same technological cycle. The nitriding was performed in a two-stage vacuum arc discharge. Before the process, the vacuum chamber was pumped down to 1.3 times 10 to the power of -3 pascals. The samples were served at a bias voltage of -1 kilovolt under a nitrogen pressure of 0.5 pascals for 30 minutes. The micro-hardness of the coatings before and after nitriding was measured using a micron gamma tester under a load of 0.5 newtons. The tribological properties of friction and wear behavior were studied on a micron tribo machine, both in air without lubrication and in the presence of water. Now let us look at the main results shown at table 1. After nitriding, we observed a significant improvement in mechanical properties. For example, the micro-hardness of steel increased from 4.6 to 10 gigapascals. In most coatings, both hardness and crack resistance increased, while the friction coefficient decreased. This means that the coatings became more durable and wear resistant. Interestingly, multi-component coatings were found to be more responsible to nitriding than simple nitrates, most likely because of the formation of stable multiphase structure. In some cases, such number 4 and number 6 coatings, the effective elastic modulus slightly decreased, while the number 7 coating showed a small increase in friction, about 15%. For high entropy coatings, nitriding led to a lower friction coefficient, confirming the beneficial effect of nitrogen ion bombardment. A comparison was made of the dependence of the friction coefficient of the study samples on the level of elastic strain in the initial state, figure 1a, and after nitriding, figure 1b. The presented data show that an increase in elastic strain leads to a decrease in the friction coefficient in most cases. We also found that the friction coefficient decreased as elastic strain increased and that plasma nitriding reduced surface roughness and leading to more stable and smoother sliding behavior as shown at figure 2. To summarize, nitriding in a nitrogen plasma environment has a positive influence on the physical mechanical properties of nitride coatings. After treatment, micro-hardness and strength parameters increased by 10 to 20%, while the friction coefficient and surface roughness decreased. And a clear correlation between friction and elastic strain was also observed. That's all. Thank you for your attention.
Thank you very much for your presentation. Our next presentation is the presentation of my colleagues from Frantsevich Institute of Problems of Material Science. However, today I will present this work instead of Tetiana Chevichelova. So I would like to present you our work, its influence of carbon-plated nickel graphite powder on the structure and typological performance of the titanium chromium carbide based coatings. In this study, we investigated the effect of nickel-gladed graphite additives on the structure and wear performance of the titanium chromium carbide nickel plasma coatings. Titanium chromium carbide is a promising candidate to replace, for example, tungsten carbide because its titanium chromium carbide is not critical raw materials, especially for Ukraine. And the idea of such carbide, it's a solid solution of chromium into titanium carbide. And due to the additives of chromium, we can increase oxidation resistance of such carbide. Nickel we used as metal binder for such coatings. However, to improve to decrease friction coefficients of such coatings, especially in the conditions under dry sliding conditions, it was idea to use additions of nickel gladed graphite. In this study, we use different contents of such additives, 5, 10, and 15 weight% in the coatings. Of course, first of all, we deposit such powders onto the steel substrate using plasma spraying at Francevich Institute for Problems of Material Science. We studied the effect of such additives, the effect of content of such additives on the structure of the coatings. You can see that the structure is very complex. It consists of the particles of titanium chromium carbides. It was interesting because the initial size of such particles was 60, 100 micrometers, but in the coating the size was much more smaller, up to 10 micrometers. The structure is very uniform, and you can see the additives of graphite, such as black inclusions in the structure. They also placed very, very uniform. And then we tested such coatings under dry sliding wear conditions. And it was determined that introducing of nickel-plated graphite is very effective to decrease friction coefficients, as well as the wear resistance, as the wear rates of such coatings. However, the more additions we have, the smaller was the coefficient of friction. So we think we will continue this work because it is currently we don't understand, because we can see that the effect of such additives on the wear resistance should be investigated much more deeply, because in not all cases such additions are effective for wear resistance. So we will continue this work and maybe we'll present you the next results later. Thank you, it's all. And our next presentation, I would like to invite Igor Smirnov from National Technical University of Ukraine, Igor Sikorsky, Kyiv Polytechnic Institute, with his presentation, Synthesis of Powder for Thermal Spraying of Abradable Coatings for Gas Turbine Aircraft Engines.
Good afternoon. I am Igor Smirnov, professor of the Igor Sikorsky Kyiv Polytechnic Institute, Welding Department. The work is devoted in the synthesis of powder for thermal spraying of abradable coatings for gas turbine aircraft engines. Abradable coatings increase the service life, efficiency, and economy of gas turbine engines, which why this work is relevant. For spraying such coatings, powder of the system aluminum silicon nitride boron was synthesized using a method of mechanical chemical alloying. The basic powder was of two types, spherical and elongated. Spherical, elongated, type 1, type 2. After mechanical chemical alloying, the powders were sprayed using atmospheric plasma method. The spraying modes were provided by a laminar plasma jet. A cross-section of the sprayed coatings can be seen on the poster, second row. Coating, cross-section coating from powders type 1 and cross-section coatings from powders type 2. The spectra and chemical composition of the coatings can be seen on the poster, third row. Type 1, type 2. The thickness of the type 1 coatings is 500 plus and minus 15 microns. The thickness of type 2 coatings is 300 plus for minus 50 nanometers. The porosity and microhundreds values differ significantly in the coatings. So, row. In the type 1 powder coatings, the porosity is 2.8% and the average microhardness value is 0.3 gigapascal. In the type 2 powders coating, the inverse dependence is observed. The porosity is 9.5% and the average microhardness value is 0.41 gigapascal. The high hardness of the type 2 powders coatings is due to a higher concentration of oxide, primarily aluminium. More special recommendations, particularly concerning the gas abrasive and erosion resistant properties, will be provided following comprehensive operation testing. This work was funded by the Ministry of Education and Science of Ukraine. Thank you very much.
Thank you very much. Please take your certification.
Дякую.
And our next.
Yeah. Good afternoon, dear colleagues. My name is Olena Stepets. Can you hear me correct?
Okay, Elena, please present your slide. You have 5 minutes.
Okay, good afternoon, dear colleagues. My name is Olena Astapets, and today I'm pleased to present the results of our recent research on absorption and dispersion of hydrogen and electrodeposited cobalt-uranium alloys. This research was conducted at the Vernadsky Institute of General and Inorganic Chemistry of NAS Ukraine within the Department of Electrochemical Materials and Science. Studies of electrolytic superalloys, alloys of refractory metals such as molybdenum, tungsten, rhenium, and with iron group metals have drawn great attention due to their unique mechanical and physicochemical properties, high corrosion resistance, hardness, wear and heat resistance, and magnetic characteristics. Depending on the electrodeposition conditions, coatings with various compositions, phases, and surface structures can be obtained, allowing the targeted optimization of their functional properties. Such alloys also show high electrolytic activity in the hydrogen evolution reaction, namely HER, and are promising for water electrolysis electrodes. Rhenium coatings allows rhenium coating alloys are practically advantageous, and their composition can be tuned over a wide range to achieve the desired balance of catalytic activity, corrosion resistance, and hardness. According to the Sabatier principle, the effective HER catalysts should interact with the stored hydrogen neither too strongly nor too weakly. This work particularly focuses on studying the electrodeposition of cobalt rhenium alloys, their electrocatalytic activity in HER, and hydrogen uptake of coatings with different rhenium contents in 1 molar potassium hydrate at 40 milliamperes per centimeter square for 10 minutes. Going to the synthesis and structure, a series of cobalt rhenium alloys were synthesized by galvanostatic electrodeposition from a perophosphate ammonia electrolyte at 50 degrees Celsius. Coatings with rhenium content from 17.7 to 43.8% atomics, and the current efficiency up to 76% were obtained, depending on the current density and per net ion concentration in the deposition electrolyte. Sorry
for that. We will continue in 1 minute.
Okay, I'll wait. Great. I will proceed with the X-ray diffraction patterns of the cobalt rhenium alloys with different rhenium contents. Show that the peak burning and shift towards smaller angles indicates a decrease in crystalline size and increase in lattice parameters during the formation of a solid solution of rhenium in the hexagonal close-packed and face-centered cubic modifications of cobalt. At 44% atomic rhenium, the formation of nanocrystalline textured coating with basal planes 001 parallel to the coating surface is observed. Getting to the electrocatalytic properties and interaction with hydrogen, the voltammograms show that the anodic peak corresponds to the absorbed hydrogen with the maximum uptake for the alloy containing 34% atomic rhenium at the right picture, and the sharp decrease at 43.8% atomic rhenium. Kinetic studies of in 1 molar potassium hydroxide revealed that the hydrogen evolution over potential decreases for alloys with 17 to 30% rhenium, indicating the higher catalytic activity. The 30% atomic rhenium alloy showed the best performance with an exchange current density of 1 milliampere square centimeter, while further rhenium increase suppresses the reaction. The optimal activity is linked to the alloy's hydrogen absorption ability. Cobalt rhenium coatings with 30% rhenium can absorb up to 6% of atomic hydrogen, interacting through two mechanisms. First one is dilution of atomic hydrogen in the solid solution lattice and formation of intermediate hydrates typical to the rhenium compounds. Waldenberg studies revealed the presence of cathodic diffusion limited current, which is likely associated with hydrogen diffusion from deeper layers of the coating with the reversible formation of the decomposition of AB2 type hybrids. The cathodic hydrogen evolution involving such intermediate hydrates can be described through the reaction you can see down the slide on the right. Alloys with 25 to 30% of rhenium demonstrate the highest electrocatalytic activity in the hydrogen evolution reaction. So in summary, we successfully obtained the electrodeposited cobalt rhenium alloys and found that both hydrogen evolution activity and hydrogen absorption capacity reach maximum at about 30% atomic rhenium. This composition combines solid solution formation with intermediate hybrid formation. Also, hydrogen absorption during deposition causes internal stress and cracking, and the resulting condensates show high efficiency as HER catalysts and provide a solid basis of designing advanced electrolytics and hydrogen storage materials. Thank you.
Thank you. And the next presentation will be, I would like to invite Marek Gorel. I know that you are online, yes?
Yes, hello.
Okay,
like to,
but
yeah.
yes, but please wait a minute because we have some troubles with the to present. Yes.
Okay, I will present it as short as possible. In our experimental, we use new, theoretically new composition of thermal spray powders containing nickel, chromium, and aluminum, and chromium carbides. But in this experimental, we not use it as a typical application like tungsten carbides or chromium carbides. We are resistant coatings, but like something new between typical repairing or bond coats which contains nickel, chromium, and aluminum or similar materials, to check if what is the properties of this alloys which contains only 30% smaller amount of hard particles. In this case, we use two typical powders which was available on the market. We mix the chromium carbide and the nickel chromium aluminum powder from Oerlikon Metco. The thermal spray was made on the using the A60 plasma torch. It is not typical F4, but the single electrode plasma gun developed by company from Germany, Thermico, and they will use their powder feeder and other equipment which was for this kind of coatings deposition. According to there is no information about parameters, we make small research in the influence of spraying parameters on the properties, on the microstructure, and selected results are presented on this poster. We changed two parameters. One of them was the power current of plasma torch between 300 to 700 amps, which was the first amount of the first power current 300 amperes are typical for spraying of carbides. The 500 was a middle compromise standard parameters, and 700 amperes is typical for thermal barrier coating. So it is high increase of temperature and energy. The similar parameters which we changed was also the hydrogen flow from 4 to 12 normal liters per minute. The rest of plasma gas, it was nitrogen. Of course, if we increase the power current, we can increase the coating thickness because we're melting the particles of the powder. In the difference of porosity was not significant, no big difference. It was about 2%. Also when we change the power current or the hydrogen high flow. The next step was an analysis of microstructure, and as you see on the mapping on the right, on the down of the post of the slide, you can see that there is no good mixing of two phases. It's metal matrix and carbides. Also, we tested the influence of these parameters on some mechanical and tribological tests, including the hardness. But we has also no significant result, which was a little bit different according to power current and the hardness of the and using the different hydrogen flow. So we cannot make the significant conclusion in this case. In the case of erosion test, it was made using ASTM standard, using the sand, which was it was similar to sandblasting of the surface of the sample. And in this case, we observed that the best parameters, in our opinion, is the standard parameters. It's 500 amps and 8 liters of hydrogen. In the case of tribological tests, the best properties was connected with the higher power current and the highest flow of hydrogen. Probably we can explain that it was connected with the melting and decarburizing. I know that this term is in Europe means totally different from greenhouse effect and similar green problems, but in our problem, the decarburizing of carbides are a very big problem in thermal spray. So probably this hard phase was decomposited, decarbonizing was observed, so the sliding properties was much more better. So as a conclusion of this short presentation, I think that it is possible to make powders using this mixture, and the next step of our activity will be connected of replacement of chromium carbides by other materials like oxides, because they are much more easier to obtain and use it as hard particles in the wear resistant coatings made by thermal spray. Thank you very much.
Thank you very much. It's really nice to hear you today, and we are very thankful you join us because Marek Gorel is from Poland, so it's
from
really
Russia, from close to Ukraine.
Thank you. Our next speaker, Mykola Sokolovsky from Paton Electric Welding Institute of the National Academy of Science of Ukraine. As I can see, Mykola is online, yes? Please wait a minute. We will switch on your presentation. Yes.
Good evening. My name is Mykola Sokolovsky, and I'd like to present the results on the study on the corrosion durability of the deposited layer on the thin-walled base of structural elements produced by laser radiation. During our wider study of laser cladding processes for manufacturing of structural elements from high alloy corrosion-resistant steel on a thin-walled base, the issue of reduction of the powder material corrosion durability, which was applied by such technologies during their use in corrosive environments, was considered. The aim of this study is to determine the effect of laser radiation intensity used to form a deposited layer on a thin-walled base made from AICI 316L high alloy corrosion-resistant steel on its corrosion resistance. To apply the deposited layer onto the thin-walled part, a laser cladding method was developed for creation of structural elements on pre-made thin-walled parts. The principle of this method lies in multi-track cladding with gaps, allowing for controlled cooling of the base metal and deposition of metal powder into grooves created by two individual tracks. During the experiments, a range of operating modes was used. Laser power of 1.5 to 2.5 kilowatts, the movement speed of the laser 2 meters per minute, and the powder delivery rate of 25 grams per minute. Specimens of the deposited layer were tested for pitting and intergranular corrosion resistance using standard methods. Results of the study of pitting corrosion resistance, shown on the slide, has shown that all pittings have occurred on the base metal and did not penetrate the base metal for more than 0.5 millimeter. Additionally, after additional mechanical post-processing, the amount of pitting dropped to the values close to that of the uncladded base material. Intergranular corrosion resistance was assessed by optical metallography after bending, results of which are also shown here. In all cases, no grain boundary degradation was detected, which is satisfactory to the standard. According to the results of corrosion tests, it was determined that the specimens of the layers of high alloy corrosion-resistant steel, ACI 316L, applied utilizing laser cladding technology on a thin-walled base, made from high alloy corrosion-resistant steel, can be considered resistant to pitting and intergranular corrosion, while maintaining the range of the values of operating modes of where power density is at 30 to 45 kilowatts per centimeter squared, as well as the energy input of 35 to 80 joules per millimeter. These results align with the results of various studies by other authors who have been testing similar cases in other case studies in different industries. The results of the study were used for further development of laser cladding technologies for thin-walled parts used in various extreme conditions, and further deepening of knowledge about modern laser cladding processes and expansion of the scope of this technology. Thank you.
Thank you very much. Our next speaker is Ilya Morsh from Kyiv Aviation Institute. Please. Micromechanical properties and microtribological behavior of detonation spray, titanium, chromium carbide, nickel coatings under dry and lubricating environment.
Okay. My name is Murshilya, and today I present my poster with SAM via behavior of detonation sprite, titanium, chromium, carbonate, nickel coatings under dry and lubrication environment. For creating via resistance coatings capable of operated at elevated temperatures, titanium chromium carbide is a suitable choice due to its high hardness, 28 gigapascal. Excellent via resistance and thermal stability. The objective of this study is to conduct a comparative analysis of the micromechanical and microtribological properties of detonation spray, titanium, chromium carbonate, nickel coatings. The titanium, chromium carbonate, nickel, titanium, chromium carbonate based coatings with 25 weight percent and 33 weight percent nickel binder were applied onto steel substrates via detonation spread. It was previously shown that plasma and detonation spread, titanium, chromium carbonate, nickel coatings demonstrate high wear resistance under dry sliding conditions. Also, we have test nano indenters. Tests were performed to determine hardness and elastic modulus by analyzing the load displacement data obtained during the indentation of the Berkovich indenter into the coating. Microtribological reciprocating tests were carried out under both dry and lubrication conditions. Water, diesel, biofuel, aviation fuel, and oil we used and lubrication environments. Post-test examination of via track was performed using interference profilometry. The titanium chromium carbide nickel detonation spread coatings exhibit dense microstructure with well bonded splats composite of fine titanium chromium carbide participle and a nickel based binder. The lowest wear values for both coatings we are observed in the oil environment, whereas and the highest wear rates occurred in the water. The phenomenon is attributed to the rebinder effect, which involves the wending action and surfactants. Water promotes microcrack initiation and accelerates material fracture. And finally, the titanium chromium carbide 25 weight percent nickel coatings showed a higher wear rate in the water environment compared to the 33 weight percent nickel coating. The behavior is associated with the higher brightness of the 25 weight percent nickel coatings, which leads more intensive, brittle, fiery under the conditions. However, the 25% nickel showed better and other results. That's all. Thank you.
Thank you. Our next speaker. Is Sergey Lavrys. Sergey Lavrys, are you with us? Maybe online? No, so we are moving to the next speaker. It's Олексій Покропивний. Да. Олексій Покропивний, are you with us? Okay, next speaker, Юрій Луговський. Offline. Please.
The name of my report is Strength Physics and Wear Resistance of Metal Ceramic Coatings. Introduction. Let us consider the question of the theoretical basis of the concept of wear resistance. In accordance with the work terms and definitions, friction, wear, and lubrication, terms and definitions GOST, wear resistance is the process of separating of a material from the surface of a solid body and or increasing its residual deformation during friction, manifested in gradual change in the size and or shape of the body. This means the destruction of the material under the action of cycle shear stresses, and therefore this process should be described from a standpoint of mechanics and solid-state physics. Modern methods of fracture mechanics during fretting fatigue of materials and coatings are presented in the works of, for example, A.A. Hatsianovsky, IPMS Nassau, and others. However, the fracture mechanics and fretting fatigue do not consider the relationship between the strength of the surface regions of materials under the action of frictional forces and its structure, and therefore has a limited theoretical basis for the controlling the strength and their resistant characteristics. The known dependencies of hardness and micro hardness of the parameters of the material structure in the development of their resistant coating do not take into account the cycle nature of the wear process under the action of friction forces and require to use the theory of dislocations and the known dependencies of strength physics of the dimensions of structural elements of materials under the action of cycle laws of the type equations and yield strength equation 1 and fatigue strength equation 2 from the structure parameter delta. There delta is the average size of structural elements, and two coefficients are in the equation with the variable n being the number of cycles to failure from 10 to power of 5 to power of 8 cycles. These equations are given in monographs. First, физические основы прочности токоплавких материалов Трефилов, Мильман, Фирстов, наукова думка, 1975. And second monograph for second equation структура, прочность и сопротивление усталости микрокристаллических и микрослойных материалов. Мовчан, Фирстов, Луговской, Киев, наукова думка, 2015 год. Second part of our results is structure, прочность, experiment results. The experiment results of the studies, these materials are presented in the table we see, which lists the compositions and cycle strengths of experimental detonation coating and two photos of fatigue characteristics which you see. You can see 10 materials and coatings in this table. Work of determining the parameters of the structure delta is ongoing. Thanks for your attention.
Thank you very much. From Karpenko Physico-Mechanical Institute of the National Academy of Science of Ukraine. Victoria, are you with us?
Yes, I'm here. Do you
Okay.
hear me?
Yes, we can hear you very well. Please start.
Okay, good afternoon, dear colleagues. I'm pleased to present our research on the properties of coatings for current collector in molten carbonate fuel cell. This work is being carried out within the framework of the NATO project named Direct Liquid Fueled Molten Carbonate Fuel Cell for Energy Security. First of all, I would like to tell something about molten carbonate fuel cell. This is a device that directly converts chemical energy into electricity, and one of their key advantages is the ability to operate in hydrocarbon fuels without external reforming, and which simplified the system and reduced cost. In molten carbonate fuel cell, bipolar plates or current collector are very important metallic components, and they must remain chemically stable in a corrosive carbonate atmosphere at high temperature. It's about 650 Celsius degrees, while maintain good electrical conductivity and low contact resistance. However, a commonly used stainless steel suffer from hot corrosion in molten carbonate environment, and it limits their long-term durability. In our previously studies, we identified materials that demonstrate both corrosion resistance and good electrical conductivity under fuel cell operating condition. At the current stage of the project, our goal is to develop a coating that not are only protective, but also has a catalytic activity, capable of promoting hydrocarbon reforming directly at the anode site of the fuel cell. Since the main concepts of this project involve direct utilization of liquid hydrocarbons, developing such catalytic coatings is a very crucial step toward improving fuel flexibility and overall system efficiently. At the beginning, we have investigated corrosion mechanism on both sides. You can see on the poster from anode side where liquid hydrocarbons are present, and cathode side where a mixture of oxygen and CO2 exists. Based on this analysis, we selected several coating systems, focusing primarily on chromium and cobalt as key element. In our study, we deposited by PVD method multi-component coatings with thickness about 5-6 micrometers, containing cobalt, chrome, and additional alloying elements such as niobium and vanadium. You can see in the table 1. As a substrate, we use stainless steel grade C16L. It's known stainless steel. The samples were tested using our standard methodology. The main characteristic studies were long-term oxidation resistance at 650 Celsius degree and electrical conductivity. Surface morphology and composition were examined using by scanning electron microscopy with EDX analysis. You can see the chemical composition of these coatings, and X-ray diffraction was used to identify phase transformation during oxidation. As a result, we can see that coatings number 2 exhibited excellent adhesion and maintain a homogeneous microstructure even after long-term exposure. And from table 2, you can see that compared to uncoated steel, this samples demonstrated approximately twice the oxidation resistance with a significant lower mass gain. Moreover, this coating surface retain high electrical conductivity after oxidation, indicated that the oxide layer formed was thin and conducted. But this is just the start of our project, and our next step will involve studying the behavior of these coatings in molten salt environment and evaluated their catalytic activity in hydrocarbon media. This is all according this presentation, and you can thank you for attention on this poster. And I will continue with another one. Yes. Yes, this is mine. So let me present my next study, but which, unlike the previous one, has a more fundamental focus. It's devoted to the development of the new electrically conductive materials with high oxidation resistance, but based on a max phase of the titanium aluminum carbon system. The main aim of this research was to develop coating that combine both these characteristics in the oxidized state. To achieve this, we investigated coating deposit from max phase, focusing on the effect of niobium and of the effect of alloying of niobium and tin. It should be noted that this work was made possible only through collaboration between several research groups. The coating were obtained in the National Science Center Kharkiv Institute of Physics and Technology, where specialists implemented deposition processes using cathodes fabricated from max phase, and the cathodes themselves were made at the Beckel Institute for superhigh materials. So these coatings were deposited using also PVD technique, but into a titanium alloy substrate. You can see this on the slide. This composition is low alloying titanium materials. We choose this technique because it ensures coatings with excellent adhesion, density, and homogeneity. From both literature data and our experience, it's known that niobium and tin can enhance the oxidation resistance of coatings. However, it's important to emphasize that in max phase, niobium is M element, while tin serves as A element, so they influence may be different. The results show that adding each element separately improves the oxidation resistance of the coating. You can see this number 1, 2, 4, 5, and 6. But combine them together reduced this effect. You can see line 3 when we added niobium and tin at the same time. In terms of electrical conductivity, tin addition did not yield a positive effect. You can see this 1, 2, and 3 materials. Whereas niobium doping significantly improved surface electrical conductivity. But the content of niobium was also a critical parameter. You can see that we choose 3 different modes, and the best results were achieved when concentration of niobium was below 0.05%. We obtain nano coatings with very dense, pore-free, you can see figure A, and demonstrate strong adhesion to the substrate. X-ray diffraction, I don't show in this slide, but X-ray diffraction analysis revealed the formation of titanium oxide with anatase structure. And after this, we can conclude that our coatings, titanium, niobium, aluminum, carbon, max phase coating produced by PVD methods exhibit high oxidation resistance, stable surface electrical conductivity, and has good adhesion to titanium alloy substrate. These findings indicate that such materials, such coatings, can be promising materials for different applications where we need combination of such properties. So this is the end of my topics. Thank you for your attention.
Thank you for joining us. We are moving for the next presentation. It's Yevgen Ivashchenko, creation of hardened cobalt carbon niobium and niobium carbon cobalt coatings on titanium alloys by electric spark alloying. Yevgeny, are you here? I saw him online. Okay, maybe later. Next speaker, it's Alexander Palchakovsky. He is offline. We are glad to see you here.
Okay, dear organizing committee, dear participants, now I will show you a presentation about ion irradiation-induced solid-state reaction in nickel-titanium multilayers. Nickel-titanium thin films with shape memory effect are promising materials for micro-electromechanical systems. The layer-by-layer technique deposition with varying thickness allow for easier control of the film composition, but requires subsequent thermal treatment. Ion irradiation is a promising surface modification technique that can promote further phase formation to achieve shape memory effect. In the present study, the effect of argon and nitrogen ion irradiation on the structure properties of nickel-titanium layered stacks with different modulation periods. This is thickness of B layer has been investigated. X-ray diffraction data shows that as deposited stacks are formed with polycrystalline structure, ion irradiation of all stacks induced bordering of nickel peak compared to the as deposited sample. Furthermore, when argon irradiation is applied to an intermediate modulation period, it induced diffusion controlled the formation of nickel-titanium phase, which indicate peaks of nickel-titanium phase 002. Seems this profiling data confirms that development of irradiation-induced intermixing between nickel and titanium layers, regardless of the applied ion species type. However, argon ions having larger atomic radii and mass compared to the nitrogen ions yield a larger diffusion effect. More pronounced metal intermixing was also observed when using a smaller modulation period. Residual stress relieved that all stacks have compressing stresses in nickel layer rising from the deposition condition. Ion irradiation with both species brings a rather slight increase in stress up to minus 31 gigapascals. The most pronounced effect of radiation with different ions is observed in electrical properties, while the resistivity of as deposited and ion irradiated samples is similar. The argon irradiation induced a resistivity increased by 2 times for the smallest modulation period of 20 nanometers. The study reports the investigation of ion irradiation effect on the structure, phase, and chemical composition, residual stress, and electrical resistivity of nickel-titanium layered stacks. It has been shown that ion irradiation-induced diffusion can be achieved in such stacks, avoiding the amorphization stage. Furthermore, both phase and chemical composition can be effectively tuned by using appropriate conditions of ion irradiation type and selecting the optimal thickness of the metal layers. This finding could be the potential interesting for the development of the controllable formation of MEMS and NEMS devices involving shape memory effect-based nanomaterials. Thank you.
Thank you very much. Please. Our next speaker is Irina Pogreluc. Irina, are you with us? No, so we are moving to the next presentation. It's my presentation. Microstructure and wear behavior of titanium chromium carbide based and tungsten carbide based laser glad coatings. I will be very short because I understand that all are tired. Okay, this study aims to compare the effect of titanium chromium carbide and tungsten chromium carbide particles on the wear behavior of the metal ceramic laser gladed coatings under high temperature abrasion conditions. The coatings were obtained at Austrian Tribology Excellence Center by laser gladding using two mixture of powders. It's titanium chromium carbide with 30% of self-flexing alloy and tungsten carbide with also 30% of self-flexing alloys. You can see the structure of such coatings. The thickness was after the treatment was about 600 micrometers, and the structure of both coatings are heterophase and consist of the particles of carbides distributed in metal matrix. Such coatings were tested under abrasion conditions according to the ACTM G765 standard. It's dry abrasion rub and wheel tester. But in high temperature configurations, we use 3 temperature room, 600 Celsius degrees and 800 Celsius degrees. The result was very surprising even for me, because it was found that increase in temperature leads to the increase in wear rates of the coatings based on tungsten carbides, but at the same time it results into the decrease in wear rates of titanium chromium carbides. Of course, you can see the difference, yes. The coatings based on the tungsten carbide after the wear test was almost fully destroyed, while the coatings based on titanium chromium carbide works very well. Of course, it was very interesting why such different behavior, and we have studied worn surfaces, but not only worn surfaces, we additionally made cross sections of the wear tracks of such coatings, and we have found that the increased wear rates of tungsten carbide based coatings at high temperature is connected with the high oxidation of tungsten carbide. You can see the destruction of the grains of tungsten carbide. However, the wear mechanism of titanium chromium carbide was very different, because we have found that some particles of abrasive particles, it was silicon carbide, during the wear test introduced into the structure of the coatings, and it leads to the strengthening or reinforcing of the coating. So abrasive further works as reinforcing phases in such coatings. And it was the main reason of such different wear mechanism, was the main reason of such different results during such investigation. It's all, and today we have one more presentation. It's Lyudmila Nirkova. Lyudmila, are you with us? Lyudmila, please switch on your microphone. I can see you are online. No? Okay, so when we are waiting for Lyudmila, maybe we will check who else with us. Maybe
Hello.
Alexey Onoprienko.
I'm here.
Lyudmila, we hear you, but not very well. Please increase the sound, maybe.
Oh.
Okay, try again.
Hello. Can you
Yes.
hear me?
Yes.
Can you
Yes.
hear me? Hello, everyone. I'm glad to present you our report, investigation of stress concentrator in weld on stress corrosion cracking of welded joint X70 steel in neonatal pH solution. This work was conducted under support of National Academy of Science of Ukraine and Polish Academy of Sciences, in compliance with agreement on scientific cooperation between Polish and Ukrainian Academy of Sciences for years 2022-2024. Steel X70 is widely used in gas pipelines for its toughness, strength, and weldability, though welding can weaken the heat-affected zone. Cooling rates affect microstructure. Slower rates form ferrite and pearlite structures. Faster ones yield a circular bionit, improving toughness. Optimal ratios of titanium to nitrogen and alloying with titanium and boron enhance impact energy by increasing a circular ferrite. Weld metal is typically the weakest zone, but well-distributed inclusions improve properties. Stress corrosion cracking studies show bionitic and ferritic steel resist cracking better in neonatal pH. Stress corrosion cracking sensibility ranks as weld metal more than heat-affected zone, more than base metal. Cracks often start in the heat-affected zone and propagate along shear stress planes. The study devotes tough X70 welds and evaluates stress corrosion cracking resistance under cathodic polarization in neonatal pH solution NS4. Stress corrosion cracking was investigated on X70 steel specimens and welded joints at a polarization potential of minus 1.50 volt and in air, figure 1. It was determined that breaking of the welded specimens occurred at a lower relative elongation, figure 1, curves 4 and 5, than that for the base metal, and the presence of stress concentrator accelerated that process, figure 2, curve 5. The fracture of the welded joint with the stress concentrator occurred along the weld metal, which correlates with the impact toughness measurements and underscores the high toughness properties of the welded joint. From the analysis of the figure 3, it can be concluded that during breaking of the welded joint, the maximum deformation is concentrated in the base metal outside the weld zone, which is due to its higher strength. It is likely that the rupture origin is located in this region. This correlates with the stress corrosion tests results showing that the welded joint broken through the base metal, figure 1. In addition, the area of maximum deformation in the base metal specimen during fracture is larger than that for the welded joint without a stress concentrator. During the fracture of the welded joint with a stress concentrator, the maximum deformation occurs beneath the nose, presumably when the crack nucleus forms. In conclusion, I want to say a welded joint of X70 steel for gas pipeline using SV08G1NMA wire was developed. Corrosion mechanical tests in natal solution at a potential minus 1.52 volts revealed stress corrosion cracking through the base metal, confirming high quality of the weld. Finite element simulations in NCs showed that during tensile failure, maximum deformation in intact joints occurred on the base metal, exceeding the base metal specimens and indicating increased brittleness. With a V-shaped stress concentrator, cracking runs over the weld metal, with peak deformation beneath the notch. These results demonstrate the joint's durability and significant role of stress concentrator in crack propagation. Thank you very much for your attention.
Thank you very much for a very nice presentation. And again, I will try to introduce, maybe our speakers are ready now. Олексій Онопрієнко, Володимир Іващенко, Наталія Вигільнянська, Сергій Лаврись, Олексій Покропивний. No, yes. So I think we can finish our session. Thank you very much to all the participants who have joined us today offline or online. It was really close and friendly atmosphere in our coatings community, yes. So thank you again, and I think we will meet next year. Okay, thank you very much.
Thank you very much.